Electronics is my passion, and I've been playing with circuits for as long as I can remember. I started as a young maker in my parents' garage, I later studied electronics in college, and today I work as an electrical engineer in Silicon Valley. Do you want to create projects based on Arduino and Raspberry Pi, but don't understand how the electronics work? If your answer is yes, congratulations! This is the course for you. A modern electronic project is composed of three main ingredients. You have a microcontroller board, you have to write some code to tell the micro what to do, and finally you have electronic components and circuits to interface with the external world. The web abounds with tutorials to help you get started with number 1 and number 2, but I couldn't find any course of electronics that was both complete and easy to understand. That is why I decided to create this course. By the end of this course, you will be able to recognize the most important components in electronics, understand a bit of the physics that make them work, and study simple electrical circuits. This knowledge will help you to understand and design circuits based on Arduino and Raspberry Pi, and above all, to make good projects. Electronics can be intimidating, but it's easy to learn with the right help. Enroll the course and start learning electronics today. Hi, and thanks for enrolling in this course. I hope you're excited to learn how electronic components and circuit works. This is an introductory course, so no previous knowledge of electronics is required. To get the best out of the lessons, you should be comfortable with some basic arithmetic. We will often write and solve equations, in particular when we analyze simple circuits. Understanding a bit of physics can help too, but it is not required. The course will start from the fundamentals, so everything that is needed will be explained. And finally, no special hardware or software is required. The course will be taught using whiteboard screencasting, which means that you will see me think through problems and write down concepts on the screen as in the example shown. I think that this way of teaching is helpful for both students and instructors, as it allows you to follow my thinking process and problem-solving methods, as it forces me to go through each of the required steps and to explain things clearly. Hi, in this section we're going to talk about electric current. We are going to discuss atoms and electrons, we're going to define what is an electric current, and we're going to talk about the current direction convention. Matter is made of atoms. We are made of atoms. Everything we touch is made of atoms. The reason why I'm bringing up atoms now is because I want to introduce the electron, which will be required to explain the electric current. On the right, I try to represent the structure of the atoms. There is a central part, which is the nucleus, which is made up of protons and neutrons. And then we have a third type of particle, which is the electron, that is floating around the nucleus. You can see here there is like a cloud of electrons around the nucleus. Protons have a positive charge of value E. E has a certain value that we'll describe later, while electrons have a negative charge of value minus E. Neutrons have no charge. E is equal to 1.6 multiplied by 10 to the power of minus 19 Coulomb, where Coulomb is the unit of measurement of the charge. Atoms are usually neutral, which means that they have the same number of electrons and protons. Now that we talk about electrons, we can talk about electric current. Electric current is simply the rate of flow of electric charge. Let's look at the example here to the right. Let's say you have an electrical wire, so like a piece of copper, for example. So we are looking at a section of the wire actually continues here and there, so it's just a little section of it. And let's say you have 3 electrons on the left side, and you are an observer, you are somewhere in the middle of the wire, and you just monitor a certain section of this wire. You just look at a particular section. Now, I could ask you to do a certain experiment, which is in a certain amount of time, delta t. You can choose the amount of time. It could be 1 second, 1 hour, 1 year. It could be 1 microsecond. It could be as long or as short as you want. You will just be sitting there and count the number of electrons that pass from left to right. At the end of the experiment, you will have a certain number of electrons here, and E. And if you multiply the electron by E, which is the charge of 1 electron, you basically know what is the total amount of charge that passed. If you divide the total amount of charge that passed, which I'm writing as Q here, by delta T, what you get is the electric current. Electric current is the amount of charge that passed during a certain time along a wire. The unit of measurement of the electric current, the natural unit of measurement, will be Coulomb divided by second, because we have charge divided by time. But because the current is such an important thing, it has its own unit of measurement that is called ampere, and it's indicated with A. So you can see here I substitute Coulomb divided by second with A. There is a very important thing to remember, which is the convention of the direction of the current. The general convention is to have the direction of the current to be the same as the direction of movement of positive charges. What does it mean? Given that usually in electric circuits and wire, what moves are really electrons, and electrons have a negative charge, the direction of the current is the opposite of the movement of the electrons. So in this case, there will not be the right direction. Let me cancel it. But the direction of the current that you measure will be the opposite. It will be in this direction, so from right to left. The first question wants to imagine to be a person sitting by an electrical wire for some reason that is observing a section of this wire during a certain amount of time, which is equal to 6 seconds. You measure a certain amount of charge moving from left to right and another amount of charge moving from right to left. In particular, the amount of charge moving from left to right is equal to 4 Coulomb, which I'm representing here with 4 little balls left to right. But at the same time, you also measure an amount of charge equal to 7 Coulomb that is moving from right to left. The problem wants you now to calculate the amount of current in amps given the delta time and given the amount of charge that moved through the wire. Solving the problem simply requires the knowledge of the definition of a current, that is defined as delta Q over delta T. Which simply, this equation simply states that the current is defined as the rate of charge moving through a wire, or the number of charge that you observe during a certain amount of time divided the amount of time. Now, for this problem, delta T is easy to calculate because it's 6 seconds. It's actually defined by the problem. Delta Q is a little bit more complicated. However, if you recall the definition, the correct definition of a current, delta Q is in effect the net amount of charge that is passing through the section of a wire. So in this case, because we have 4 Coulomb moving from left to right and 7 Coulomb moving from right to left, we can say that the net amount of charge moving through the wire is an amount of charge equal to 3 Coulomb moving from right to left. So we could cancel this, and we could say that the net amount of charge is simply equivalent to 3 Coulomb moving from right to left. So now we know what is the delta Q that we have to use to solve this little equation. This is 3 Coulomb. Now we can very easily solve this little equation. So I will be equal to 3 divided by 6, which is equal to 0.5 amp, or 500 milliamp. The next question wants you to determine the direction of the current that you've just calculated. The current is equal to 0.5 amp, or 500 milliamp, but this could be going from left to right or from right to left. Determining the direction of the current is pretty easy. Just remember that conventionally, the current always moves in the same direction as the positive charges. Now, in this example, we have calculated that the net amount of charge in the end is equal to 3 Coulomb. So 3 Coulomb is a positive amount of charge. So we have an amount of charge that is positive and it's moving from right to left. Therefore, the current is also going from right to left. So at the end of the day, we can say that in this wire, we have a current equal to 500 milliamp that is moving from the right side of the wire to the left side. To answer this question, we need to calculate the value of the current, considering a case where the delta time, the time during which we do our measurement of the charge, is not anymore 6 seconds, but it's only 2 seconds. Everything else stays the same. So the amount of charge that we see during these 2 seconds is the same that we saw before during 6 seconds. What is the new value of the current? Well, the equation is the same as before. Let's take a little area here to do the math. So I is still equal to delta Q divided by delta T. Now we know that delta Q is 3 Coulomb. Delta T now is 2 seconds. So the final result is 1.5 amps. So the current now is 3 times bigger than the current that we had before, that was 0.5 amp. This makes sense because we have the same amount of charge during a time that is 3 times shorter. So the rate of charge is 3 times larger, hence the current is 3 times bigger. In this section, we're going to talk about the electrical voltage. We will start describing what work and potential energies are. We will talk about forces between charges. We will introduce electric fields. And finally, we'll be able to define the voltage. Let's try to define work. When I say work, I don't mean like a job, but I mean the definition that a physicist will give you. So work, as defined on the left, is done on an object when a force acts on it in the direction of its motion. So this definition is probably not super intuitive, so I come out with a little drawing here on the side to explain it a little bit better. Let's say there's a person here, and this person wants to push an object with a certain mass, and he wants to push the object in this direction. Now, what the person will do will push, so will apply a certain force, F. This force will be in the direction of the motion, obviously. And after a while, the person hopefully will be successful and move the object from that initial position to another position at a certain distance L. Now, in this very simplified example, the work that a person has done, which I'm indicating with W, is equal to the product of the force multiplied by the distance. So the unit of measurement in this case is Newton, which is the unit of measurement always used for forces, and meters, which is obviously for the distance. This unit of measurement is also equivalent to joule. Now that we understand what work is, we can talk about potential energy U, which is the capability of a force of doing a work which depends on position or configuration. This is really the key. I have a little example here to understand it better. Let's say you have a ball of a mass m. It could be really any object with a mass that at a certain time 0, it is at a certain height h. Now we know that every object with a mass is subject to the force of gravity, a force that will take the object, push it down, and bring it to the ground. So after some time, at a time t, the object would have gone from the height h to the ground, so height equal to 0, for example. According to the definition of potential energy, at a time 0, the object has a potential energy equal to F multiplied by h, because in that moment, just because of the position of the object, so here how we connect to the definition, just because of the fact that the object is elevated from the ground, the force of gravity F can act on it and do a certain work. Remember that you have work when the object moves in a certain direction and there is a force applied to it in the same direction, which is the case in this example. At time t, the object is on the floor, there is no net force applied to the object anymore, and the object and also the height is 0 now, so the potential energy is 0 in that case. Work and energy, as you can see, are interchangeable in a way, so they're both measured in joule. One thing that is really important to highlight for potential energy is that the potential energy of an object is not an absolute value. So, for example, in this case, we say that when the object is, the ball is at a certain height h, the potential energy is exactly F multiplied by h. In reality, it is possible to demonstrate that every potential energy is defined plus minus a certain arbitrary constant. As long as we apply the same constant to all the other potential energy in the system, everything works. But what does it mean? This sounds a little strange. Now, the energy could be any value. What I'm trying to say is simply that The only things that really matters, the only thing that really has a significance is the difference of energy. For example, between time 0 and time t, the difference of potential energy between the ball is always going to be equal to F multiplied by H. Doesn't matter what is the constant that we add, because when you do the difference, the constant will be simplified. So saying that the ball has energy equal to 0 on the ground, it's perfectly fine, but it's just an arbitrary convention. This is something really important to understand, because potential energy is intimately related to voltage, and the same concept, exactly the same concept, also applies to the voltage. When you say that in a certain point there are 3 volts, in reality, all you're saying is that in that point there are 3 volts more than some other point. It doesn't really mean that that point is exactly absolutely 3 volts. It's simply the difference relative to another point of the circuit. We are almost ready to explain what voltage is, but before that, few other simple concepts. So the first is shown here to the right of the slide. Don't read the text for now. This is very simple. This drawing is simply showing something that you probably already know, which is that charges of the same sign repel each other. So whether they are both positive or also both negative, there will be a force that pushes them away. And by the way, this force is called Coulomb force. Whereas if the charges, they have different sign, they will attract each other. This is all nice and easy, but there's probably a question in your mind. It certainly was in mine. How does this charge know that there is another charge Q with the same sign of the charge, so that a certain force F is going to be applied to it, depending on the distance d between the two charges? This is an important concept because as human beings, we're used that if you want to communicate something, you have to emit some sort of signal. Audio if you talk, video if you wave your hand. But here, that's not the case here, because charges don't have ears or they don't have eyes. So how do they communicate? Well, to explain this phenomenon, physicists introduced the concept of electric field. Every charge emits electric field in all directions around them. You can think of the electric field as a sort of a sound wave. Just as a sound wave, the intensity of the field is higher close to the charge and becomes lower and lower as you go away from the charge. The electric field will spread at an infinite distance, but obviously at some point it will be really, really, really tiny. And the other charge Q, depending on the relative distance between the two charges, will fill a certain electric field, and depending on the intensity of the electric field in the position of the charge Q, it will be subject to a certain force F. So electric fields are used by charges to feel the presence of each other and reacting accordingly to Coulomb's law. Let's try now to understand what is the connection between electric field and potential energy that we'll now call electrical potential energy because we're talking about charges. The picture here is a similar example as before. We have two charges, Q1 and Q2. For Q1, I show the electric field, which is emitted radially by the charge. The electric field is indicated with E. There is a little arrow here just to indicate that in any point of the space, it's not enough to tell the value of the electric field, but you also have to indicate what is the direction of the electric field. And then we have Q2 here, which will fill the electric field. The intensity of the electric field that Q2 will fill depends on the distance r. The higher is the distance r, the lower is the intensity of the electric field. Q2 will be subject to a certain force F, which depends on the value of the electric field where Q2 sits, multiplied by Q2. The force F applied to Q2 will push Q2 away and will do a work on Q2, because again there is a movement and a force in the same direction of the movement. So because there is the possibility of a work to be done that arises from the relative position of Q2 and Q1, we can say that Q2 has a certain potential energy. To summarize, a charge in an electric field has electric potential energy because work can be accomplished by the field via Coulomb forces. Similarly to the example before, where the ball had lower energy when it was on the ground, in this case, Q2 will have lower energy if it's very, very, very far away from Q1, because the intensity of the electric field is very small. Some work can be done, but it's a very small work. Whereas if the two charges are very close to each other, they have a lot of potential energy because the work that can be done is greater. It is possible to demonstrate that the potential energy of the charge Q2 can be written with this equation. So U is equal to K, which is a constant, multiplied by Q1, Q2. So it depends on the value of Q1, obviously, because the higher is Q1, the bigger is the electric field. It depends on Q2, because the bigger is Q2, the bigger will be the force. So the bigger will be the work that will be done. And it also depends on R, on the distance, because the smaller is the distance, for the same value of the charges, the higher will be the electric field in the position of Q2. We can finally talk about voltage. Voltage is electric potential energy per unit of charge. So in the example before, if this was the equation of the potential energy for Q2, the voltage at Q2 at the position of Q2 will be equal to K, which was a constant, Q1 divided by R. So you see it's simply the same equation, we just eliminated Q2. The voltage is a more convenient way to talk about electric potential energy in electrical circuits, but it's intimately related to the electric potential energy. Voltage, as you certainly know, is measured in volts, and the symbol of volts is a capital V. In this section, we'll learn what is electric voltage. We started talking about the physical definition of work. We then move on to potential energy. We talk about Coulomb force between charges. And finally, we talk about electrical potential energy and voltage. These are all fundamental and very important concepts. And while these are not used in the day-to-day work of an electrical engineer or of an hobbyist, I wanted to walk you through this part with the hope that I could give you an intuitive understanding of what voltage is. Let's have a little recap of what we have learned so far. So in the previous section, we learned that current is made by moving charges. In the case of electrical circuit, we have electrons that move. So we have some amount of negative charge that somehow is on the move, and that generates electric current. In this section, we also learned that charges are subject to an attractive or repulsive force, which is based on their polarity. What this means is that if you take two positive charges and you put them close to each other, they will want to run away. Same if you take two negative charges. Conversely, if you take a positive charge and a negative charge, they will want to attract each other. Voltage is an indication of how strong is the force applied to a charge, which indicates how much the charge wants to move. Let me give you a little intuitive example about this. On the right, I represented a wire in two different conditions. So the wire is the black box. You can think of it as a box where you can put a certain amount of charge into it. In this case, I've assumed that we have three positive charges in the wire. And we have two different scenarios. So scenario 1 and scenario 2. So in scenario 1, the charges are uniformly distributed. So what does this mean in terms of voltage if you want? Well, charges are not allowed to escape the wire, so they have to stay inside. And these charges have the same sign, they're all positive. So they also don't like to stay close to each other. So if you let them be wherever they want to be, they will distribute uniformly across the wire, because they have no other reason to distribute in any other way. So that is a scenario where the energy of the charge is the minimum possible, because they're already in their preferred condition, in their preferred state, far away from each other, and try to use up all the space available in the conductor. So in this case, voltage is equal to 0, charges are moving, there's no current. In the second case, somehow you were able to accumulate a lot of positive charges close to each other on one side of the wire. What do you think is going to happen the moment you let the charge free to go? Well, the charge will immediately sprint toward the right, because they don't like to stay close to each other, and they see a lot of empty space on the right of the conductor. That will cause a net movement of charge in one direction, so it will generate a net current from left to right. So you can say that in this case, you have a voltage different than 0, higher than 0 with that direction, because the charges are not allowed to be in their preferred state, which is the state of minimum energy, but they're forced to be in a position they don't like. The current that will develop in scenario number 2 will only exist for a short amount of time. At first, the current will be rather high, because these charges really don't enjoy staying close to each other, so they will spring to the right. But eventually, the current will go down to 0. And at the end, after a long amount of time, the scenario number 2 will look just like scenario number 1, where charges are in the minimum energy state, uniformly distributed across the wire. In order to have a constant current across the wire, you need to have a device able to apply a constant voltage difference between the two terminals of the wire, and this device is the battery. Now that both current and voltage have been discussed, we can introduce the concept of signal and noise. Current and voltage are not fixed quantities. They can and usually change with the time inside the circuit. Here you can see the definition of electrical signal. An electrical signal is an electrical quantity, such as current, voltage, or electromagnetic wave, that can be varied in such a way as to convey information. On the right, you can see two examples of electrical signals. This image is a capture from an oscilloscope. An oscilloscope is an instrument that can be used to see how the voltage varies across time. In this image, the voltage at two nodes of a circuit have been captured. This will be one node and this will be the other node. Now we don't know exactly what's happening here, but as you can see, the voltage is going up and down in a way that sounds somewhat predictable, and it definitely looks like a behavior that is intended for a circuit. So this is what we call electrical signal. Conversely, noise is an electric disturbance in a circuit that interferes with or prevents with the reception of a signal or of an information. You can think of it as the buzz on a telephone or snow on a television screen, like shown here. This graph here shows how the voltage looks like when it's carrying just noise and no signal. As you can see, the voltage here is just going up and down in a random fashion and not carrying any information. It is important to make sure that the signal is always much bigger than the noise. Let's now look at some notable type of signals. This will allow me to introduce some terminology that I will use in future lessons. I will discuss voltage signals for simplicity, but similar consideration apply to the current as well. The first type of signal is the constant signal. This is a signal that has always the same value at any time. This voltage is also called DC voltage. So this is called constant, but also DC. The second type of signal is the pulse. A pulse is a signal that starts at a certain level, it goes briefly to another level, and then it goes back to the original level. The pulse can go up, can go down, and the two levels are arbitrary. So this signal is called pulse. Other notable signals are the step and the spike signal. This is a step, and this is a spike. A step is just part of a pulse, just the edge that goes up or that goes down, that is the step. And you can think of the spike as a very, very short pulse. Finally, this signal is called ramp because the voltage increases or decreases at a steady pace. In this lesson, we're going to talk about periodic signals. A periodic signal is a signal that repeats its value in regular intervals or period. Here the definition. Let's look at an example. On the right, we have a sinusoidal signal. The cycle is the part of the signal that keeps repeating itself. If we look at this signal, we can see how we can use this part of the signal as the cycle. This part. In reality, there are infinite choices that you can make for the cycle. For example, one could decide to use this as the cycle. It doesn't matter. As you can see, a periodic signal is composed by the infinite repetition of the same cycle over and over. Here I'm indicating that the signal will continue here and will continue also in this direction. This is how a periodic signal looks like. The duration of one cycle is called period, and it's measured in seconds. So in this case, we decided that this is our cycle. So this will be one period. Periods are indicated with a capital T and measured in seconds. One interesting parameter for periodic signals is the frequency. The frequency of a periodic signal indicates how many cycles are completed by the signal in 1 second. Mathematically, it is the opposite of the period, and it is measured in hertz. So the frequency is indicated with F is equal to the inverse of the period T, and it is measured in hertz. The amplitude of a sinusoidal signal can be indicated in different ways. The easiest way to represent the amplitude is simply to measure the distance between the center of the waveform and the peak. In this case, this will be the amplitude, and we can call the amplitude A. Another way to indicate the amplitude of a sinusoid is to use the peak-to-peak amplitude, which in this case will be the distance between the two peaks, and it's obviously equal to 2A because the waveform is perfectly symmetric. Other famous electronic signals are the square wave, that looks like this. This is also a square wave, where the values are only positive for the voltage. This type of waveform is very popular in digital systems, and it is used to transmit information or just to generate the clock of a CPU, for example. So this one is really popular, and this is the square wave. Other type of notable signals are the triangular signal, which looks like this. So you see the cycle is a triangle that keeps repeating. So this is triangular. And then another type of periodic signal is the sawtooth waveform, which looks like this. Signals can be divided in two big categories, analog and digital signals. In this lesson, we're going to talk about the difference between the two. Let's start with the analog signals. We have a definition here. Analog signals are signals in which any value of the voltage or the current is used to transmit information at any given time. Even if the voltage on a circuit is limited between two values, for example 0 volts and the value of the battery voltage, there are still infinite possible values of the voltage in between, and each one of them at any single given time is transmitting an information. Let me give you an example. Here I try to represent an audio signal. Audio signal moves smoothly between different values, and we know that each of the points of the curve at any given time is giving us an important information. It's communicating what is the value of the pressure change in the air due to a singer or an instrument. So we don't want to lose any of these points because each one of them is important. Even points that are very close to each other, like this one and this one, they're still carrying a different information that we want to keep, so that our analog signal is as rich as possible. In digital signals, on the contrary, the value of the voltage or the current is used to represent only a finite number of possible values, usually only 2. Let me give you an example. This looks like a classic digital signal. The voltage moves rapidly between 2 possible values, up and down, up and down. The 2 possible values of the voltage are either called high and low for high voltage and low voltage, or most of the time they're just called 1 and 0. So in this case we have a 0 at the beginning, then it becomes a 1, 0, 1, 0, 1, and 0. Now before we move on, I want to make a very important point. Digital signals tend to look like this. The voltage jumps up and down, but that doesn't mean that the voltage is actually really jumping between the low value and the high value. If you take this edge, for example, and you zoom it, you will see that the voltage is initially low, so it's a zero logic level. Then it will start rising. It will probably ring a little bit, and then it will settle to the new value, which is the high value corresponding to a logic 1. Voltages cannot change instantaneously between one value to another. They can't do it physically. So we can say that all signals are continuous and analog in their nature, and really the only difference between analog and digital signal is the different interpretation that we give to the value of the voltage or the current. With analog signals, any value of the voltage or the current at any given time is important in carrying information, while with digital signals, we simplify things and we just say that voltages that are high enough are a logic 1, and voltages that are low enough are a logic 0. So for instance, if we look at the zoom waveform that we have here, there is a difference between this point and this point. This point is a little bit higher than this other point, but because they're both high enough, there's no difference of information there. They're both logic 1s. How do we determine what is a logic 1 and what is a logic 0? Well, the designer of the circuit will have to define two thresholds. One will be somewhere here, and is usually called VIH, and the other one will be here, and it's usually called VIL. Every voltage higher than VIH is a logic 1. Every voltage lower than VIL will be a logic 0. Voltages in between are carrying an undetermined logic state. So it's undesired value for the voltage. And that is one of the reasons why digital signal tend to move as quickly as possible between logic 0 and logic 1. There's no reason for the signal to be in between the thresholds. It's not carrying any information. In this section, we're going to talk about batteries. We are going to define how a battery works, what is the meaning of the voltage of a battery, and how to find and calculate what is the internal energy of a battery. The image on the right shows a battery, like a big AA battery here, connected to a light bulb through two wires. A battery is composed of three main elements. There is an electrolyte, which is a gel or a liquid. And in this electrolyte, there are two metallic plates immersed in it. One of them is the cathode at the positive terminal, and the other is the anode at the negative terminal. Anode and cathode use two different metals, depending on the specific battery. Now, chemical reactions occurs between the cathode, the anode, and the electrolyte, and the net result of that is that you can imagine a build-up of electrons where the anode is, and a shortage of electrons where the cathode is. The fact that there is a build-up of electron at the anode generates an electric field inside the battery. The electric field will have this direction, so it's going from positive charges to negative charges. This will also mean that the electrons will want to go towards the anode. This is easy to understand because if you think about it, the electrons are a bunch of particles with a negative charge. For some reason, for the chemical reaction, they ended up being bunched up into a little area, but they don't really want to be close to each other because they are negative charges. They really want to go as far as possible from each other. Unfortunately, the electrolyte not only generated the initial chemical reaction that caused the buildup, but now prevents the electron from going from the anode to the cathode. So when you have a battery that is not connected to a circuit, there's really nothing to do for the electrons but to stay there. When you connect a circuit to the battery and you close the loop, you are giving the electrons an alternative path to reach the cathode. Now that the circuit is connected to the battery, the electrons have a way to reach the cathode, and one by one they will go along the wire, they will go through the light bulb hopefully will emit some light, and eventually they will reach the cathode. When there's no buildup of electrons at the atom anymore, the battery has electrons that are uniformly distributed. There won't be anymore any electric field within the battery. There won't be electric potential energy between the battery. And that simply means that no net work can be done on electrons, which also means the electrons don't really want to move from where they are. So even if you connect the battery to your circuit, you will not have any movement of electrons. One thing that I want to highlight here is that despite the fact that the electrons go from the anode to the cathode, because they are negative charges, the conventional direction of the current will be the opposite of the movement of the electrons. So the current will be assumed to be positive and going down from the cathode to the anode. Let's continue to analyze the example of the battery connected to the light bulb. If this battery is an AA battery, that means that we have a difference of potential equal to 1.5 volt between the two terminals. What does it mean? As we discussed before, voltage is the electric potential energy per unit of charge, and it's measured in volt. So that simply means that for each electron that goes from the anode to the cathode, the battery will have to do some work to push the electron across the circuit. And the work that the battery will have to do, it is equal to what calculated by this equation, which is 1.5 volt multiplied by the charge of the electron. Because the energy per unit of charge is 1.5, so if you multiply by the charge of one electron, then you get the energy that is spent on that electron to make the electron go from the anode to the cathode. The final value is quite small, 2.4 multiplied by 10 to the minus 19 joule. Now, an AA battery could have about 10,000 joule of energy. That means that it can move a certain number of electrons before completely discharging, and calculating the number of electrons, it's quite simple. We just divide 10,000 joule divided by the energy of one electron, and we get that the total number of electrons that can be moved by this battery is equal to 4 followed by 22 zero electrons. Because voltage is potential energy per unit of charge, it is also defined plus or minus an arbitrary constant. For example, if we call this node A and this node is called B, all I can say is that VA minus VB is equal to 1.5 volt. So the voltage at VA minus the voltage at VB is equal to 1.5 volt. But the value of the voltage at A and the value of the voltage at B could be any combination of numbers whose difference is 1.5 volt. Usually, to make things simpler, the node of the two that has a lower potential is assigned with a voltage equal to 0 volt. So usually VB in this example will have 0 volt, and as a consequence VA will be equal to 1.5 volt. The node that is at 0 volt, in this case B, is usually called ground, indicated with G and D as well. And most of the time the circuit will also have a special symbol to indicate this node, and this symbol could be looking something like this, just like a triangle hanging from a wire, or something like this. These symbols imply that that point, that node, is physically connected to the earth, to the ground, under your house, for example. The reality is that it's not true most of the time. Think about a mobile phone. It's definitely not connected to anything. It is a standalone device. But the symbol is used nonetheless to indicate that that node is the node considered to be a 0 volt. In the previous example, I mentioned that an AA battery can have an internal energy equal to 10,000 joule. While you're probably familiar with the fact that the AA battery is a 1.5 volt battery, you probably never heard any amount of energy in joule specified for the battery. That is because usually the internal energy of a battery is expressed in milliamp per hour, which is a way to indicate the total charge inside of the battery. Remember that milliamp, it's a unit of measurement of current, and current is charge divided by time, and hour is time. So when you multiply current by the time, you get charge, Q. So here I'm just doing that calculation for you. So multiply 2000 milliamp per hour, which is a good value for a battery, multiplied by 3600 seconds, which is the number of seconds in an hour, and you get 7200 coulomb. So that is the total amount of charge, Q. Now the energy, if you want to have it expressed in joule, you just multiply the amount of charge inside the battery multiplied by the voltage V, which is in this case is 1.5 volt. Remember that the voltage is the energy for a unit of charge, so if you multiply by the total charge, you get the total amount of energy. And in this case, you get a number that it's about 10,000 joule. In this section, we're going to talk about resistors, which are very important and omnipresent components in electronics. We'll define what is resistance. We'll talk about resistor in series and in parallel. We'll discuss the Kirchhoff voltage and current laws, and in the end we'll also talk about electric power. What is resistance? The resistance of a component is the ratio of the voltage applied and the current that flows through it. So if you take a device, you apply a certain voltage to it, you measure the current that goes through it as a result of it, and you make the ratio between the voltage and the current, what you get is the resistance. So if you want to write it in an equation, this is it, V divided by I is equal to R. That is usually how resistance is indicated. This is called Ohm's law, and the unit of measurement of resistance is Ohm. Let's look at a little example. Let's say we have a circuit like this one represented on the right. We have a battery, so it's a voltage generator. Let's say this battery is a 1.5 volt battery. And then what we connected here to the circuit is a piece of material. So it could be anything. You could connect wood, you could connect metal, or really anything you want. So as a result of the 1.5 volt applied to this material, we're going to have a certain current I going through the material. And again, as described before, if you do the ratio between the voltage 1.5 volt in this case and the current, you get the resistance of the material. The resistance of a material represents how much the material opposes to the passage of electrons. So in this case, we have a battery. So as we said before, the anode of the battery is full of electrons. These electrons really want to go to the cathode of the battery, which is the positive terminal. Now we have a closed loop, a closed circuit here, so it's possible for this electron to go and reach the cathode. So what's going to happen is that the electron is going to start to travel, go through this ideal wire here, reach this material. Now inside of this material, the path of the electron is probably not going to be straight, because the material itself is made of atoms. So as the electron is trying to go through the material, it's going to bounce around. It's going to hit an atom, change direction, do something like this. So bounce a little bit around, but eventually it's going to find its way out, and it's going to reach the cathode. Let's try to understand the difference between power and energy with another hydraulic example. So here we have a little system with a cistern. Cistern is a big tank full of water, and this big tank is at a certain elevation compared with the turbine, and let's call this different in height h, and let's say that is equal to 100 meters. Then we have a valve that can be open and closed, so allowing the water to flow down through the turbine, and the turbine is just a device that can be used to convert the energy of the water into electrical energy, for example to power a house. Now let's do a little bit of a calculation to see, first of all, what is the energy that is stored into the system. As we've seen before, because we have a certain amount of water with a certain mass at a certain elevation, that is equivalent, that means that the water will have a certain potential energy, in this case gravitational potential energy. So here we have a few numbers. Let's just do the math. So we have been told that the volume of the system is 10 cubic meters. So as a consequence, because this is water, we have a weight of 10 tons, so 10,000 kilograms. So now the energy, U, it's equal to mgh, where g is the gravitational acceleration, which is roughly equal to 10. So if you substitute, so the mass is again 10 tons, g is about equal to 10, and h is about 100. So in the end, what you get is about 10 megajoule. So this is the energy that is stored into the system that can be used to produce a certain amount of work. The way you produce the work in this case is by opening the valve, letting the water flow down, and turn the turbine so that the energy can be converted into electric energy. Now, let's say we have a certain flow of water that is equal to 1 cubic meter per second. So when you open the valve, you have 1 cubic meter per second of water coming down. So now, in this way, we can easily calculate what is the power that is transferred from the water to the turbine. So we have 1 cubic meter per second. Now this cubic meter, each of the cubic meter has a weight of 1 ton. And then we can multiply by the acceleration of gravity and the height. So in this case, you see, it's kind of a similar equation. We have the mass, we have the acceleration, and we have the altitude, and all of that divided by second, meaning this is an energy that we are transferring every second. So this is equivalent to, if you do the math, 1 megawatt. So this is the amount of energy that is transferred every second from the system through the turbine. So in this case, because we have 10 megajoule and we are delivering a power of 1 megawatt, that means that after 10 seconds, all the energy will be consumed. What is a resistor now? A resistor is an electronic component that is specifically designed to have a certain resistance. So a resistor usually in schematics have this symbol here. Sometimes when I draw by hand, it will most likely look more like this, just because it's kind of hard to make this shape. But it's a very simple component to use and to understand. As we said before, you put it in a circuit. If you know what is the voltage across the device, you can calculate the current very easily by dividing the voltage by the resistance. And vice versa, obviously. If I tell you what is the amount of current going through the resistor, you can immediately calculate the voltage across the device by multiplying the current by the resistance. Down here, there is an example of a resistor, just in case you ever open an electronic device. This type of resistor are called 2-volt. They are not the latest and most modern components because they're quite big, but they're still used in the industry quite a bit. In order to push electrons through a resistor, you need to spend some energy. So this energy is initially in the form of potential energy, as if you remember, the voltage across the resistor is basically a representation of the potential energy that the electrons have. The potential energy is converted into kinetic energies, and that's how the electrons are pushed through the device. But then, as the electrons go through the resistor and hit the lattice of the material, they will convert the energy into thermal energy that will increase the temperature of your resistor. So if you take a circuit without a battery, and nothing is connected, there's no current, you measure the temperature of your resistor, and then you connect a battery to it, and all of a sudden you have a current going through the resistor. You wait some time, you measure the temperature of the resistor again, you will see that the temperature of the resistor is increased. The first time we talked about current, we made an analogy between current and a water stream. It's an analogy that works really well, as you can think at the current as a stream of electrons. Now we're going to extend that analogy to include also the voltage and the resistance. This analogy should help you understand better these concepts. Let's talk about the hydraulic circuit first, on the left on the slide. At the bottom we see there is a reservoir of water. You can think of this as a big lake or an ocean. Simply is a place that has so much water that no matter what you do with your little circuit, you're not going to be able to influence it at all. Close to the reservoir, there is a low pressure, and this is a characteristic of the reservoir as well. Again, because this is directly in contact with the reservoir, if the reservoir happens to have a low pressure, all the rest of the circuit in direct contact with the reservoir is going to have a very low pressure as well. There's no way you're going to change that. Then we see we have a pump. The pump is able to change the pressure from low to high. That's exactly the goal of the pump, to apply a certain pressure to the water so that the water will actually flow through your circuit. Then your circuit is simply made of a big tube with pretty big cross-section, so the water is really free to go around your circuit. But then you see that at some point here you actually have a choke, a point where the cross-section of the tube becomes much smaller, so it's going to be much more difficult for the water to go through that. You can say that this choke is applying a resistance to the flow of the water. It's pretty easy to understand what is the electric equivalent of this hydraulic circuit. The flow of the water, it's clearly the current, equivalent of the current. The pressure is the equivalent of the voltage. So we have low pressure, low voltage, and high pressure, higher voltage. The pump is the equivalent of a battery, like a device that is able to change the pressure from one point to another. and the choke is the equivalent to the resistance. So we have the equivalent circuit here on the side. We have a battery, again, which is equivalent of the pump, high voltage at the top, low voltage at the bottom, a resistor in between, and we know that through the Ohm's law, we are able to calculate that the current that will flow through the circuit will be equivalent to the difference in voltage divided by the resistance. At the same time, the flow of the water through this hydraulic system is equal to the difference in pressure divided by the resistance. Not all electronic circuits can be explained using the water analogy. For now, this water analogy is very useful to understand in an intuitive way the relationship between voltage, battery, current, and resistance. The Kirchhoff voltage law, abbreviated with KVL, is one of the most important laws that you need to know in order to solve electronic circuit. As indicated on the side here, this is the definition of the Kirchhoff voltage law, and it basically says that the sum of all the voltage in a loop must be equal to 0. What is a loop? A loop is any path traced from one point in the circuit around other points in the circuit and then back to the initial point. So very simple definition. How do you actually implement that practically speaking? So I'm just going to show you very simply with an example on the right. So you see here a simple circuit. It's actually the most complicated circuit we have seen so far. We have three components. We have a battery, we have two resistors, R1, R2. Now we don't know exactly what is the value of the resistor, and that is not really important. We know that the voltage of the battery is equal to 5 volt, and we know that the voltage across one resistor is equal to 3 volts. Now, what is the voltage across the resistor R2? Probably very simple to understand what is the voltage at that point, but some circuits might be more complicated than others. And so it is important to understand what is sort of a formal procedure to follow to make sure your result is always correct. It's pretty simple to implement. So what you do, let me take my green pen, is that you identify the loop. Here we only have one loop, so there's no doubt. You pick a random direction for the voltages. That is already done. And when I see a random direction, I mean apply a random orientation for the arrow of the voltage. Like in this case, we know, okay, the 5 volt is in this direction, so the potential is higher here than here. We know that 3 volt is in this direction. V2, we don't know yet what is the direction of the voltage. It could actually be directed the other way around. It doesn't matter. I decide that the voltage most likely is directed in this direction, so there is a higher potential here than here. So that is totally random. Then you assign the direction of the loop. So you have this loop, you just write a circle here, and you decide, let's use this direction as a convention. Any direction is fine. It can be clockwise or counterclockwise. And now all you're going to do is that you're going to sum all these voltages together, and the one that goes with the same direction of the circle are going to be positive. The one that goes with the direction opposite of the circle, they're going to be negative, and the total sum has to be equal to 0. So in this case, 5, it's going in the same direction of the circle, so I'm just going to write plus 5. Now when I get here, 3 is the opposite of the circle, so minus 3 volts. V2, I don't know what is the value, but I can clearly see that it's going in the opposite direction of this arbitrary orientation, so minus V2. And now we completed the circle, so equals 0. Now this equation can be solved. I will give very easily the solution, which is V2 is equal to 2 volts. Easy, right? The example that we have looked at before, it's a very simple one because clearly there's just one loop in the whole circuit. If you consider a more complicated one, like this one on the right, there could be many more loops here. The Kirchhoff voltage law applies for any loop that you can possibly choose. That will always be true. So in this example, that is one loop. It's already highlighted. But let me take a different color, blue for example. This is another loop. This is also another loop. You can also choose a loop that works like this. Or you can also choose a loop that does something like this. Any loop is a fair game. You can choose any loop you want. And if you apply the Kirchhoff voltage law the way that I just explained, you will always be able to solve the circuit. Another very important law of electronics is the Kirchhoff current law, which is abbreviated often with KCL. Here's the definition of the law. The algebraic sum of all currents entering and exiting a node must be equal to 0. A node is any point on a circuit where two or more circuit elements meet. In this example on the right, we have two nodes, A and B. And most of the time, people use a dot to represent a node. The procedure to calculate all the value of the currents is very simple. You first define an arbitrary direction for the currents that you don't know. In this example, we already been told what is the value of this current and the direction of the current. We already been told the direction and the value of this other current. We don't know the value of the current in this branch of the circuit. So as far as we can tell, the current could be going down or up. We don't know that yet. So what we have to do is to apply an arbitrary direction. It doesn't matter what you pick. If you pick the right direction, you will get a positive number as a result. If you get a negative number, you knew that the direction was the opposite. Now, to calculate the current I, the missing one, you just apply this simple rule. So you take a certain node. You could take A or B. In this example, they are exactly the same. Let's take A. So if you look at A, this current, this 1 amp current, is entering A. So we can write plus 1 amp. The 0.3 amp current is leaving the node. So we can write minus 0.3 amp. And the current I that we're trying to find is entering the node. So it's plus I, all equal to 0. It's very simple to solve this equation. I is equal to minus 0.7 amp. So the fact that the current is negative means that the real direction of the current is actually the opposite, which completely makes sense. If you think about it, you have 1 amp going into this node, and if 0.3 amp are going down, 0.7 amp have to be going in the other direction. The Kirchhoff current law is a representation of the principle of conservation of charge. It simply means that you cannot destroy or create charges out of nothing. So if I tell you that there are 3 charges going into the node in this direction, and I'm also telling you that there are 2 charges going in this other direction, you can be sure that you're going to have 1 charge going in this other direction. Otherwise, if that wasn't the case, that would mean that some charge somehow disappeared, or you create some charge out of nothing, which is impossible. I want to show you that it doesn't matter which node you choose. Ultimately, there is only one solution for the current in the circuit. So let's do the same calculation using node B instead of node A. So now the 1 amp current is obviously coming out of it. So it's minus 1 amp. The 0.3 current is coming inside of it. So 0.3 amp. And the current I that we're trying to find is leaving the node. So it's minus I is equal to 0. So as you can see, we get exactly the same results. I is equal to minus 0.7 amp. And that has to be the case. Otherwise, that means we have committed some mistake in the previous calculation or in this calculation. Real circuits are much more complicated than the one that we are dealing with for now. Usually, they are made of many more components. So it's really important to learn a few tricks that allows you to simplify the circuits, or even just to understand what's going on even when there are a lot of components. The circuit on the left has 4 components. There is a voltage generator, and there are 3 resistors, R1, R2, and R3. These 3 resistors are in series with each other. The same current will go through the 3 resistors, because obviously just looking at the circuit, there's really no other way to go for the current. In the middle of the scheme, we have another circuit where we replace the 3 resistors with an equivalent series resistor. So what we're trying to do here is we're trying to simplify the circuit, and we're trying to find what is the value of R series that for the same voltage V, so the exact same battery is applied to the R series resistor, will give us the same current as the series of R1, R2, R3. So we're really trying to simplify the circuit. If the goal of the resistor was to generate a certain current from the voltage of the battery, or if we replace the resistor with an equivalent resistor, nothing is really changed. In order to calculate the equivalent series resistance, we'll have to use Ohm's law and the Kirchhoff voltage law. The way we're going to do this is very simple. We have V, we have I, and we have R1, R2, R3. So V is an input because it's the battery that we placed here. What we want to do is we want to, from these circuits, from the original circuit on the left, we want to calculate the values of I. Of course, we're not going to be able to calculate the value in terms of amperes, because we don't have the value of the voltage, we don't have the value of resistance, so we will never know the actual value of the current. Our goal is to calculate I as a function of V, R1, R2, R3. In order to do that, the first thing we want to do is to give a name to the voltage across the three resistors. So because the resistors are called R1, R2, R3, we're going to call the voltage V1, V2, V3. The orientation of the arrow of the voltage is random. Of course, I know already what is the result, so I put the smart way to put this the orientation, but even if you place it upside down, you can still get the right results if you follow the Kirchhoff voltage rule. So anyway, just random orientation from the top, and that's it. So now, using Ohm's law, I can write the value of V1 as a function of I and R1, because V1 has to be equal to R1 multiplied by I. And for the same reason, V2 is equal to R2 multiplied by I, and V3 equal to R3 multiplied by I. Very simple. So now, if we use the Kirchhoff voltage law, like this, I can apply the side a certain random orientation. It's very easy to write that V has to be equal to V1 plus V2 plus V3. So now you can see that here we have all the elements, right? We define V as a function of V1, V2, V3, and V1, V2, V3 has been defined as a function of R1 and R2, R3, and I. So now if we replace V1, V2, V3 with the definition of V1, V2, V3 from these three equations, we get the V is equal to R1 multiplied by I, R2 multiplied by I, plus R3 multiplied by I. Now we can collect I, because this is, we have the sum of three terms, and all three terms have I. So if we collect I, we obtain R1 plus R2 plus R3. If we do this, very easy to calculate what is the value of the current as a function of V, R1, R2, R3. So the current I will have to be equal to V divided by R1 plus R2 plus R3. Now, what we're trying to do with this exercise was to find a value for the resistor R series that will give us the same current for the same voltage applied V. It's very easy to see from this very equation that the value that R series has to be to give it the same current I is equal to R1 plus R2 plus R3. So R series will be equal to R1 plus R2 plus R3. To conclude on resistor in series, here we have like a generic statement that you can keep in mind. So let's say you have a certain number of resistors in series. So in this case, I'm assuming, from R1 all the way to Rn. So it doesn't matter what is n, and it could be 100, it could be 1000, it doesn't matter. You can sum as many as you want. The series of a certain number of resistors is equivalent to a single resistor whose value is equal to the sum of the value of all the other resistors. So in this case, all these resistors in series will be equivalent to just one resistor called R series, whose resistance is equal to R1 plus R2 plus R3 plus all the way till Rn. Let's now look at what happens with the resistors in parallel. The circuit on the left, there are two resistors, R1, R2. In this case, they are not in series, but they are in parallel. Components that are in parallel share the same voltage. That is fairly easy to see. Voltage is defined between nodes of a circuit. And here we really only have two nodes. One node is this one, node A, and the other node is this one, node B. You see that between these two nodes, you can only define one voltage between these two nodes. So automatically, the voltage V that is generated by the voltage generator or a battery is going across both R1 and R2. Now, depending on the value of R1 and R2, we can possibly have different currents I1 and I2, or they could also be the same if R1 and R2 are the same value of resistance. What we want to do here is exactly the same as what we did before for the resistor in series, which is we want to find the value of R parallel, the value of a single resistor that has the same effect as the two resistors R1 and R2 in parallel. From a point of view of the voltage generator V, whether there are 2 resistors, 1 resistor, 1,000 resistors, a mix of series and parallel resistor, it doesn't matter. The net effect of having 2 resistors and 1 resistor will be to generate a current I from a voltage V that the voltage generator had created. So from the point of view of the generator V, having 1 or 2 resistors doesn't make a difference as long as the resulting current I is the same. So what we want to do is exactly that, to find what is the value of our R parallel, as I call it here, that actually has the same effect as the parallel of R1 and R2. In order to do that, we will make use of the Ohm's law and also the Kirchhoff law. In particular, we'll adopt a similar strategy as done before. If you take R parallel and you write it in terms of Ohm's law, what you can write is the following. R parallel is equal to V divided by I. So V is kind of like an input because it is defined by a battery. We don't know what is the value, but it's a certain number. I is really the incognita here, right? Because the I, it really depends on the resistor, R1, R2, and so on. So what we're going to do, similar to what we've done before, is that to use the circuit to the left, the first circuit, calculate the value of I relative to V from using the Kirchhoff law and Ohm's law. And then once we've done that, we'll replace the value of I into this equation. Because I will be dependent on V, V will simplify, and in the end, we'll just have a value of R parallel, which uniquely depends on R1 and R2. Let's start looking at these circuits. The first thing we want to do is we want to define I1 and I2 using Ohm's law. So it's very simple to do. You can do it this way. So the Ohm's law for these two currents, it's very simple. I1 is equal to V divided by R1, and I2 is equal to V divided by R2. So it's very simple. Again, we don't have any number here, but these are Ohm's law for resistance R1 and R2. It's basically the definition of how a resistor works. Now the second thing, we want to connect I1 and I2 that we just defined with I. So it's very easy to see what is the result, because it's a very simple circuit, but we can apply the Kirchhoff current law to be a little bit more rigorous. So what we do, we choose a node. Obviously, we can choose any of the nodes. In this case, let's choose this one. Obviously, it has to be a node where I1 and R2 go. A node used by I1 and I2. A definitely works well for us. And now we're just going to write that it's actually very straightforward. I minus I2 minus I1 minus I2 equal to 0. So I'm summing all the currents entering the node and subtracting the one leaving the node, everything equal to 0. And this simply tells me that I is equal to I1 plus I2, which is kind of obvious if you look at this and you think at the water equivalent. The water I, or the current I, is coming into the node. There are two currents coming out of it, so the sum of these two currents has to be the same unless some electron got lost in the way. So now that the final part, it's very similar to what we've done before. The equation I is a function of I1 and I2, but I1 and I2 are defined by the Ohm's law, so we just write the same thing. But just substituting the expression for I1 and I2. V divided by R1 plus V divided by R2. So we have taken these two equations and this equation and combined into one. And now we're very close to the end. As we discussed before, R parallel is defined as V divided by I. Let me just call it RP. V divided by I from the second circuit here. From here you can tell it's V divided by I. So the V is the same as the one in the previous circuit, and it is an input. So there's really no other way to break it down in smaller pieces. But I, it's a function of R1 and R2, which in turn is a function of R1 and R2. So now we'll just replace I with the new definition of I that we found. V divided by R1 plus V divided by R2. Obviously, you can see that we have V at both numerator and denominator, so that can be simplified. So the final equation that we obtain is the following. where this part at the end, this is the value of the equivalent parallel resistor. In this slide, I summarize the final result, the final equation needed to calculate the parallel of resistor. Again, on the left, we have an hypothetical circuit with n resistor in parallel. The number of the resistor can be any, it could be 100 resistor, 10 resistor, 3 resistor, doesn't matter. And on the other side, we have the equivalent parallel resistor, and this one is the equation that you need to use to calculate it. So as we've seen before, the way you do it is you take the inverse of each of the resistance, you sum all the inverses, and then you do the inverse of the whole thing. So this one is a little bit more complicated than this resistor in series, but I mean, not too much, it is manageable. Also, many times you won't really have many resistors in parallel. Many times it will just be 2 resistors most of the time. So there is a simplified version of this equation, like if you just have 2 resistors in this, so you only have R1 and R2, and you kind of play a little bit with the math. There is like an easier version, at least easier to remember. So R parallel, in that case, become R1 multiplied by R2 divided by R1 plus R2. So this one is a little bit easier to remember, at least for me, and honestly is the one that you use most of the time. I want to stress a concept that is really important before we move on. What does it mean equivalent here when we say equivalent parallel resistance? Because obviously if we take this circuit and change it into this one, the circuits are not equivalent anymore. We even have a different number of components. How could they be equivalent? What the equivalent word means is that this network of components behave exactly the same way as this individual component from the point of view of the external circuit. So this, it's a little bit of a mouthful, but let me just explain with a very simple circuit. So if we have a battery generator connected, our usual battery generator, you could see this network of resistances as one big component. Now, the battery source, the voltage generator, doesn't know what it is connected to. The only thing it knows is that it applies the voltage across these components. So you have 0 volt here and V volts here. And as a result of that, there is a certain current I that is requested out of the voltage generator. From a point of view of the voltage generator, whether this component is made of n resistor or it's made of just one resistor, there's no difference as long as the required current is the same. There's no way this voltage source has a way to understand that there's only one resistor instead of 10. So this is what the equivalent word means. It's equivalent from the point of view of the rest of the circuit. Now, if you consider the overall circuit, obviously these two circuits are not equivalent anymore. Here we have n plus 1 components, including the battery source, the voltage generator, and in the other case we will only have 2 components, the voltage source and the parallel resistor. So this is a really important concept. The equivalent parallel and serial resistance is a very useful concept. Most of the time it's just used to simplify the mathematical calculation, because if you knew what is the equivalent value of this parallel resistor, it will be much easier for you to calculate the current given a voltage. Whereas if you don't know what is the equivalent parallel resistance, every time I change the voltage, to know what is the current I, you will have to calculate the current in each of the resistors, then sum it up all together, and then you can tell me what is the value of I. So that is one of the usage of the equivalent parallel and serial resistor. Other times, you might actually calculate the value so that you can replace many components with a fewer number of components, but it's very important to stress that that is not a must. Doesn't make necessarily a circuit better than another. Each case is different. In this lesson, we're going to talk about voltage dividers. Voltage divider, in the simplest form, is simply made of 2 resistors in series. And the goal of a voltage divider is to take a larger voltage, which could be battery voltage in this case, or any other voltage, and divide the large voltage into different smaller voltages, like in this case, V2 and V1. And all the output voltages obviously are a fraction of the input voltage accordingly to the Kirchhoff voltage law. The value of V1 and V2, it's easy to calculate. From the Kirchhoff voltage law, we know that the sum of V1 and V2 has to be equal to V bar. So V bar is equal to V1 plus V2. And in order to calculate the value of V1 and V2, we can simply do the following. So we remember that the equivalent series resistance of R1 and R2 is equal to the sum of R1 and R2. So RS, we can call it, is R1 plus R2. Then we calculate the current that is going through the series of these two resistors, just like this. And the value of the current will be equal to the V bar divided by R1 plus R2, which is the series resistance. And then finally, we have the current going through the two resistors, so we should be able to calculate the two final voltages. So the two final results, V1 will be equal to VB, instead of V bar, just for short, R1 plus R2, and V2 is equal to VB, R2, R1 plus R2. The same idea can be extended for a larger number of resistors. So if you have your supply here, but instead of having only two resistors, you have 4 of them. Now, as a result, you're gonna have 4 voltages that you can pick. This resistor will be R1, R2, R3, R4. This one I call it V in this time. And now you're gonna have V1, V2, V3, and V4. The sum of these voltages is going to be equal to V in again for the Kirchhoff voltage law. And you can use a generic equation to calculate the voltage across each one of the resistors. So the voltage, so the Vx, so the voltage across any generic resistor X, will be equal to Rx, so the value of the resistor, divided by the sum, so R1 plus R2 plus Rn, so all the resistors that you have in the voltage divider, obviously multiplied by the input voltage. So this equation gives you an idea of how things go, and the fact that the voltage across one resistor compared to the other is proportional to how big is the resistance of the resistor compared to the other resistor in the voltage divider. For example, if you have a voltage divider made just with 2 resistors and the resistors are the same, the voltage will be equally split between the 2 resistors. If you have 3 resistors that are all the same, you will have 1/3 of the voltage on each of the resistors, and so on. Instead, if you have, for example, a resistor that is 10 times as big as the other, and you have only 2 resistors, you will have that 1/11 of the voltage will go on the smaller resistor, and 10/11 of the voltage will go with the larger resistor. Voltage dividers can be made using a different number of resistors. You start with a minimum value, which is 2, but then you can have 4, 3, 5, 10, as many as you want in principle. The idea is that by increasing the number of resistors, you get a higher number of output voltages. Now, I want to make a few comments on this. First of all, remember that the total sum of all the voltages on the resistors is going to be equal to the input voltage. So if you increase the number of resistors too much, you're just going to get very, very tiny voltages. Also, these voltages are going to be not very accurate. The resistors themselves are not very accurate. When we say the resistor is 1 kilo ohm, usually when you actually buy a component, it will come with a certain tolerance, for example, plus minus 5%. It also changes with temperature a little bit. If you try to just divide the voltage roughly by 2, that is fine. You can use a voltage divider. But if you're trying to get very precise values of voltages, and many of them, then you're going to get quite surprising results. If you look at this equation here that we calculated for Vx, but in general, if you think about the relationship for these two, for V2 is equal to V bar R2 divided R1 plus R2. So you will notice something very interesting. So the voltage divider is pretty much agnostic on the absolute value of the resistance. All the voltage divider care is about the relative value of the resistance. In this case, if R1 is equal to R2, you're always going to have the V2 is equal to half V bar. Now that means that R1 and R2 could be equal to 1 ohm, They could be 1 kilo ohm, 1 mega ohm, or 10 mega ohm, or whatever you want. You still get the same result. The reality, the practice of engineering here tells you that you can't really choose any value of resistance that you want, because while that will mathematically work, it will have some serious limitation of your real circuit. You can choose value of resistor that are either too small or too big. If you choose a value of the resistor that's too small, you're gonna have a big bias current going through your voltage divider, and that is generally undesirable for several reasons. First of all, if this voltage generator is really a battery, you're gonna be draining the battery very quickly for no reason. Secondly, having a pretty big current most likely is gonna mean that you have a big power dissipated on the resistors. Remember that the power dissipated is square of the current multiplied by the resistor, and that means that your resistor will have to be pretty fat, because otherwise it will heat up quite a bit and it could even burn. On the other hand, you also don't want to choose a value of resistance that's too high. First of all, very high value of resistance is difficult to find, and in addition to that, if you choose a value of resistance that's too high, the problem with that is that you're going to have a very tiny bias current going through your voltage divider, because remember that the I bias is roughly equal to V bar divided by R1 plus R2 in this example. So if R1 and R2 are too big, the I bias would be very small. And if the I bias is really small, first of all, you're very likely not respecting condition number 2, which means that you really have to have zero current from the central tap for this voltage divider to work. And secondly, even if you really have zero voltage, the problem is you're always going to have some noise injected in your circuit by other appliances, other electronic tools nearby. For example, if you have a phone or things like that. So they will inject voltage and current in your circuit. And you want a voltage divider to be somewhat solid and robust. And in order to do so, you want decently sized current to go through it, so that even if there is some external factor, inject a little perturbation, overall your results stay the same. So you want this current to be somewhat significant. So usually the rule of the thumb is to use value resistors in the range of kilo ohm. For example, 10 kilo ohm, 5 kilo ohm, up to, I don't know, 100 kilo ohm max kind of value. But then again, every circuit is a different story. If you really need to use this voltage divider, but your I load is insignificant, then you should use a smaller value of resistor. Voltage divider is still not really a good way to get a precise reference voltage. Though this might be stated here, I'm also saying that there are serious limitations. So as I highlighted before, resistors have tolerance, so they change their value within a certain random range that you never know, and the value of the resistance also change with the temperature, so you can't fully rely on them. Secondly, it's very quick to see that if you really want to have any significant load current here, in order to have a stable voltage, you will really have to use very low resistor values, and that is really undesirable because you will end up consuming a lot of current. The voltage divider is good to generate reference voltage only when the current from the load is really tiny, and when you really don't need to have a precise voltage to begin with, but you just roughly have to have, let's say, half of the input voltage, something like that. Another important assumption that we made that I have not discussed yet on the voltage divider is that the input voltage is constant. That might be the case depending on your circuit, but most of the time that is not the case. In particular, if you connect as an input voltage a battery like I'm assuming here. The voltage battery is changing quite a bit during the operation. The voltage at 100% charge is much different than the voltage at 50% charge for a battery. And so you'll have to be very careful when you design a voltage divider to keep into account that the input voltage might be changing as well. So if your goal of the voltage divider was to generate a voltage that is half the battery voltage, then it doesn't matter that the battery is changing. If you have R1 equal to R2, for example, you're always going to have the output being equal to half the input voltage. But if your goal was to generate an exact value of the voltage, then you're going to be in trouble, because as your input voltage is changing over time, so is your output voltages. If you need something precise, stable, something, for example, used to actually supply the voltage to a chip, then you will very likely use something else, probably a voltage regulator. The current divider is the equivalent of the voltage divider but for current. With the voltage divider, we had a large voltage and we divided it using resistors. Here we have a large current, and we divide it in different branches using resistors as well. The simplest form of the current divider is shown on the left. And it's made by two resistors in parallel. The voltage divider is in parallel to a voltage source, a battery in this case, and we have called the overall current from the battery I bat. The Kirchhoff current law tells us that I bat will have to split between the two branches of the two resistors. We can call I1 the current in the resistor R1 and I2 the current in the resistor R2. The goal of this lesson is to determine the value of I1 and I2 relative to I bat. In other words, we want to determine how the current I bat divides between the two nets of the circuit. R1 and R2 are in parallel, and we know the value of the voltage across them, V bat. Therefore, it's natural to start by calculating the value of the current I1 and I2. The current I1 is simply equal to V bat divided by R1 and I2 is equal to V bat divided by R2. I bat is also easy to calculate, as it is the current going into the parallel between R1 and R2. I use this symbol to indicate the parallel between R1 and R2. The parallel between R1 and R2 is equal to R1 by R2 divided by R1 plus R2. Now, if we combine these two equations into one, we obtain that I bat is equal to V bat multiplied by R1 plus R2 divided R1 multiplied by R2. Finally, we can calculate the ratio between I1 and I bat and I2 and I bat, which give us the percentage of the current I bat going into R1 and the percentage going into R2. Needless to say that a similar approach can be used to find the value of the current in voltage dividers with more than two branches. These equations that we have just calculated are similar to the one of the voltage divider, but there is a fundamental difference. If we had a voltage divider composed by two resistors, R1 and R2, and we wanted to calculate the percentage of V bat falling on R1, the results would have been R1 over R1 plus R2. In the case of the current divider, instead, the portion of I bat going into R1 is R2 divided by R1 plus R2. You see the difference? In the case of the voltage, we put in the numerator the resistor whose voltage drop we are calculating, while in the case of the current, we put the other resistor. You see here we are calculating I1 over I bat, and the result is R2 divided by the sum of the resistor. And at the same time, when we want to calculate the current in I2, we have R1 divided by the sum of the resistor. This is the opposite of what you get if you are calculating the voltage over this resistor in a voltage divider. This might seem strange, but it's very intuitive. In the voltage divider, for the same current, a high resistor takes a larger portion of the input voltage, while in the case of the current divider, For the same voltage, the higher the other resistor, the higher is the portion of the current that will prefer to flow in the resistor under study. Current dividers work well when their different branches are truly in parallel with each other. If you were to connect anything in series to any of the resistors, like this little box in series to R2, the equations of the current divider that we have just calculated won't be mathematically correct anymore. But it will still be okay as long as the voltage drop across this new element is much smaller than V bar. I want to spend a few more words on the concept of the path of least resistance. As we've seen before, the current tends to use the path where the resistance is the least. We can see an example of this in the two equations that we have just calculated. These ones. Assume for a minute that R1 is 2 times as big as R2. So R1 equal 2 times R2. If we replace R1 in both these equations, we get that I1 is equal to I bat divided by 3, and I2 is equal to I bat divided by 3 multiplied by 2. As you can see, 2/3 of the current went into the smaller resistor R2, and only 1/3 went into R1. In other words, because R1 is twice as big as R2, the current in R2 is 2 times the current in R1. We can use an hydraulic example to qualitatively explain these results. An equivalent hydraulic circuit for this current divider could be a tube carrying some water that splits into two subtubes T1 and T2. The subtubes are not of the same size. On the contrary, because T2 is representing a resistor that is half the size as the other, the subtube will be twice as large. It is not hard to see how, in the scenario that I've just described, most of the water will prefer to flow into T2, just as 2/3 of the current prefers to flow into R2 rather than R1 in the electrical circuit. Finally, let's look at the corner case. Imagine that R2 is equal to 0. That is, the resistor is replaced with a short circuit. Or in the case of the hydraulic circuit, the second tube is replaced by an infinitely large tube. In this case, the equation tells us that no current will flow into R1, and that all the current will go into R2. A short circuit will therefore deprive the circuit of all of its current and cause a large amount of current to concentrate into a tiny wire. I1 will be 0, and I2 will be equal to I bat. Note that not only I2 will be equal to I bat, but if you consider the specific circuit, the value of I bat will also become infinite, because now you are applying a voltage of a certain value, V bat, across a resistor equal to 0. So if you use Ohm's law, you can calculate that the current will become infinite. In real circuits, the current cannot really become infinite, but it will definitely become really large. That is why short circuits are so dangerous. They generate large current in small areas, and they often not only prevent the circuit from working as intended, but they can also start a fire and destroy the circuit. In this lesson, we will talk about a very important principle of electronics, the superposition principle. This principle will help us to solve more complicated circuits. As indicated here, the principle says that for a linear circuit, the net response caused by two or more generators is equivalent to the sum of the responses that would have been caused by the individual generators. Let's first define what is a linear circuit. A linear circuit is a circuit composed by linear components, such as resistors, capacitors, and inductors, plus voltage and current sources. For instance, the circuit on the left is a linear circuit because it is entirely made of resistors, voltage sources, and current sources. Let's imagine that we want to calculate the value of the voltage V3 on the resistor R3. This seems quite a complicated endeavor, as more than one generator is acting on the circuit and will somewhat influence the outcome. How can we solve this problem? Here is where the superposition principle comes to save the day. The superposition principle tells us that, as long as the circuit is linear, one does not need to tackle the whole thing at once, but the final result can be computed as the sum of the effects of the individual generators. On the right of the slide, I indicated a procedure one must follow to solve the circuit. Step 1. Turn off all generators but one, and compute its effect on the desired node. Let's start by calculating the effect of VA. That means that we have to turn off IB and VC. How do we do that? Well, IB is a current source, so its job is to produce a current. Turning it off means setting the current to zero. A net, where the current is zero, is indistinguishable from an open circuit, so turning off a current generator is equivalent to removing it from the circuit and leaving the net open. VC is a voltage source. Its job is to generate a voltage. Turning it off means setting the voltage to zero. A component that, no matter the current, always has a voltage drop of 0 volt is indistinguishable from a wire. So turning off a voltage generator is equivalent to replacing it with a wire. So we are shorting VC out. Now that we have turned off IB and VC, we are left with a circuit with only one generator and a few resistors. This circuit is simple to solve. We recognize that R2 and R3 are in parallel, and that their parallel will generate a voltage divider with R1. So the contribution of VA to V3, a quantity that we can call V3A, will be equal to VA multiplied by R2 parallel R3 divided by R1 plus R2 parallel R3. Now that the calculation of the contribute of one of the generators is complete, we can move on to the next one till we have considered all the generators in the circuit. At the end of the procedure, the final results for V3 will be given by the sum of each of the contributes. So V3 will be equal to V3A plus V3B plus V3C. Let's see an example. We consider the same circuit as before, but now we have assigned value to the components. The resistor resistance is 1 ohm, VA is plus 3 volts, IB is 3 amps in this direction, and VC is minus 1.5 volt. The incognita is still V3, the voltage across R3. On the right of the slide, I represented how the circuit is transformed when one turns off all generators but one. In case A, the only generator left is what was called VA. In case B, we keep only IB on. And finally, in case C, we consider the effect of VC. We have already discussed the effect of VA on V3. It is to calculate that with the numbers in this example, the contribute is equal to plus 1 volt. To calculate the effect of IB, we turn off both VA and VC by replacing them with short circuits. The 3 1-ohm resistor will now be in parallel with the 3 amp generator. We don't need to resort to any calculation here. The 3 amp current has 3 identical branches where it can go into, so it will evenly split between them. A 1 amp current into a 1 ohm resistor generates a voltage equal to 1 volt. The contribute of IB to the voltage V3 is also plus 1 volt. Lastly, we can compute the effect of VC. This case is similar to the first one. Once VA and IB are turned into a short and an open circuit, respectively, we are left with a single voltage divider. It is easy to calculate the contribute of VC to V3 is minus 0.5. Finally, the value of V3 when all generators are kept on is given by V3 equal to V3A plus V3B plus V3C, which in this case is equal to 1.5 volt. Simple, isn't it? If we had tried to solve the circuit keeping all 3 generators on, we would have had to write more complicated equations. Instead, thanks to the superposition principle, we can follow an easy procedure and determine the contributes from each of the generators, and from that, determine the final result. In this lesson, we will talk about ports in an electrical circuit. Any electrical circuit has at least one port. A port is a combination of 2 terminals of the circuit. In this example, I represented a simple voltage divider powered by a voltage source, like a battery, for example. The divider's output is then connected to RL, which is the load of the circuit. This can be seen as just one big circuit, but it can also be thought as made of different blocks that talk to each other, and blocks talk to each other via ports. In this example, I added some white circle to individuate ports and to divide the schematic in 3 different blocks. Here are the circles that I used to indicate terminals. The first block contains the battery. A battery does not have any input. It is the source of energy for the circuit, so it only has one port. We could call it output port. This is the port. The second block is the voltage divider. This block has an input port where the voltage of the battery is applied, and an output port, which is indicated by 2 terminals across R2. Finally, the last block is the load, which really only contains the resistor RL. This block also has only a single port. I want to highlight a few more things. A port is always defined by 2 terminals. The reason for this is that you need 2 points to define a voltage, and currents always need to have a return path. If you look at this port, for example, the one of the battery, the Kirchhoff current law tells us that the current injected by the battery into the voltage divider must return from the other terminal. So if we call this one IB, we must have an IB coming back on the other terminal. Hence, a block without a second terminal will make no physical sense. Sometimes you will see blocks represented with one terminal only, but that is simply due to graphical simplification that assumes that the second terminal is either hidden or it is ground. Ports are also not fixed for a given circuit. You can literally define a port between any 2 nodes of the circuit if you like. In this example, one additional port could be the one whose terminals are around the resistor R1. So we could define this. This could be another port. However, in this case, the voltage on R1 does not seem to be used by the circuit. The load, in fact, is connected on R2. So defining this port will be at least curious, but there's nothing wrong with it. Splitting circuits in block and defining ports is an arbitrary process. One could have chosen to consider the battery and the voltage divider as one big block, having only one output port. Like this. Just one block with an output port. One could even consider the whole circuit as a block with one output. The opposite extreme of this example would be if each of the components become its own block. But that is a rather pointless case, as you might as well look at the schematic at that point. The goal of dividing a circuit in blocks is to make it simpler to study. But where the line between one block and another is drawn is arbitrary and changes from person to person. For example, on the same project, the circuit designer will need to look at the detail of the schematic, while a system architect, who is looking at the design from a higher point of view, would prefer to study a block diagram to hide the details and focus on the bigger picture. In this lesson, we will talk about the Thevenin equivalent circuit. Let's consider a fairly complicated circuit composed of voltage sources, current sources, and resistors, like the one I represented on the left of this slide, this one. Then take a part of the circuit, that is, a pair of terminals connecting to it, like these two, and attach a load. In this case, I represented the load as a resistor-looking device in gray, but it could really be anything. This is the load. The circuit will have a certain effect on the load, namely, it will generate a certain voltage and current in the load. The Thevenin equivalent is a circuit composed by the series of a voltage source and a resistor. I represented it here. The theory says that one can find the value of the V equivalent and R equivalent such as this circuit is undistinguishable from the original circuit as seen from the load. That means that no matter what is the load that you consider, both circuits will always generate the same voltage and current in it. The two circuits are completely different internally, but from the point of view of what you can see, looking from that port, the two circuits look identical. If a circuit has more than one port, it will have, in general, different Thevenin equivalents for each of its ports. Thevenin equivalents are useful because they provide a level of abstraction and allow to ease the study and design of more complicated circuits. For instance, say that you want to connect not just a load, but another circuit to this port of this network, and you're wondering how the two circuits will work together. Wouldn't it be easier by replacing the first circuit with the Thevenin equivalent? Do you really need to know how all the voltages and currents inside the circuit move in order to determine how the circuit will interact from that port? The answer to this question is often no. Let me give you another perhaps silly example from daily life. To use a computer, do you need to know all the intricacies of the internal design? Do you need to know the model of the CPU, how much RAM it has, and how many resistors are used in its circuits? The answer is no. The operating system and your input devices like the keyboard and the mouse provide a level of abstraction and allow you to effectively move electrons around inside of your computer and all over the world via the internet without having to know how all of that works. Without this level of abstraction between internal circuit and the user, nearly no one will be able to use a PC. Alright, now the question is, how do you find the Thevenin equivalent of a circuit? Well, there is a procedure that you have to follow that is indicated here. Step 1, disconnect the load. The Thevenin equivalent is meant to represent the circuit, the rest of the circuit, so the load cannot be part of it. So in this case, we will just eliminate this. Step number 2, use the superposition principle to find what is the open circuit voltage VOC at the port under consideration. That will be the value of the generator V equivalent. So in this case, we have eliminated the load. Let me delete it. And now we will use the superposition principle to find the value of the voltage here. And this voltage is called VOC, V open circuit, and that will be equivalent to the V equivalent of the Thevenin equivalent circuit. Step 3, turn off all the generators in the circuit and simplify the network of the resistors till you're left with one resistor at the output port. That will be the value of the resistance in the Thevenin equivalent circuit. So in this case, we will turn off all the generator, which means the current source becomes open, the voltage sources become shorts, and then all we are left is a network of resistor. And we can do series and parallel until we simplify it all, and we are just left with one resistor between the two terminals of the port that we are considering. The value of that resistance will be equivalent to the R equivalent of the Thevenin equivalent circuit. Not too difficult, isn't it? Well, you could argue that this was quite some work, and that one might better spend it just to solve the circuit and to find the voltage across the load. Well, if your goal is simply to find the voltage on the load once, and you're sure that the load will never change, then you're right. Determining the Thevenin equivalent of the circuit adds some overhead to an already complicated calculation. The Thevenin equivalent comes in handy, however, when the circuit can be used to drive different loads, because once the Thevenin equivalent model is known, determining the voltage and the current on a new load is much easier than do the calculation all over again. Not only that, but the Thevenin equivalent circuit also allows you to compare how different circuits looks from one of their port, something that is quite hard to do if the two circuits are complicated and significantly different. Let's look at an example. On the left, we have a fairly complex circuit with 2 generators and 3 resistors, and we want to find its Thevenin equivalent. Let's go step by step. Step 1, remove the load. Done. Step 2, find the value of V equivalent using the superposition principle. As you can see here, I've already done the work. On the left, I show the equivalent circuit when the current source is turned off. The circuit is a simple voltage divider that generates an output voltage of plus 2 volts. On the right, I did the opposite and turned off the voltage source instead. The resulting current divider generates a voltage drop equal to minus 1 volt. The value of the open circuit voltage VOC is therefore 1 volt. This is also the value of the equivalent Thevenin voltage. Step 3. All generators are off, and we need to simplify the network till a single resistor is left between the terminals of the output port that we are considering. We have 3 1 ohm resistors here, in parallel with each other. Hence, the Thevenin equivalent resistance will be 1/3 of 1 ohm, or about 333 milliohm. Now, we can replace V equivalent and R equivalent with the respective values. This is the Thevenin equivalent of the circuit on the left, and it can be used to study the effect of this complicated network to any load or circuit that we might decide to connect to its output port. In this lesson, we're going to talk about type of resistors. The first thing we want to talk about is the termination type. So we have 2 big categories of resistor here: through all components, which sometimes is abbreviated with TH or PTH, where P means plated. And the other category is surface mount components, which is usually abbreviated as SMD, surface mount device, or SMT, surface mount technology. Here we have an image of a through-hole resistor. As you can see, he has this little shape, kind of like a sausage shape, and he has many little colored rings on it. So these rings are used to determine the value of the resistor and also to communicate the tolerance. Now, another important thing is just to kind of explain the name of this category of resistor. You can notice that they have this through-hole resistor, they have these leads that are very easy to bend. So the way you assemble this on a circuit is the following. So let's say this is your board, your electronic board. You're looking from the side of the board. So, you know, the board kind of continues like this. But let's assume we look from the side. Now you take your resistor, and so this is kind of your resistor. And then what you do is that you take the leads, you bend them, and you make them go through the board. That's why they're called through hole, because they have these leads that goes through the through holes in the board. Then what you do is that you take your soldering iron and you solder the other side. Obviously the leads normally are much longer than this, so they continue going, but after you solder them, you just trim them, because you don't want to have leads hanging on the other side of the board, which are not doing anything anyway. So that's how you assemble it, and that's how we justify the name of this category of components. Another thing I want to highlight is the 1/6 of a watt indicated here. This is the so-called power rating of the component. And what these numbers is telling you is that you want to make sure that your circuit, the way it is designed, is such as the maximum power that is going to be dissipated on the resistor is always going to be lower than this number, so that everything will work fine. Because if the power becomes higher than this value, then the component will overheat and eventually it will break. In this lesson, we're going to learn how to read the value of a resistor using its colored band. So we're talking about through-hole resistors here, and we're going to use this table to determine the value of the resistance and the tolerance. A resistor can have 4 bands or 5 bands code. Let's start with the 4 bands, that is the simplest. So in case of the 4 band, you can notice right away that the bands are split into groups. We have first 3 bands in a group all the way to the left, and then we have another band that is isolated. So the first 3 bands are used to determine the value of the resistance, and the last one will be used to determine the tolerance. So if we start with the first group, the first bands, so all the bands but the last pretty much, they need to be taken at face value. What do I mean here is that you look at this table and you see that green always means 5 and blue always means 6. So because of the 2 first bands, so this will be part of the actual value of the resistance. So we do 5 and 6. The last band of the group, you might be inclined to say, well, the last one is yellow, so the value is 4. So is it the 564 ohm? No, the last one of the group always needs to be used as a multiplier. So in this case, the multiplier is 10 kilo. So the 4 is actually applied to 10 as a power. So what you're basically doing is multiplying by 10 to the power of 4. And what you get out of this is 560 kilo. So that's the value of the resistance. Now the last band, the isolated one, it's gold. That's the most common value that you will, color that you will find for the tolerance. And that means that the tolerance of the resistance is plus minus 5%. So that means that as you buy these components and you put it on the board, the nominal value is 560 kilo, but really the value of the resistance could be anywhere within 560 kilo plus minus 5%. Now, if you look at the 5-band code, this one is exactly the same concept. Even here, you can distinguish the bands between 2 groups. There are 4 bands in a group together and 1 that is isolated. And just as before, for the first group, the first bands has to be taken at face value. So we have red, orange, and violet. So red is 2, orange is 3, and violet is 7. So it's a 2, 3, 7. And then the last band of the first group is the multiplier. So in this case, it's black, so the multiplier is 1 ohm. So in this case, the value of the resistance is actually 237 ohm. And then the last band, which is the one that is isolated, is again the tolerance, which, as you can see here, brown is equivalent to plus minus 1%. So the final value of the resistance is 237 ohm plus minus 1%. The second category of termination type for resistor is the surface mount type, SMD, surface mount components. We have an example here. This is by far the most common type of termination for resistors in modern electronics. It's not difficult to understand why. So this component is really, really tiny. For example, this one, 1206, is the indication of the package. So a 1206 component is a component that is, like if we draw it like this, the 1206 is 3 by 2 by 1.6 millimeter. So just like this, 3 by 2, 1.6, and these are millimeters. And this is one of the biggest dimensions for SMD components. You can go all the way to the package that is 0.1005. And in this case, the dimensions are 0.2 by 0.4 millimeters. So really, really, really tiny. These components are not assembled the same way you assemble the through-hole, obviously, but as the name implies, they are mounted on the surface of the board. So let's say if this is the side of the board, what you do this time is that you drop your component here, like this, and then you're just going to solder here and there. So it's completely sitting on the top, it doesn't require holes in the board, and it's mounted on the surface. So that explains the name. We see that this component is a 100 ohm resistance value. So the way you determine that for SMD, there are two ways. So if the component is big enough to actually have digits on the surface, the number is represented in this way. Like in this way, we have 101, which indicates 100 ohm, because usually the first digits are a representation of, actual digit of the value of the resistance. So 1 and 0. And then the last digit is usually a multiplier. So it means, in this case, it means that you have to take 10 and you multiply by 10 to the power of 1, where 1 is the last digit. So in this case, 10 by 10 is equal to 100 ohm. So for example, if this was 102, that will indicate 1 kilo, because it would be 10 multiplied by 10 to the power of 2, which is 100. So you get 1 kilo. The reason the number is represented this way is pretty obvious. You will never have enough digits available on the body of the component to be able to represent, the biggest number of resistance. When the package becomes too small, like in the case of 01005 or 0204 or this kind of size of 0201 size of package, then in that case, you don't even try to write the value of the resistance on it. So in that case, the components look all the same and you just really have to know it. So you have to take it correctly, or you can always take a multimeter and measure it. Now the two resistors that I introduced before, this one and this one, they differ because of the termination type, but they were, in both cases, these were fixed resistor. So that means that the value of the resistance shouldn't change, at least at the first order. Now, this is not a perfectly accurate explanation because the resistance does change a little bit based on several factors like the temperature, but the change should be pretty small, and it's an unwanted change. It's just something you have to deal with. But at first order, kind of the big picture is that the value of this resistor shouldn't change very much. There are other types of resistors, of components that are built to be variable resistors, and these are called potentiometer. So you see two examples of potentiometer here, and as you can notice, there is a handy knob that can be used by a user to turn and do something to this component. We're going to figure out exactly how this works. But these are the type of components that you will find in circuits wherever there is a need for a user to operate a certain knob to do something to the circuit. For example, if you have a stereo, you're going to have a knob that you can turn to change the volume of the music, for example. And in that case, most likely a potentiometer was implemented to allow the user to apply this rotation movement and change some parameter. Let's try to understand how this potentiometer works. I'll start with an example. Let's say you're building a resistor, and you want to build this resistor this way. So you have the wire coming in, and then, as we know, a resistor is a component that opposes to the passage of current. So you find some material that has this property, it opposes particularly well to the passage of current. And then you define you take a piece of this material, and based on the geometry of these pieces of material, you get a certain value of resistance. For example, let's say 4 kilo. The question is, what happens if I take another pieces of wire and connect it in the middle and I make it available from the outside? Well, what happens is very simple. So if I want to draw the symbol of this, we went from one single resistor with 4 kilo. Now we have 2 resistor equal to 2 kilo, and we have a terminal in the middle. So in a way, we built sort of a voltage divider here. Now, what happens if I move this central terminal that is actually not fixed, but it can be moved, and I move it to 3/4 of the way from the bottom. So now it's pretty simple to understand what's going on. The resistance for the current from the entry point till the output of the central terminal is much smaller than the resistance from the central terminal to the lower terminal. So now we're going to have 1 kilo here and 3 kilo at the bottom. So you see two fundamental things here. No matter where you place this central terminal, the total sum of the two resistance has always to be 4 kilo, because that is completely determined by the material I pick and the dimension, the geometrical dimension of the material. And the other thing is that depending on where I position the central terminal, I will break down this value of resistance differently between the upper and lower resistance. If we go back looking at this potentiometer picture that we have here, it should be easy to understand why they have 3 terminals instead of 2. As we just said, we have the first 2 terminals, terminal 1 and terminal 3, for example. So the one top and bottom are just connected. Between them, there is a constant resistance. And then there is another terminal, which is the terminal number 2, the one in the middle, that is actually a special terminal that taps the resistor, the internal resistor, in different positions, so it can move up and down depending on the position of the knob. So again, the resistance between 1 and 3 is always constant, but the resistance between 2 and 1 or 2 and 3 completely depends on the position of the knob. One of the reasons to use a potentiometer is, for example, to get a variable voltage divider. So a voltage divider works the following way. Let's say if we take this one, which is a voltage divider, we have V in here, the input voltage, and then we have R1 and R2, and this is V out. So V out is equal to V in multiplied by R2 divided by R tot, where R tot total is the sum of R1 and R2. Now, in case of a potentiometer, R tot is constant and depends on the value of the potentiometer that you buy, but R2 totally depends on the position of the knob. So pretty much from a constant input voltage, you can get a varying output voltage that goes from 0 all the way up to V in, depending on where you position your knob. The schematic symbol of a potentiometer has to be something different than this, because otherwise it would be indistinguishable between the voltage divider. And this also does not represent it well, because it does not contain any information on the fact that R2 and R1 are variable depending on the knob position. So the potentiometers, they have a dedicated symbol, which is the following. So you have the symbol of a resistor plus an arrow to the middle of it. So that's pretty simple to understand. The top and the bottom here are terminal 1 and 3, and the one in the middle is terminal 2. So you know that the resistance is constant between 1 and 3, but it can change between 2 and 1 and 2 and 3. Let's talk about electric power. Electric power is a very fundamental quantity and often is confused with energy. So let's try to make a little bit of clarity. Here we have the definition. As you can read here, the electric power is the rate at which the energy is converted from electrical energy of electrons to other form of energy. So let's remember the energy is the capacity to do some work. So when you have a certain amount of energy in a battery, that means that if you connect a battery to a circuit, you can actually accomplish some work, whose value would be equivalent to the energy stored in the battery. And the power is measuring the rate at which the work is done. The power is telling you how quickly you're consuming the energy that is stored into your battery. Let's now try to calculate the relationship between power and voltage and current. Right now, this is the first time we have seen power, the concept of power. And we are familiar with voltage and current, and we wonder if there is a relationship between them. So let's try by defining again the current and the voltage. So the current can be written as the number of electrons multiplied by the charge of the electron divided by the time. So again, you can imagine sitting by a wire, looking at a section of a wire. There will be a net amount of charge moving in a certain direction, so a net amount of electrons moving in one direction. you multiply the number of electrons by the charge of one electron, so you get a certain amount of charge that move in a certain direction across the wire during a certain time. Then you divide that by the amount of time that the charge has taken to pass, and that is the value of the current. Now the voltage, as defined in the past, is the electric potential energy per unit of charge. So if you have a certain amount of electrons sitting into a wire, they're going to have a certain electric potential, and you just then divide by the total charge. So now you have the energy per unit of charge. We can also rewrite this as U divided by number of electrons multiplied by the charge of the electron. Now, if you multiply V by the current, what we obtain is very easy to calculate, because you see immediately that these two, the numerator here and the denominator here, they will simplify. And so what you will obtain at the end will be just, the energy divided by the time. So multiplying the voltage by the current into a certain wire, it gives you the change of energy with the time. This is exactly the definition of electrical power, which is the rate at which the energy is converted or transmitted. So we can call this P, and the unit of measurement is the watt. Let's talk a little bit more about the definition of electric power. So the electric power is the rate at which the energy is transferred from one system to another, but also the rate at which the energy is converted from electrical energy to other form of energy. So this could be a little bit complex to understand. So I wanted to give you an example, in particular of conversion of energy from electrical to thermal. This is something we already discussed in the past, but it's good to bring it back now that we have discussed power. So a resistor, as indicated down here, now we move to this definition, inhibits the flow of current in a circuit. The larger the resistance, the more difficult it will be to have a current through it. In fact, energy is required in order to have a current going through a resistor. Energy, which in electrical circuit is usually represented by a voltage, as the voltage is a representation of electric potential energy. In fact, if we have zero voltage, we also have zero current. There's no energy available to have an electron go through the resistor. Now, the interesting thing here is that in the case of the resistor, the energy is dissipating, heating the resistor itself. So as the electrons are pushed through the device, through the resistor, as we discussed at that time, they will bounce against the structure of the resistor, against the lattice of the resistor, and they will convert their electric energy into thermal energy. And the net result of this is that the resistor temperature will increase. Now, let's calculate what's the power that is dissipated on the resistor. And in order to do that, we just reuse this fundamental equation that we just calculated here, and we apply that for the case of the resistor. For a resistor, well, we have V multiplied by I, and now what we can do, we could replace I with another equation from the Ohm's law. So V is also equal for a resistor of V divided by R. So now if you write it this way, we can say that this is also equal to V squared divided by R, and is equal to the power. This equation can also be written in another way. Instead of replacing I with V divided by R, we can replace it V with I multiplied by R. So in that case, this is equal to I squared multiplied by R. So these are two identical equations. They give exactly the same result, and the power that is dissipated through a resistor is the rate at which the electrical energy is converted from electrical of the electrons into thermal energy. Let's try to understand the difference between power and energy with another hydraulic example. So here we have a little system with a cistern. Cistern is a big tank full of water, and this big tank is at a certain elevation compared with the turbine, and let's call this different in height h, and let's say that is equal to 100 meters. Then we have a valve that can be open and closed, so allowing the water to flow down through the turbine. And the turbine is just a device that can be used to convert the energy of the water into electrical energy, for example, to power a house. Now let's do a little bit of a calculation to see, first of all, what is the energy that is stored into the system. As we said before, because we have a certain amount of water with a certain mass at a certain elevation, that is equivalent, that means that the water will have a certain potential energy, in this case gravitational potential energy. So here we have a few numbers. Let's just do the math. So we have been told that the volume of the system is 10 cubic meters. So as a consequence, because this is water, we have a weight of 10 tons, so 10,000 kilograms. So now the energy, U, it's equal to mgh, where g is the gravitational acceleration, which is roughly equal to 10. So if you substitute, so the mass is again 10 ton, g is about equal to 10, and h is about 100. So in the end, what you get is about 10 megajoule. So this is the energy that is stored into the system that can be used to produce a certain amount of work. The way you produce the work, in this case, is by opening the valve, letting the water flow down, and turn the turbine, so that the energy can be converted into electric energy. Now, let's say we have a certain flow of water that is equal to 1 cubic meter per second. So when you open the valve, you have 1 cubic meter per second of water coming down. So now, in this way, we can easily calculate what is the power that is transferred from the water to the turbine. So we have 1 cubic meter per second. Now this cubic meter, each of the cubic meter has a weight of 1 ton. And then we can multiply by the acceleration of gravity and the height. So in this case, you see, it's kind of a similar equation. We have the mass, we have the acceleration, and we have the altitude, and all of that divided by second, meaning this is the energy that we are transferring every second. So this is equivalent to, if you do the math, 1 megawatt. So this is the amount of energy that is transferred every second from the system through the turbine. So in this case, because we have 10 megajoule and we are delivering a power of 1 megawatt, that means that after 10 seconds, all the energy will be consumed. Now on the right, I have exactly the same drawing. The system is the same, it's still 10 cubic meter. So the mass of the water is the same, it's 10 ton. But now, as you can tell, probably from the drawing, the size of the tube that connects the system to the valve is much bigger. So it's possible for a much larger amount of water to flow down to the turbine. As a consequence, I also increased the size of the turbine, just so that it fits correctly the size of the tube, but that is a secondary detail. So obviously, if we do the same math that we've done before, the energy stored is still going to be the same, mgh, so it's equal to 10 megajoule, because we have the same amount of water and we have the same amount of height difference between the system and the turbine. But now, because the tube is much bigger, it is possible for the system to deliver bigger power, because just a bigger amount of water is allowed to flow down from the system to the turbine. So now let's say this tube is roughly twice as large as the previous tube, at least in my very simplified drawing. So let's say now the capability, the flow of water can be 2 cubic meter per second. So now this cubic meter per second, each of the cubic meter will have energy of 1 megajoule, and because we have 2 of them, so we have 2 megajoule per second. So if we have this, the power that is delivered, it will be 2 megajoule per second, which is equal to 2 megawatt. By the way, if I haven't told that before, obviously given the relationship between power and energy, while the energy unit of measurement is joule, J, the power is watt, W, which is equal to joule per second, because as we said, the power is basically a representation of a rate of energy. So it is natural that the unit of measurement, which we decided to call watt, is the ratio between joule and time. But now let's go back to these results here. So we see that in these two examples, we have the same amount of energy. Again, these two systems has the capability to deliver an overall total amount of work, 10 megajoule, both of them can do the same thing because they have the same amount of water at the same altitude. But in one case, the tube is larger than the other case, so it is possible for the water to flow out of the cistern at a higher speed, and as a consequence, we can generate a much bigger amount of power. Again, this water analogy can be linked to the electrical analogy, where the energy is obviously the energy into a battery. The flow of the water, expressed in this case in a cubic meter per second, is equivalent to the current. The altitude is sort of an equivalent to the voltage. So as you can see here, in these two cases, we are representing a case where we have a battery with the same amount of energy, the same amount of voltage, but in one case, we have a capability of delivering a much higher current to the load, which is the turbine, so we are able to generate a bigger power. So you can think at an example where, for example, we have the battery here, it could be 5 volts, and a certain resistance R, while in this case, we have again 5 volt, the battery is the same, has the same amount of energy, but in this case we have, for example, 2 times the resistance, which means that the current that can flow through the system is half the current that can run into the other case. So the power that we are going to deliver is also going to be half. In this section, we are going to talk about capacitors, which are another very important component used in electronics. We will discuss how capacitor works. We will talk about capacitor in series and in parallel. We will discuss charge, discharge, and time constant of capacitors. And finally, we'll talk about applications of capacitors. What is a capacitor? A capacitor is an electrical component with 2 terminals, kind of like the resistor. People commonly refer to capacitor as cap for short. Caps are components that are particular, differently from resistors that don't store any energy. Capacitors are able to store electrical energy, and you can think of them sort of as little batteries. Capacitors are used as energy storage. They're used for signal filtering and also to suppress voltage spike. In this lesson, we are going to discover how capacitors are made, what's the fundamental structure, and how they work. So first of all, let's focus our attention on the left of the slide, where we have a sketch of a parallel plate capacitor. This is the way capacitors are usually introduced, like in school, because it's the easiest way to understand how the capacitor work and what are the fundamental components of its structure, though obviously commercial capacitors you can buy, they're not fabricated this way, but this is nonetheless a good way to introduce the component. As you can see, it looks like sort of a sandwich. There are 3 main components. So 2 of them are on the top and the bottom, and they are metallic plates. So you can think about this as really 2 pieces of metal, flat as a plate in this case, that are able to conduct electricity. And then in the middle of the sandwich, we have a material here represented in gray, which is an insulator. So this material actually does not allow the current to go through the device. And this material is called dielectric. And you can have different materials there, and different material will be characterized by different constant, which is epsilon r. And the epsilon r indicate the relative permittivity of the material. Now, as we will see later, depending on the geometry of the plates, the distance of the plates, and the epsilon r, the relative permittivity of the material, you will get different value for the capacitor. On the right of the slide, we now go ahead to explain how the capacitor actually work. So there is a little circuit here, so let me introduce the circuit first. So we recognize different elements. So this one is the voltage generator. Again, this could be just a battery. That's probably the easiest way to think about it. But ultimately, this could also be there are instruments that you can buy and then just give you a certain voltage. Then we have a switch here. And then on the right, we have a stylized version of the parallel plate capacitor that we just talked about. Actually, this is exactly the way the capacitor is represented in circuits. So we'll see that later a little bit better, but capacitors usually are represented in circuits just like this. So exactly to remind you the example of the parallel plate capacitor, and to remind you the way the component actually works. Let's now see what happens when we close the switch. So we close the switch. So now the two part of the two components of the circuit, which is the battery and the capacitor, are now going to be in parallel, as you can easily tell. Hence, they'll be subject to the same voltage. So whatever is the voltage of the battery, you are applying that voltage to the capacitor. As we discussed before, the capacitor is made of two parallel plates, which are made of metallic material. You can think as if they are made with the same type of material of the wire. So just like a strange looking wire. But in the middle, there is a material that is an insulator. So it's kind of intuitive to think that, okay, maybe something will happen just the instant after you close the switch. There will be some current, some readjustment of charge and voltage. But then eventually, the current through the circuit has to be zero. Because as just I'm indicating with the symbol of the capacitor, there's really no direct connection between the upper and the lower part of the circuit. And that is in fact true. So when you have a constant voltage applied to a capacitor, eventually the current becomes zero. This may seem a little bit strange, but actually capacitor can still be very, very, very useful as an energy storage device, as we'll see later. So what happens is that a certain amount of positive charge is accumulated on the plate, on the upper plate, and a certain amount of negative charge is accumulated on the lower plate. Keep in mind that usually the distance between the two plates, now here is highly exaggerated just to make a point, but usually it's really, really, really small. So yes, the circuit is open, there's no direct connection between the two parts of the circuits, the two terminals of the battery, but these two plates are really, really close to each other. So positive charges and negative charges are not allowed to cross the capacitor to go on the other side, but they definitely see each other really well. And because positive and negative charges want to attract each other, we're going to have a significant electric field inside of the capacitor, just as I'm indicating here. The slides contain the two fundamental equations of the capacitor. So the first is this, very important. So this equation is a relationship between the amount of charge that a capacitor stores on its plates, the value of the voltage applied to the capacitor, and a parameter that is called C, which is the capacitance of the device. So obviously, a component called capacitor is characterized by a fundamental parameter, which is its capacitance. Now, this equation tells us that the amount of charge that can be stored on the plates is directly proportional to the capacitance and the voltage applied to the capacitor itself. The second equation that we want to discuss is down here, and this equation defines the value of the capacitance for a capacitor of a certain geometry and made of certain materials. The formula says that the capacitance C is equal to epsilon 0 multiplied by epsilon r, where epsilon r is a relative permittivity, whereas epsilon 0 is the permittivity of vacuum. So these are just constant. Epsilon r depends on the material that you use to make the dielectric, and then it's multiplied by A, which is the area of the metallic plate, and D is the distance between the metallic plates. So in this case, D will be the distance between these two plates, and A will be the area. The unit of measurement of capacitance is the farad, which is indicated with a capital F. 1 farad is a pretty big amount of capacitance. You will almost never find a capacitor with capacitance equal to 1 farad. So most of the time, the value of the capacitance will be in the range of microfarad, nanofarad, or picofarad. The equations that we just discovered tell us a very important thing. So the first step here tells us that the amount of charge that is stored in a capacitor for a given voltage depends on the capacitance. The other equation down here tells us that the capacitance in turn depends on the geometry of the capacitor and the material used to build the capacitor. So if you put these two concepts together, the result is that the charge that can be accumulated, that can be stored on a capacitor for a given voltage, depends on the geometry of the capacitor and the material used to build it. The goal of this lesson is to give an intuitive understanding of why that is the case. Two are the things that you have to keep in mind to understand this, and are very simple. The first is that charges with different sign attract each other, and the second is that charges with the same sign repel each other. The battery here, you can imagine it as an unlimited supply of positive and negative charges. So what we're trying to understand here is why, after all is said and done, only 4 positive charges and 4 negative charges are sitting on the plates. Why not 5? Why not 6? Well, in order to understand that, we'll imagine to be in the mind of a positive charge sitting there and try to decide whether to go in the capacitor or to stay in the battery. So 2 thoughts will go through the charge's mind. So the first is that the charge really wants to go on the capacitor plate because it really wants to reach the other side of the battery. It really wants to reach and recombine with negative charges. At the same time though, in order to do that, that charge will have to go on the plate, which is full of positive charges. We know the charges of the same sign repel each other, so that's one reason why that charge might not want to go on the capacitor plate. This trade-off between wanting to go on the plate and not really wanting to go there goes through, if you want, every charge's mind. But in the end, an equilibrium is reached and a certain amount of charge is allowed to be on the plate. It's now easy to see why the geometry of the capacitor and the material used for the dielectric changes the equilibrium point that determines the number of charges accumulating on the plates. Let's start with the first element here, which is probably the simplest one to describe, is the distance. So if I change the distance between these 2 plates, now for this charge sitting here, there is a much stronger incentive to go on the plate, because yes, there are still positive charges there, but there's still just 4 of them, and now the negative charges are much closer. So there is a stronger incentive to go on the plate. Of course, after the 5th charge that's gone on the plate, a new charge, a 6th charge that wanted to go on the plate, will have to take into account that now for the given distance, now there are 5 positive charges on the plate. So it is possible that the 6th charge decides not to go in the capacitor after all. Let's now consider the effect of the area on the amount of charge accumulated on the capacitor. Well, the area works in a different way than the distance, in the opposite way actually. So it's a bigger area that gives you a higher amount of charge in the capacitor. The reason for that is intuitive and simple. So if we increase the size of this plate, the area of the plate, now for the same distance between the positive charges and the negative charges, now the positive charge sitting here and trying to decide what to do, we'll see that after all going on the plate is not as bad because the density of positive charges is not so high. So yes, there will be 4 charges, but that new charge will be able to carve a larger space for itself. So the charge eventually decided to go on the plate. Now again, a 6th charge wanted to do the same. We'll have to consider that the real estate available has been decreased because a 5th charge went there, and so on. Last but not least, let's describe the effect of the dielectric material here, epsilon r. The dielectric material is put in between the 2 plates. So for a certain fixed distance between the plates and a certain area of the plates, if you change the dielectric, you can change the amount of charge that will be willing to be stored. The reason for that is that the dielectric can make it easier or more difficult for the positive and negative charges to see each other. So if you choose a dielectric, then make it easier, more charges will be stored in the capacitor. If you choose a dielectric, then make it more difficult for charges to see each other, there will be a much lower incentive for charges to cram themselves in the plates, and as a result, a lower amount of charge will be stored. Another thing worth noting is that a capacitor always has the same amount of positive and negative charges. As you can see here, for each negative charge on the lower plate, you have a positive charge in the upper plate. Each positive charge in the upper plate is neutralizing the effect of one negative charge in the lower plate, so that a new positive charge doesn't have an incentive to go on the plate. If you had a much higher number of negative charges than positive charges, then other positive charges will want to go on the plate because they will be able to see the negative charges through the positive charges. But the moment that you have the same amount of positive and negative charges, the capacitor becomes neutral in a way, so a new charge will not have an incentive to go on the plate. So at the equilibrium, the number of positive charge and negative charges is always the same. To summarize what we have learned so far, the simplest representation of a capacitor is made by an insulating material that is called dielectric. And this material is sandwiched between 2 metallic, so conductive plates. one on the top, upper plate, and the lower plate. The capacitance of a capacitor, which is the main parameter of this component, represent the amount of charge collected on one plate for a given voltage. So if you apply a certain voltage V across the component, you will accumulate a certain amount of charge plus Q on one of the plate and minus Q on the other plate. The capacitance, which is indicated with C, remember that Q is equal to C multiplied by V. The capacitance C is measured in farad, but as I already said before, farad is a really big amount for capacitance. So most likely you will see values of capacitance expressed with different submultiple of the farad. For example, with typical scientific notation, microfarad, nanofarad, and picofarad, where each of these unit of measurements means that you have 10 to the minus 6 farad, 10 to the minus 9 farad, and 10 to the minus 12. So for example, if someone gives you a capacitor that has a capacitance of 1 microfarad, you will know that the amount of capacitance of this capacitor is 1 over 1 millionth farad. In this lesson, we're going to discuss why a capacitor is an energy storage device, and we're going to try to provide an intuitive explanation of why that is the case, though we're not going to go into complex physical calculation or demonstrations. On the left, we have our usual parallel plate capacitor. As you can see, we have the two parallel plates, metallic plates, we have a dielectric. We apply the voltage across the two terminals, and we know that when that happens, that means that we have a certain amount of positive charge accumulated into the upper plate and a certain amount of negative charge on the lower plate. And the presence of this accumulation of charge, or positive and negative charge, generates an electric field within the dielectric. We also know that the amount of charge that is accumulated on the capacitor depends on the voltage and also on the value of the capacitance of the device, which in turn depends on the geometry of the device and the dielectric, accordingly to this equation, Q equal to C multiplied by V. Let's talk about the energy storage aspect of a capacitor. So let's say we have this capacitor on the left that is biased at 3 volts, which means V is equal to 3 volts. For example, we can say this terminal is a ground, so 0 volt, and this terminal is at 3 volts. Now, if we remember the definition of volt, we know that volt is electric potential energy per unit of charge. Well, now if we look at this drawing, we see that we have a certain amount of positive charge Q that is sitting there at 3 volt potential. So if volt is electric potential energy per unit of charge, and we have a certain amount of charge sitting there at that potential, at that voltage, that means that the capacitor in a way is storing a certain amount of electric potential energy. Now, if we look at the second bullet, we also remember that Q, the amount of charge, is also directly proportional to the capacitance. So for the same amount of voltage that you apply to the capacitor, if you double the value of the capacitor, you double the amount of charge that is stored in the plate, which in turn means that you are doubling the amount of energy that is stored by the capacitor. So in a way, we can say that the capacitor is an energy storage device. So if you have a capacitor and you apply a certain voltage, that means you are storing in the capacitor a certain amount of energy. The bigger the capacitor, the bigger the energy for the same voltage, and vice versa. If you now want to quantify the amount of energy, that is not a very easy feat. In order to do that, you actually have to do a more complex calculation that involves integral. I give you the short version of it, or rather I just give you the solution. So if we look at the last bullet here, that shows us what is the electric potential energy that is stored on the capacitor for a certain given amount of voltage and a certain amount of capacitance. So the value of the energy is 0.5 multiplied by C and multiplied by the square of V. So actually the energy stored in the capacitor highly depends on the voltage. So the voltage goes with the square. So if you double the voltage, you actually quadruple the amount of energy. And it goes linear with the capacitance, as we said before. So if you double the value of the capacitance, you double the amount of energy. Before moving on, I want to make an important point about the capacitor that is illustrated in bullet 3. So we said that capacitors store energy And that is true, the capacitor stores energy in the electric field, and despite the fact that my explanation was everything but accurate physically, the concept is real and the equation I provided for the energy is correct mathematically. Now, you also heard me say many times that the capacitor stores charge. But if you think about it, that is not really true. Just look at the drawing that I have on the left. Does it look like the capacitor is storing charge? I don't think so. Think about it. Like, all I'm saying here is that when I apply a certain positive voltage, I have a certain plus Q on the upper plate and a certain minus Q, a negative charge on the negative plate. So if that is the case, this doesn't really match very much with the dictionary definition of storing something. I have a plus something on one plate and minus something on the other plate. So when I consider the capacitor as a whole, there's really no net charge that's being stored. Plus Q and minus Q will simplify each other. So at the end of the day, you could say that the net amount of charge is always the same. So what's going on here? Well, what's going on is this. So remember, we don't really have positive charge in circuits. It's all about electrons moving around. So when you apply a certain voltage to a capacitor, what's happening is that a certain amount of electrons are accumulating to the lower plate. So they are adding to the already present electrons in the plate. And the same amount of electrons are fleeing the upper plate. So remember, the plates are metallic, so they have their natural amount of electrons there. And when you apply a voltage, all you're doing is that you're adding some electron to the lower plate. So you end up with more electrons. And you remove some electron from the upper plate. So that is what's happening. So in effect, there is no storage of charge because you increase the charge on one plate, but you decrease the charge on the other plate. The human brain doesn't deal well with the absence of object. So it's very non-intuitive to say that you have a positive charge plus Q on the upper plate because you have a lower number of negative charges accumulated there and a lower number of electrons. It's much simpler to believe that a positive imaginary charge exists, and when you say that I have a amount of positive charge accumulated on a plate, it means that this positive charge somehow got accumulated there. Similarly to what happens to the lower plate for electrons. Different being that for the lower plate that is true, for the upper plate that is just a trick, just something that we imagine to make the analysis of the capacitor easier. Another reason why using positive charges is useful is that positive charges move in the same direction of the current, and the human brain really wants to make analogies to understand events. So in the case of the current, it's very easy to make an analogy between a stream of water and the current. In the stream of water, you know that the stream is going in that direction, the flow is going in that direction, because a bunch of molecules of water are going in that direction. And it's easy to believe the same for the current as well. So the current is going in that direction, there must be something moving in that direction. So that's why using positive charge is something that is down all the time, but you have to keep in mind that usually whenever I plus Q, it really means that you have a lower number of electrons there than you would usually have if there was no voltage applied. To summarize again, the capacitor in effect does not store any charge, but it simply changes the distribution of the same amount of electrons between the two plates. So one plate ends up having a higher amount of electrons, the lower plate. The other plate ends up having a lower amount of electrons. In this lesson, we're going to talk about the symbol used to represent the capacitor in a schematic. I already used a symbol before. I've used this one. And as you can see, it represents really well how a parallel plate capacitor is built. In general, it represents how capacitors are built. They're made of two plates separated by an insulator, and this symbol is very good at reminding you that. Now here I represent the 5 different options for the symbol that you can use. In most cases, the difference between, for example, this symbol and this symbol or this symbol is simply depends on a style choice for your design. And sometimes the difference is also geographical difference, like some symbols are more used in US, others are more used in Europe, but as you can tell, there is no fundamental difference between these symbols. They all represent the same component. The only two symbols that are really significantly different are these two in the middle. The symbol contains a plus sign here. In the case of this one, we also have one of the two plates has a different color, a different filling. So in this case, the plus is not me trying to represent a positive charge accumulated, but this symbol is meant to indicate that the component needs to be mounted with a certain orientation, meaning that the way this capacitor is fabricated is such as the voltage at these terminals always needs to be higher than the voltage in the other terminal. So when you eventually put in your circuit, you have to make sure that the voltage in your circuit is always applies in this direction, and it's never applied with the opposite orientation. So the terminal on the top in this drawing always has to have a higher potential than the one at the bottom. Otherwise, if you don't do that, the capacitor could actually explode. It will definitely be damaged. These components are called polarized. And again, all it means is that they have a certain orientation. Once they are placed in the circuit and once they are in operation, they behave just like any other capacitor. But you just have to be extra careful to make sure that the orientation is the correct one to prevent any damage. In order to understand better how a capacitor works, and in order to have a better intuitive understanding, I'm going to resort again to a water analogy. So you see here on the left, we have an hydraulic equivalent of a circuit. Which circuit? Well, it's very simple. There is a voltage generator represented by the pump. There is a resistor, and then there is a capacitor. So C, R, and V. So we have already seen that the pump role in these circuits is to generate a differential pressure between the intake and the outtake. So all the pump is doing is to generate a certain delta P that for us is a representation of a delta voltage. Now the resistor, we know it's an element that opposes to the passage of a current. So in the case of a hydraulic example, is the passage of a water. So it can be represented as a choke into the tube that connects the pump and the capacitor. And the capacitor instead can be represented as a water tank split in half by an elastic membrane. So as you can see here, there is a membrane in the middle. This membrane is elastic, so it can be bent by a difference of pressure between the two chambers of the tank, but it's watertight. So it's not possible for any water to actually go through. But again, it's elastic, so if there is a difference of pressure between the two parts of the tank, it will be able to bend. A final thing that I want to highlight is that the two chambers of the tank, they have each one of them as a certain volume. So that means they can store a certain amount of water that for us is a representation of the charge. Before considering what happens when we turn on the pump, let's assume that the pump is off at first, and let's establish what's the value of the important parameters of the circuit. So in particular, for an electric circuit, we want to know what's the value of the voltage at every node and what is the value of the current in the circuit. In this case, this is an hydraulic example, so we know that the voltage is represented by the pressure and the current is represented by the water flow. So let's try to define those. So the bottom part of the circuit is equipotential, equipressure. So they're going to have a certain value, and let's assume that the value of the pressure is equal to 0. Again, in electronic circuits, what really matters is the difference in pressure. So the fact that we assign the value 0 for the lower part of the circuit does not make any difference. It's just a convenient starting value. The pressure on the top part of the circuit will be different on the left and on the right side of the resistor in general. So we are gonna distinguish those two areas, and we are gonna draw two little graphs because we expect the pressure to evolve with the time after we turn on the pump. So we'll have these two little graphs, and at time equal to 0, which is what we are considering now, time equal to 0, the pressure is equal to 0 on both sides of the resistor. This means that the current going through the resistor is 0. There's no incentive for the water to go to the left or to the right side of the resistor because the pressure is the same. But another important consequence is the following. If we look at the capacitor, what we're saying is that the difference in pressure here is equal to 0. Now, pressure is a representation of a force over an area. So because the area is the same of the membrane on the two sides, the force applied in this direction and the force applied in this direction will be the same. So the membrane will just stay in the middle of the capacitor completely relaxed. This means that the two halves, the two chambers of the capacitor, will store the same amount of water. For us, the amount of water in the two chambers of the capacitor, it's a representation of the amount of charge stored by each of the plate, and in particular, it's a representation of the amount of electrons. Let's say we're now at time equal to 1, could be 1 second, 1 minute, and at this time we turn on the pump. So the pump is now on. This specific pump was designed to generate a delta pressure equal to V. I call it V because we already know the delta pressure is a representation of the voltage. So now, if we look at the pressure on the left of the resistor, we know that at time 1, the pressure went from 0 to a value equal to V. And from that moment on, the pressure will always be equal to V until we turn off the pump, because that is exactly how the pump is designed, fixed difference in pressure. We want to know what happens to the right of the resistor and specifically on at the capacitor. So at time equal to 1, the pressure in the capacitor will still be equal to 0. Because in order to have an increase in pressure there, we need to have a certain amount of water be added to the capacitor, to the upper chamber of the capacitor, and you need at least a certain amount of time to fill it with some water. So at time 1, you just turn on the pump, still the pressure in the capacitor is equal to 0. If the pressure is equal to 0 in the capacitor, now we can see that we have a difference in pressure across the resistor. So if we measure it like this, we have a difference in pressure that is exactly equal to delta P, which in our case is equal to V, because we have a pressure equal to V on the left and a pressure equal to 0 on the right, so the difference in pressure is equal to V. That means that we're going to have a current going through the resistor, or a water flow through the resistor, and this current is going to be equal to V divided by R accordingly to the Ohm's law. As the water keeps flowing from the left of the resistor to the right, water gets accumulated in the in the upper chamber of the capacitor. Remember that the membrane is watertight, so it's not possible for the water to actually circulate in the circuit, but the upper chamber will start getting filled with more and more water. So because there's no possibility of water to flow through the membrane, that means that the pressure on the upper chamber of the capacitor starts increasing, just like this. Pressure is force over area. So if we look at the chamber now, the bottom part of the chamber, the bottom chamber, has a pressure equal to 0. So the force, now here if you change it, that means that the force is equal to pressure multiplied by area. So in that case, the force will be equal to 0. So we have a force up here equal to 0. On the other side, on the top, on the upper chamber of the capacitor, we have a certain amount of water. The pressure is not 0 anymore. So we have a force that is bigger than 0. So that means that there is a net force that is applied to the membrane, and as a result, the membrane will start to bend. So if I delete it here and I represent with a dashed line the original position of the membrane, we'll see that the membrane start getting the form more and more as the pressure keep increasing. Now the question is this trend going to keep going forever? Is the pressure going to keep increasing in the capacitor and the membrane will keep deforming and deforming forever? It's easy to understand how this cannot go on forever, because otherwise the membrane at some point will break. Inevitably, it cannot be able to sustain an infinite force. So in order to understand what's happening, we have to look at the graph that we are drawing a little bit better. So we had initially a pressure equal to V on the left side of the resistor and a pressure equal to 0 on the right side of the resistor. And for that reason, we said that the current was going to be equal to V divided by R. That was true, but if you think about it, that was true only at the very beginning. Only at time equal to 1, the pressure was exactly equal to V and the current was equal to V divided by R. As the pressure built up on the left side of the resistor, the current will have to decrease. So let's try to do a little bit drawing here to represent this. Instead of having this fixed value for the delta pressure, I'm just gonna introduce another graph. So this graph represents the delta pressure across the resistor. At the beginning was equal to 0. At time equal to 0, it was 0. And then at time equal to 1, it became equal to V. All of a sudden it jumped up. But now, as you can see here, the pressure is increasing on the other side, so the delta pressure is slowly going up. And because the current is equal to the delta pressure divided by R, that means that also the current, it's decreasing with exactly the same waveform, with exactly the same behavior. This means that the rate at which the upper chamber of the capacitor is filling up is decreasing as the time goes on. So initially it fills up very quickly, but later the flow of water starts decreasing, so the amount by which the membrane gets stretched becomes smaller and smaller. If you let a long amount of time pass, the final state, the final equilibrium state at which you will find the circuit is the following. So the pressure across the capacitor, or the pressure in the upper chamber, would have reached the same value of the pressure that is applied on the left side of the resistor. So it will be equal to V, the same pressure value as the pump. For that reason, the delta pressure on the resistor would have reached 0, and same will happen for the current. So there will be no current anymore going across the resistor, because again, the pressure across the resistor is the same. The membrane will be deformed to the maximum extent, and it will stop moving. The water analogy for a capacitor allows us to see how a capacitor is a device able to store energy, and it also allows us to see once more that a capacitor is not, despite what people say when they use it, and despite what I say when I use it, when I refer to it, a capacitor is not a device that stores charge. We have seen with the exercise that after a pump is turned on, a certain different pressure is applied, and if you wait a long enough time, you are gonna have a different pressure applied across the two chambers of the capacitor. So you end up with the delta pressure here that is equal to V, is equal to the same delta pressure applied by the pump. So the difference in pressure means the difference of force applied to the membrane. So the membrane that is watertight, but it's elastic, will bend. The energy that we know a capacitor is storing in the electric field is represented in this water analogy by the elastic membrane being bent, because any elastic material, when it's in non-relaxed state, is in effect storing energy in a form of elastic potential energy. Because you know that if you release the force on that device will snap back, so it is able to produce a certain amount of work. So this membrane that is in a stress condition, it is bent, and storing energy as elastic potential energy. Regarding the charge, it's easy to see from this water analogy that whatever charge entered the upper chamber, the same amount of charge have to have left the second chamber, because the membrane is completely watertight. You simply move the membrane, so the same amount of water that entered the membrane from the top left the bottom of the capacitor. So this is equivalent to say that when we say that a capacitor has a certain amount of charge Q, all we are saying is that we have an additional amount of electrons accumulated on the negative plate, and the same amount of electron has left the positive plate. Let's now see with a slightly better example how the capacitor stores energy with this water analogy. So as you can see on the slide, we got two capacitors there. I isolated the capacitor from the rest of the circuit. Same as before, let's assume that the pressure down here is equal to 0. And this is, the atmospheric pressure, for example. So the pressure is equal to 0 everywhere outside, like in this page. The lower part of the capacitor is open, so the pressure is equal to the ambient. Now we have these two capacitors, and we assume two examples. So one case is we have the capacitor with the membrane at rest, and so that means that the pressure inside is equal to 0. And the other case, the pressure inside is bigger than 0. And as you can see here, I drew a little door there. So in a way, you close the upper chamber of the capacitor so that the pressure can be kept there. And of course, we are assuming that there is a bunch of water here, for an example. Well, I don't think I need to provide much more explanation than this one. Everybody will realize that there's a very big difference of the behavior of the capacitor when we let the door open. So in one case, in the case on the left, when we let the door open, as I indicated here, let me delete and redraw this. Open, so now it's open. Nothing really is going to happen. The water is going to stay inside the capacitor because there is the same pressure outside, inside. It's really like a smooth event. Nothing really is happening. Like in this other case, though, that makes a big difference. Like when the door is open like this, the pressure inside is higher than the pressure outside. A bunch of water will just come out of this capacitor. So that hopefully should give you a better understanding of why elastic material that is in a stress state is storing energy. This energy is elastic potential energy. Generally speaking, as you know, energy is generated and stored every time you somehow fix the setup, fix the system in a way where it doesn't really want to stay. Like in this case, the membrane wants to be relaxed, it doesn't want to be stressed, but somehow you build around it a setup that keeps the membrane in that state. In this case, you put the water and you close the cap of the capacitor, you close the door. But then you see that the moment that you open, the energy will be released and a certain amount of work will be accomplished. In this case, the work is accomplished to move the water out of the capacitor. So I hope this example helped clarify a little bit. In this lesson, I want to talk about AC current in a capacitor. First, let's start with some definition. So here you can see the definition of DC current or direct current. DC current is a current where the electric charge always flows in the same direction. So for example, this is a possible representation of a DC current. So it's a current that always have the same sign, basically. So all the currents that we've seen so far were of this type. We had a battery. The battery is also a DC voltage, so-called, because the voltage also never changes sign. And then you connect it to the circuit, you wait some time, and eventually, let's say if you have a resistor, you have a current that is constant and always in the same direction. On the contrary, AC currents, or alternating current, as the name suggests, is a current where the electric charge changes direction periodically. So for example, electric AC current is a current whose behavior is like this. So it changes sinusoidally from a value, a positive value, to a negative value, which means that the charge is moving back and forth in your circuit. Before talking about alternating current, let's refresh our memory with studying what happens in this circuit for DC current. So I forgot the membrane here. So DC current is a current that is always going in the same direction. For example, a constant current like this one. Now this current is always positive, which means that you have a certain amount of water, in this water example, going in this direction. Now this water has nowhere else to go than inside the capacitor. And inside the capacitor, unfortunately, there is a membrane that is watertight, so the water doesn't have any other thing to do than just accumulate into the upper chamber. Now, in order to allow for additional water, we have already seen that the membrane will have to deform. And if we are forcing a current that has this shape, that is constant and it's forever a positive value for the current, that means the membrane will have to continue stretch. Now, it's easy to see how this is not possible to sustain indefinitely, and eventually the membrane will break. And this is exactly what happens also in the electric circuits. If you try to force a DC current into a capacitor, the voltage across the capacitor will keep increasing, and eventually you break the device. Let's now move on to the alternating AC current case. So let's say you have a current here that, because you have a special pump, this current behaves like this. So it keeps doing like this. So you have an I peak, and then you have a minus I peak. So the current keeps changing in a sinusoidal way. So it keeps changing direction with the time in a periodic fashion. So if you look at the water in a section of the tube, the water keeps going back and forth, back and forth, back and forth. What does this mean for the capacitor? Well, if you look at the membrane, when the water is going down, so the current is positive, so the water is getting accumulated in the upper chamber. So the membrane will stretch like this, whereas in the second part of the period, the current is actually going up. So we are actually taking water out of the upper chamber and injecting water in the lower chamber. So now the membrane will stretch this way. So with alternating current, the membrane will keep just being bent up and down, up and down. There is no net accumulation of water in either of the chambers. And as you can clearly, intuitively understand, this is a situation where we can keep operating the capacitor indefinitely. In conclusion, we can say that capacitor block DC currents but allow AC currents. So it is possible to sustain indefinitely a current through a capacitor as long as this current is alternating. So as long as the direction of the current is periodically alternating, so that there's no net accumulation of charge or any of the plate of the capacitor. So remember not to get fooled. The constant of current is purely related to the movement of charges. It doesn't require that the charge starts from one side of the pump and goes all over around the circuit to the other side. Because if that was the case, then you couldn't have any current with a capacitor, because you have a watertight membrane that will not allow a charge to complete the whole loop. The current has everything to do with the movement of charges. So that if you sit in any section of the circuit and you just look at that section, no matter how the rest of the circuit look, if you see some charges moving in a direction or another, you can say that there is a current. That is why capacitor, despite the fact that technically leaves the circuit open, still allows a certain current. What the capacitor does, in a way, it doesn't technically close the circuit, but it allows the two parts of the circuit to feel each other through an elastic membrane. So it allows the two parts of the circuit to influence each other based on a difference of pressure in this hydraulic example, or a difference of voltage. In this lesson, we'll discuss the relationship between the voltage, the current, and the charge for a capacitor. Before doing so, though, we want to refresh our memory talking about the relationship between voltage and current in a resistor. I represented the resistor here on the left. That's the schematic symbol. I represented the voltage in red and the current in green. And down here, I wrote the equation, the relationship between voltage and current for a resistor. This is called Ohm's law, and is a representation of a very simple relationship. It's a linear relationship where the current through the resistor is simply equal to the voltage divided by the resistance. You can also obviously write this equation in many different ways. For example, you can write it like this: V equal to resistance multiplied by the current, and vice versa. Now, what we want to do now is to represent this relationship in a chart. This is a VI chart. The VI chart represents a VI curve, which is the voltage and current relationship of a component, in this case a resistor. So as you can see, the linear relationship is simply represented by a straight line. I wanted to highlight a few different things. So first of all, as clear from the equation, when the voltage is zero, the current will be zero. So all of these curves are passing from the origin of the graph. So, and that is always the case with the resistor. And then another thing that is interesting to highlight is that in this case I represented curves for three different resistors. And you can see that as the resistance becomes larger, the slope of the curve becomes lower and lower, because you need a higher amount of voltage to generate the same current. In fact, if I clean up a little bit here, and let's say I assume, let's pick a certain value for the current, Ix here, for example, and I draw a line. So that is a line that represents the value of current equal to Ix. You see that for resistor R1, that is the smallest of all, you only need this amount of voltage to generate that current. For R2, you need a higher amount of voltage. And for R3, which is the bigger resistance, you need an amount of voltage that is even higher to generate the current Ix. For the most mathematical view, you can also note that there is a relationship between the slope of the curve and the equation, because the Ohm's law, it's just a linear equation. So the V in this case is the independent variable, which is the horizontal axis. The current is the output of the equation in this case. And you can see that usually a straight line is represented with an equation that is mx plus q, where m is the slope and q is like a fixed constant. So in our case, the q is 0, because the current is going to be 0 when the voltage is 0. But our m, in this case, which is a representation of the slope, is 1 over r. So each of these curves have a slope that is equal to 1 over r1, and this one has a slope that is equal to 1 over r2, and the last one has a slope that is 1 over r3. So the larger is the resistance, the lower will be the slope of the curve. Let's talk about the capacitor now. Just as I did for the resistor, I represented a schematic symbol of a capacitor. I indicated the voltage in red, the current in green. This time I also indicated the charge in blue, which is an important parameter for capacitors. Down here, I also wrote the equation between the charge stored in a capacitor, the capacitance, and the voltage. This equation is a linear equation. So similarly to what we've seen for the resistor, for Ohm's law, this will be represented by a straight line passing from the origin. And now this is an equation representing a completely different thing. It's not a VI curve, but it's still a mathematically linear equation, so it's still represented by a line. Similarly, as we've seen before, different value of capacitance will give you a line with a different slope. And in this case, the higher is the capacitance, the higher will be the slope, because for the same voltage, if the capacitance is higher, that means you have stored a larger amount of charge. The relationship between the current and the voltage in a capacitor is not as simple as in the case of the resistor, where you have a linear relationship. So we wanna discover it going step by step, and we're gonna go with a little exercise where I provide a value for the current, a waveform for the current, and we extract the equivalent value for the charge and then for the voltage. So here I have a graph that represents the behavior of the current over time. And then down here we have a graph that represents the behavior of the charge over time, and will also represent the voltage. One thing that I want to highlight is that the behavior of the current was an input of this exercise. So the shape that I chose was completely arbitrary for the current, and I chose this specific shape because it will let me explain a little bit better how the capacitor works, but it could have been any shape for the current because it was our input. Whereas the charge and the voltage will be just like an output, a consequence of the waveform of the current. Now, as you can see, the current waveform is split in 5 different regions where the current behaves in a completely different way, as you can see here. So in the first region, we have a constant current that is pretty high, a constant and positive current pretty high. Then in the second region, we have a constant and positive current, but the value is rather low. In the third period, we have zero current. In the fourth period, we have a negative small current going through the capacitor. And in the fifth period, the current is positive and it's increasing linearly with the time. So the current is getting higher and higher as the times go. The next step is to take the graph showing the waveform of the current, and by using what we know about the capacitor, extract the behavior for the charge. As you can see, I already done that, and we're going to describe each of the periods in details. But in order to understand how I went from the current to the charge, we need to remind ourselves what's the definition of the current, and also to resort once more to the hydraulic equivalent of a capacitor. So the current, as we've seen, is defined by the delta charge over delta T, and in our hydraulic example is represented by the flux of water, which is represented as, for example, cubic meter of water per second. Now the capacitor can be represented as a tank with a certain amount of water inside, and the volume of the tank is the representation of the capacitance, while the height of the water, the level of the water, is a representation of the charge. This relationship, this hydraulic example, should allow us to get the behavior of the charge, at least qualitatively, for a given behavior, for a given waveform of the current. If you take the relationship, the equation representing the definition of the current, and you multiply both sides by delta T, what you get is that delta Q is the current multiplied by delta T. This equation is telling you that there is a linear relationship between the charge and the time if the current is constant. This is pretty intuitive if you think about the hydraulic example, because this simply means that if you have a constant current, which means a constant flux of water going into your tank, the level of the water will just increase linearly with the time. So it will just go up like a straight line, and if you, for example, wait twice as much time, your level is going to increase twice as much the amount. So let's see, we'll use this relationship to solve the behavior of the charge for the first 4 periods. So let's start here. So first of all, I'm assuming that the charge starts from 0. Again, this is an assumption that I made. It's totally arbitrary. The charge and the capacitor could have had any value at the beginning. It's a state of the system, but let's make things simpler and assume the capacitor is discharged at first. So the voltage is 0, the charge is 0. Now, in the first period, we have a constant current, so we can use the relationship up there, and it's pretty high. So as I said before, that means that you have a stream of water, a flow of water going into your tank. It's pretty consistent amount of water. It's positive, so the water is going into the tank. That means that the charge is increasing linearly with the time. So we go from here to there, and then we go in a linear fashion. You probably understood the trick now. In the second period, the amount of the flow of water has decreased. It's still positive, but it's much lower. So now the charge, the level of the water will keep increase to the next level, still linearly, but at a much lower slope. So I want to highlight that this equation in effect gives you the delta Q. So it doesn't give you the total charge. It doesn't give you the total level of the water, but for each of the period, will give you the additional change from the current, from the initial state of the level. There can be a positive or negative change, but it's simply the change. So you always build on top of whatever was the leftover charge that you had in the previous period. Now, in the third period, the current is zero. So current is zero means that we turn off the water. So unless your tank has leaks, that means that the level of the water will stay the same. Hence, the level of the charge will stay the same. And finally, in the fourth period, the current is small, but it's negative now, which means that we are taking the water out of the tank somehow at a constant rate. So that means that the level is decreasing at a constant pace, so just as a straight line, and it will settle to a certain U level at the end of the period. It's a little bit more difficult to determine the behavior of the charge during the fifth period, because in the fifth period the current is not fixed, but it's changing. However, we can use the learnings that we had from the first four periods, and we can apply it there to get a qualitative waveform for the charge as well. So I believe that if we have to summarize really in a few bullets what we learned at the beginning of the exercise, we really learned two things. So one is that whether the charge increase or decrease, it really depends on the sign of the current. So when the current is positive, the charge is increasing, and when the current is negative, the charge is decreasing. So in the fifth period, despite the fact that the behavior of the current is kind of strange, it is always positive, so we expect the charge to increase. The second thing we'll learn is that the pace, the speed at which the charge is increasing in a period depends on the magnitude of the current. Here we see that the current is changing with time. But what we can do is that we can look at few points along the curve and determine what we expect to see. And based on that, we can draw a waveform for the charge. So if you look at the beginning of the curve, we see that the current is positive, so the charge has to increase. But the current is pretty low. So we expect that in this region, the charge will increase but slowly. If you look at the end of the curve, at the end of the period, the fifth period, we see that now the current is still positive, but it's much higher value. So we expect the charge to be increasing pretty fast. It is possible to draw a curve that looks like this. And as you can see, it's a curve that it shows that the charge is growing, and the speed at which the charge is growing is becoming faster and faster with the time. If you're curious, it's possible to mathematically calculate that the behavior of the charge in the fifth period is proportional, this symbol means proportional, with the square of the time. Which means that differently from the other periods, where if you double the amount of time with the current, you will end up with twice as much extra charge. In this case, if you double the time of period number 5, the delta charge that you obtain is not 2x, but it's 4x. I want to now make an important point regarding to the state of a charge of a capacitor. And it is something similar to what I said at the beginning when I said that assuming that the charge at the beginning was 0 was a totally arbitrary thing, and I could have chosen any other value. That is true. And if you look at the charge evolution on the capacitor, you can notice one interesting thing. In a way, the charge in the capacitor is a sort of a memory effect that the capacitor has on anything that happened previously to that point. So, for example, the fact that the charge is at this level at the end of period 3, it's because the charge started at 0 at the beginning, and then we had a certain amount of current in period 1, a certain amount of current in period 2, and another amount of current in period 3. So in a way, if the exercise started at point 3, we would have a different starting point for the charge, and the reason for that will be completely unknown to us, but it will be a representation of certain values that the current had previously to that point. For instance, if we add a different amount of charge at this point, time equal to 0, we will not know why the charge was at this point. Probably a certain amount of positive current was applied to the capacitor. Doesn't matter, but that value for the charge is an indication of things that happened to the capacitor in the past. And now, if we had to represent the evolution of the charge from that point, it would be very simple to know, to calculate, because as we said before, we are simply computing period per period the extra charge that is added to the capacitor. So in this case, if we start from this point, the resulting charge will be like this. So it will just be exactly the same graph, but it will just be shifted up by the amount of the initial charge. Finally, let's calculate the behavior, the waveform of the voltage given the charge. That should be pretty easy because, as we can see here, the charge and the voltage are connected by a linear relationship, where the voltage is equal to the charge divided by the capacitance. So if we assume that the capacitance is equal to 1 farad, which is a huge value but makes my calculation simpler, and we also assume another assumption we can make, that we have the axis of the voltage here is determined such as where you have 1 volt, you have 1 coulomb, so they are aligned. Well, then in that case, the waveform of the voltage will be exactly the same as the one of the charge in this graph. So it will follow exactly the same behavior. And naturally, the voltage is represented relative to a different vertical axis, but I trick the numbers so that they will perfectly overlap. But anyway, the main concept here is that once you have the shape for the waveform of the charge, the behavior of the charge over time, the behavior of the voltage will be exactly the same. So where the charge is increasing linearly, the voltage will also increase linearly, and vice versa. So in a way, when we look at the previous, at the hydraulic example here, the level of the water is a representation of the charge, but it's also it can be also used as a representation of the voltage, because there is a linear relationship between charge and voltage for a capacitor. In this lesson, we're going to do a little bit of mathematics to derive the final equation linking the voltage and the current in a capacitor. We have the symbol of a capacitor here, where I indicate the voltage and current in the usual way. We remember this equation here that says that the charge on the capacitor is equal to the capacitance multiplied by the voltage. So there is a direct relationship between charge and voltage. And we also know that the charge does not have a direct relationship with the current, but rather the charge is at a certain time in the capacitor is a representation of the values, an indication of the values that the current had in the past for the capacitor, because it is the leftover charge that was left in the capacitor due to certain profile of the current in the past. So in a way, the charge is sort of a memory effect that the capacitor has. We're now going to go and look at the equations that we know for the charge and the current, combine them together to get the final relationship between current and voltage for the capacitor. So we start with the usual equation here, Q equals C by V. And then the other equation here is the one representing the definition of the current. So the current is a delta Q over delta T, which means, again, you always have to imagine that you're sitting by and looking out to, you're the little person and looking at the section of the wire. And this section, you see a certain amount of charge moving down during a certain amount of time. You divide these two quantities, and what you get is the average current during that time. Now, what we're going to do is that we're going to take these two equations and combine them together. So in practice, what we do is that we take the current equation and we replace the Q in that equation with the definition of the Q provided by the first equation. So instead of having that the current is equal to delta Q over delta T, we have that the current is equal to delta C multiplied by V divided delta T. So we just replace the Q with C by V. At first order, the capacitance is a constant value. It's just as we said before, is a property of the geometry of the capacitor and the properties of the dielectric material. So it's not something that's going to change. So we can take it out of the delta operator, and we get that the current is equal to the capacitance multiplied by delta V over delta T, which is the variation of the voltage over a certain time. In order to get to the final mathematical definition, mathematical equation linking current and voltage for a capacitor, we need to go an extra further step and introduce the concept of derivative. What we want to change is that we don't really like the fact that we are expressing variation of quantities using the delta operator, the little triangle. So the delta operator is an indication of a macroscopic change of a variable, like a variable going from 1 to 2, like kind of a big change. So that is fine for a delta V or delta Q up here, but it's not really fine to be used for delta T. And I'm going to give you an example to explain you why. So let's say you have your charge as you're doing this experiment, being the little guy looking at the wire. You have a charge changing with the time, kind of like that, right? And now I ask you, okay, give me what is the current here. So this is the profile of the charge, right? So that means that every little instant of the time, that's the amount of charge that you see passing, right? So let's say I tell you, okay, give me the current, and you see the definition of the current is delta Q over delta T. So you get to pick your delta T. You can pick any value you want, and that is totally fine. What you'll get will be the average current during that period. So let's say you pick a period that is from 0 to this point. As you look at the charge, you're gonna add it up. So in the end, the value of the charge that you have, the delta Q that you have, it's gonna be pretty much represented by the area under this curve. And now, once you have the area, you're gonna do the ratio with the delta T and you get the current. So if you have to give me the graph of the current over time, now you only have one number for the whole period, and your representation will be sort of a kind of a straight line like this, because you can only give me the average of the current in the whole period, because eventually you come up with just one number, right? If instead of that time period, you choose something that is, let's say, the delta T is like 1/3, then the initial delta T. So this is the delta T that you pick in that equation. Well, then in that case, you will give me 3 numbers, because for each of the delta T, you have a different amount of charge. So you have 3 numbers for the current. So you're representing the current during that period with 3 points instead of 1. So it's natural to see how that will be a better representation of the current, right? So you will give me something like this for this part, something like this for the second period, and something like this for the third period. So this is a much better representation of the behavior of the current. You see where I'm going, right? The smallest the delta T you pick, the better is the representation of the current. So ideally, if you choose a delta T that is infinitesimally small, not exactly 0, but trending to 0, then you will get a representation of the current that is exactly the representation of the charge over time. Choosing something that trends to 0 might seem a little bit complicated, but all I'm saying is that you have to choose a value that is smaller than the minimum unit of measurements of the time that you use in your experiment. So for example, if you are considering an experiment where the minimum information you want to have is in the range of 1 second, then if you choose the delta T to be 1/10 of a second, that is small enough. It can be considered sort of like trending to 0, right? It's kind of like saying, well, I'm measuring the distance from here to another city, so I'm going to use kilometers. The millimeter in that case is pretty much a distance equal to 0, right? Because it's so small, it's so insignificant relative to the unit of measurement that you're using, right? So here is the same story. So mathematically, that is really a number that tends to 0. Really, mathematically, it's like the smallest possible number you can get. But practically speaking, all I'm saying is that you just want to pick this value to be small enough. If you do that, your equation still looks very, very similar. You just change the shape of the operator. So instead of having the operator with a little triangle, which is delta, you replace it with a d, with a lowercase d. And when you write dv over dt, this is called derivative. And if you check it out online, you will see that the derivative, in this case, dv on dt, is a representation of the slope of the voltage over time. So if you have a voltage that over time is being flat, there's no slope, so the derivative is gonna be equal to 0, which means the capacitor, the current of the capacitor will be 0. If you think this makes sense, because if the voltage isn't changing on the capacitor, that means no extra charge is being taken or added to the capacitor, so that means there is no current, right? So it makes sense. If you have the voltage that is increasing like this, then the derivative will be positive, meaning that the current is positive, you have damping charge in the capacitor. If you have the voltage that behaves like this, then the derivative will be positive and even higher value. And if the voltage is doing like this, then you have a negative value for the derivative, hence a negative value for the current, meaning that you're actually taking charge out of the capacitor. What we want to do now is the sort of the opposite exercise of what we've done before. Before we have taken the evolution of the current through a capacitor, and from that, using the hydraulic equivalent of the capacitor, we calculated the evolution of the charge in the capacitor as represented by the level of the water into a tank. And then because we knew that the charge and the voltage are directly related through the value of the capacitance, we got the value of the voltage at the end. Now we want to do the opposite. We start with the behavior of the voltage in the capacitor over time, the evolution of the voltage of the capacitor, and we want to derive the behavior of the current. Now this is more difficult than the other way around, because going from the current to the voltage, you can use the hydraulic example, which is quite intuitive. Whereas going from the voltage to the current, it's a little bit more complicated. You can still rely on the hydraulic example, but mostly I wanted to derive the equation linking the voltage and the current on the capacitor, and now we can use it much more easily to derive the behavior of the voltage. Now let's start with the exercise. So first of all, again, we start from a certain known value. This is a value that is representative of a charge accumulated in the capacitor up to that point from the beginning of time up to time equal to 0. We'll just take it as an input. And now we look at the behavior of the voltage to determining the behavior of the current. In the first period, we have 5 periods here. So maybe I'm just going to add the little numbers here. So it's 1, 2, 3, 4, and 5. So in the first period, the voltage is flat. So the voltage isn't changing. So as we've seen before, the derivative, the slope of the voltage would be 0 in this case. Hence, the current would be 0. Okay. And again, this makes sense. It means that the level of the water in the tank of the capacitor isn't changing, which must mean that there's no current going in and out. In the second case, in the second period, we have that the voltage is increasing. So it's increasing with a constant pace. So the derivative of that will be a positive number. So the current will be positive and constant because the slope is fixed. In the third period, we see that the voltage is decreasing, and you can tell it's decreasing faster than it was increasing before. So the derivative will be negative, and it will give us an absolute value bigger than the one we got in period 2. So that means that the current is going to be negative and with a bigger value there. The passage between period 3 and period 4 is a little bit tricky. As you can see, there is a little bit of a discontinuity. You see that the voltage is pretty much stepping from one value to another. If you stick to the mathematic, the derivative of that point is infinite, because you're going with an infinite speed from one point to another. So that means that the current in that point will be shooting up really high. Theoretically, this value will be equal to infinite. Before thinking too much about this, we'll revisit this later. Let's move on to the fourth and the fifth period, and then we'll talk about the consequences and the meaning of this infinite current. In the fourth period, again, the derivative of the voltage is positive and quite low, so it's almost flat. So that means that somehow the current goes down from the infinite, and now it will be flat and a pretty low value. And finally, in the fifth period, we have again the voltage that is flat, that is the derivative is equal to 0. So the current will be back to 0 again. Let's try to understand this peak of the current that we have derived from the equation. Well, there is two ways to explain that. So one is to just point to the equation. If the equation is correct, technically that point has to have a very, very high current. The equation isn't correct, so the current technically needs to be infinite. Now, let's try to give a more intuitive understanding there, and in order to do so, we can connect to the concept of energy. We remember that a capacitor is an energy storage device, and the energy that is stored by a capacitor, the fact that there is some energy stored, is indicated by the voltage. If you remember, the energy is actually connected to the square of the voltage. So if you change the voltage instantaneously, like this, that means that you're changing the energy instantaneously. Now, we also remember that power is an indication of the variation of the energy over time. So power is, if you want, delta U, if you use U for energy, over delta time. What we are saying is that we had a certain amount of energy change. So this delta U is quantifiable, is a certain number. But the delta T over which delta U happened was pretty much 0. So if you divide a number by 0, then you get P equal to infinite. So that means that in order to allow a change of the voltage so fast, you need an infinite amount of power. Power in the capacitor will be the current multiplied by the voltage, as we've seen before. And the voltage is going from one value to another. So this value could be any number. So it could be going from 1 volt to 2, for example, right? So in order to make the power infinite, because the power is the product of V per I multiplied by I, you'll have to have infinite current. And that is exactly what happens. So in a way, if you want to have an instantaneous change of energy, that is like just a fundamental physical things, you need an infinite amount of power. For a capacitor, that means an infinite amount of current. Capacitors in general are components that oppose to the change of voltage. That means that you can change the voltage across the capacitor, but in order to do that, you have to pay for it. And the way you pay for it is through current. So you want to change the voltage on the capacitor really fast? Very well. Be ready to provide an infinite amount of current. If you want to change the voltage on the capacitor slowly, then you'll have to pay in current, but the tax that you pay in this case will be lower. Like here, for example, we are changing the voltage slowly, so what I have to provide is a current that is just a normal value. I wanted to state the obvious here, because in order to change the voltage on the capacitor, like the way we've shown, instantaneously from one value to another, you need an infinite amount of current, and because an infinite amount of current is not available in any real system, the conclusion is that you can change the voltage on the capacitor infinitely fast. So you're always limited with a certain slope. Capacitors are indeed devices that oppose to the change of voltage, or better, the change of energy that they store. And that makes them ideal candidate in certain type of application that we're gonna see later in the course. In the previous lesson, we've seen that the relationship between the current and the voltage in a capacitor is the following. So the current is equal to C multiplied by the derivative of the voltage on the capacitor. This is bad news because this is a differential equation. So if you want to solve a circuit, even the simplest circuit with a capacitor, you have to solve a differential equation, which is not as simple as if you just had resistor. Here we're going to solve a very simple circuit. And the reality of the practical work, also of an engineer, that usually you don't end up solving your differential equations, but what you do is that you study, at least in school, very well, 2-3 typical scenarios. And then when you see a complicated circuit, you recognize which kind of category that circuit is, which scenario the circuit follow. And then you know what is the equation, the solution to the differential equation, and you just use it. So the solution will be 100% accurate. You'll not be doing any approximation, but simply you don't need to solve the differential equation every time. Other time, the circuit might be complicated to solve, so you are just going to do an approximation of the circuit. Consider the circuit behaves like these are the type of circuit, and then use the corresponding solution. And finally, if the circuit is really very complicated, you're just going to use a simulator. We're going to look at here the very classical circuit, which is the RC circuit. So this is a circuit where there is a capacitor and a resistor, and the capacitor gets charge or discharge through the resistor. So as you can see here, I'm already indicating, forget about the value of the current for now, but I'm already indicating that the capacitor starts with 0 voltage. Then we have a supply that is 10 volt that's going to be connected to it through a switch. And you know, probably your intuition already tell you that if you let enough time pass, at the end of the process, the capacitor will be charged to 10 volt. So we are charging the capacitor through a resistor R. So we actually add values of resistor and capacitor. We have a 1 kilo ohm for the resistor and 10 microfarad for a capacitor, so that we can solve the circuit with using actual numbers. As you can see, this is the first slide. We are considering the time, what's happening at time 0. And then as we go ahead, we'll move the time ahead step by step with small steps so that we can solve the circuit in each of these points. So this to avoid having to use the differential equation. Instead of using the differential equation, we will use some more basic relationship and things we know about a capacitor. And the first one you can see here is simply that we know that the current is equal to charge over time. So if you multiply the current by a certain time, you're going to get a certain delta charge. So at every time we look at the starting point of the circuit and we say, well, there is a certain current going through it for how long we are considering. And then we say, well, that means there is an additional extra charge in the capacitor. Now we know from the relationship of the capacitor with the charge and the voltage that if we have an extra charge in the capacitor, then we're going to have an extra voltage. And I want to highlight the extra voltage, meaning that whatever is the extra voltage that we calculate, this delta V, it's going to be added to the voltage of the capacitor to give us a new voltage that I'm going to call VC first. I'm using this little mathematical notation here first. Same story for the current. So once you have calculated the new value for the voltage of the capacitor, it's pretty simple to calculate what is the current going through the resistor by using the Kirchhoff law of voltage. If you know you know that you have 10 volts across the supply. Now you know what is the voltage across your capacitor, which is this new VC first. And it's very easy to see that the voltage of the resistor will be the difference between the voltage of the capacitor, the voltage of the battery and the capacitor. And of course, once you know that, you just divide by the value of the resistance and you get a current. The switch in this image I'm showing is open, but for every other case on in the circuit will be closed. So as a matter of fact, you can consider as the switch isn't even there. This might seem a little bit complicated, but don't worry, and we're going to go step by step every time. Alright, let's start looking at this circuit. At time, let's look for now at the time t equal to 0. Until the switch is open, the current has to be 0, right? There cannot be any current. And for the voltage of the capacitor, by just an arbitrary choice, let's assume the voltage of the capacitor is 0 at the beginning. So voltage of the capacitor is 0. Let's see what happens at time 0 plus. Sometimes people indicate 0 plus, meaning that it's basically 0, but just like 1, nanosecond after it. And the difference between time 0 and time 0 plus is that the switch is closed. So the moment in which the switch is closed, we know already from before that the value of the current of the voltage in the capacitor cannot change instantaneously, because in order to do so, you will have to have infinite amount of current, because the voltage on the capacitor represents energy, so you'll have to have infinite power to make it change the step function. So if the time that pass from 0 and 0 plus is really short, we can say that the voltage across the capacitor is probably still about 0. Maybe it's not exactly 0, maybe it's like 0.00001 volt, but as a matter of fact, as far as we're concerned, it's 0 volt. So now that allows us to calculate the current in the resistor. So we know that the voltage here is 10. We know that the voltage in the capacitor is 0. If you consider the voltage on the resistor like this, it's very simple to see that the voltage falling on the resistor in this case is 0 volt. You can very simply calculate it doing the Kirchhoff law of the voltage. And in this case, if you have 10 volts, then you divide it by 1 kilo. It's very simple to see that the initial value of the current as soon as the switch is closed is 10 milliamp. So the first point, we solve the first point of the circuit as the time 0 plus, which is voltage of the capacitor is 0, and current in the resistor is 10 milliamp. Let's continue the analysis of the circuit, and let's see what happens when we get to the time 5 milliseconds. Now here everything is already solved, but I'm going to guide you through it. So before we said that the current was equal to 10 milliamp at time 0. Now we simply go through this equation one by one, because as you can see, the result of this equation is to give us the new value for the voltage and the current. The first says that the delta charge is equal to, so the additional charge in the capacitor will be equal to the current multiplied by the time. If you substitute here and you take 10 milliamp, and this one is 5 milliseconds, because we went from 0 to 5 milliseconds, the results that you get is 50 microcoulomb. Now you take 50 microcoulomb and you divide by the value of the capacitance, which is 10 microfarad, and you get 5 volt. So 5 volt is the difference, the additional voltage in the capacitor. The capacitor has 0 volt at first, so now we're adding 5, so the new value of the voltage of the capacitor is 5 volts. And finally, we use the same equation as before. The current in the resistor will be equal to 10 minus, this time this is 5, divided by 1K, this is 1K, so you get 5 milliamp. So now what we are doing is that we have this here is where the 5 millisecond would be, and what we're doing is that we're indicating that the voltage went from 0 to 5 volt, and the current went from 10 milliamp to 5 milliamp, so it decreased. Of course, the switch is almost closed here, don't get fooled, even though I showed it open, but it's closed. From now on, it will always be closed. Obviously, we don't know what happens, for example, at 3 milliseconds. We just didn't look at that point. So we just went straight from 0 to 5. So I've chosen this time step so that we can see what is the behavior of the voltage and the current. But of course, it's easy to imagine that probably the behavior of the voltage and the current wasn't to go straight, like with a straight line from one point to another. It will be slightly different. We'll see that at the end. But for now, because we don't know anything about what happened between 0 and 5, we only have the point at 0 and the point at 5, we just connect them with straight lines. Now let's look at 10 milliseconds. So same story as before. Remember that the previous value for the current was 5 milliamp. So now we put 5 milliamp here. The time now, it's again actually 5 milliseconds. So the delta time is always the same. But now 5 by 5 is 25. So we have 25 microcoulomb. So you see, same step in the time domain. So we went 5 milliseconds long. But this time, the amount of charge that was dumped in the capacitor is actually half the amount of charge we had before. So with 25 microcoulomb, the delta voltage is 2.5 volts now. Now the new voltage of the capacitor is 5 plus 2.5, so 7.5 volts. And finally, the current going in the resistor, hence going in the capacitor, is 10 minus 7.5 divided, so that gave us 2.5 volts, divided by 1K is 2.5 milliamp. So again, as we've done before, at the 10 millisecond mark, we just indicate the voltage. So it looks like the voltage keeps increasing, probably towards 10 volts, as we'll see, and the current keeps decreasing. So it was 10, and then it's 5, and now it's 2.5. It's actually halving every time in this case. T equal to 15 milliseconds, so we keep going ahead, 5 milliseconds every time. Same, works before, so we had the current was equal to 2.5 milliamp in this case. We still multiply by 5, so now we get 12.5 microcoulomb. That means the voltage, the additional voltage in the capacitor is 1.25, and now we are summing 7.5 plus 1.25, and we get 8.75. And finally, the voltage across the resistor now is 1.25 volts, and divided by 1 kilo, it gives us 1.25 milliamps. So we keep drawing, we keep connecting with straight line. This is the mark for the 15 millisecond, and we get the voltage again keeps going up toward 10 volts, and the current keeps decreasing. And you can notice that although again we are simplifying things, we're just looking at a few discrete points in the time domain, you can tell that the slope, the speed at which the voltage increase and the current decrease is slowly and slowly decreasing. We could keep going ahead, try to solve this circuit step by step, and for example go ahead and look at 20 milliseconds. But I think you got the gist of it, so it's not hard to unveil what are the actual mathematical solutions of the circuit. And here they are. These two equations are the solution for the voltage and the current over time for this very simple circuit. As you can see, they are exponential, and exponential equations are usually the type of solution that you get when you have a capacitor and a resistor in your circuit. So it's really important to understand how they work. They might look a little bit intimidating, but actually they always have the same appearance, and it's kind of easy to understand which one it is and how to determine the different parameters. We won't go into detail into this lesson, but I want to give you a high-level understanding. Before proceeding further, I just want to give you a little refresher on exponential functions, because exponential functions are everywhere in electronics, in particular in solution of RC circuits. So this graph that I took from the Wikipedia page that I encourage you to use to get more knowledge and more to refresh your exponential functions. So let's say this is x and this is y. This graph is representing y is equal to e to the power of x. So now I want to highlight few characteristics of this function. So the first is that when x is equal to minus infinite, so we're going all the way down here, you can tell that y is going to be equal to 0. When x is equal to plus infinite, y is going to be equal to infinite. And then, very important, when x is equal to 0, y is equal to 1. Key I want to remind is a Euler constant, and it's equal to about 2.72. Another thing that is very important is that this function never really reaches zero here, so it keeps approaching zero, getting closer and closer and closer, but it will only get zero really if you go to minus infinite. But anyway, it soon becomes very close to zero. And then the other thing you can note is that this function, after you move a little bit in the x-axis, it starts growing really fast. So that's another really, really important thing. Sometimes in the study of circuits, you will find, as we are actually already found in our case, a case where you have another function, and this function is going to be equal to y is equal to e to the minus x. Because x is basically the horizontal axis here, you just replace x with minus x. So it's equivalent if you want to take the horizontal axis and flip it vertically. So what's going to happen in this case is that the function will actually look like this. So it will be pretty much symmetric relative to 0, to x equal to 0. And that makes sense, because if you think about it, now if you have x equals to infinite, it's equivalent to when you had minus infinite before. So you're going to get 0. When you have x equals to minus infinite, now it's equivalent to have e to the infinite. So you get plus infinite. And again, when x equal to 0, it doesn't make a difference. You always get 1. Now let's go ahead and study the solution here. So as we said, these one are the two solutions for voltage and the current in a capacitor. Those are the mathematical solution to this circuit. So they are perfectly exact. Let's look at the current one because it's slightly simpler, I would say. So this one, we see we have an exponential multiplied by a constant. So let's look at the constant first. So the constant is V bar, which is just a fancy name for the 10 volts of the supply. So it's the voltage of the battery. So it's 10 volt. Divided by the value of the resistor, 1 kilo. So this quantity in the parentheses is equal to 10 milliamp. So if you remember from the previous calculation, 10 milliamp is exactly the value that the current has at the beginning, at t equal to 0. So this point was 10 milliamp. This quantity is then multiplied by an exponential. So an exponential, we have just seen it before. We see that exponential is a type of exponential that is a negative horizontal axis, like in the exponent. The t is with a minus sign instead of a plus sign. So as you remember from before, the curve will tend to do something like this, where x equal to 0, we get 1. If this is x, in our case we have t, we don't have x, but exactly it's the same function, so it works exactly the same way. So you can see that for t equal to 0, the exponential function will be equal to 1. So it gets exactly this point here, exactly has a druid here, and it's also the same as the point that we found manually. And then, as you recall, as the time progresses toward infinite, the value of the exponent will slowly decrease, eventually approaching 0. So you can see that's exactly what we are doing with this function. So the quantity is decreasing. It's approaching 0. It never really fully reaches 0, but it becomes very, very close pretty quickly. Before moving on to the study of the voltage of the capacitor, let's study a little bit more the evolution of the current of the capacitor, because I wanted to introduce another important parameter, which is the time constant. By now, you should be familiar with the shape of exponential functions, and it should be easy to understand by studying the circuit what is the initial value of the current and what is the final value of the current. In order to draw exponential function correctly, you need to know 3 important parameters. So the first is the initial value of the exponential. The second is the final value. And the third is the time constant. The first point, the initial value, is easy to calculate, and usually it can be calculated by studying the circuit. In this case, if you remember, the battery is 10 volts. The initial value of the voltage on the capacitor is 0. So the moment in which you close the switch, the drop across the resistor will be 10 volts. Hence, we have a current here that is 10 milliamp. So that's the initial value of the current, easy to calculate. The final value is also easy because the capacitor if the voltage is not alternating voltage, but it's just a constant voltage. After you close the switch, there will be a certain time for things to settle, but eventually the current has to be 0 in a capacitor. So we know that we are heading towards 0. So this is our point number 1, and this is point number 2. The question is now, what is the time constant, and how do I calculate it? Well, the time constant is really important for exponential because it gives you an idea of the speed at which the exponential evolves. If you only have point 1 and point 2 and you have to draw an exponential, you are in trouble because there are infinite exponentials that you could represent. For example, here, an exponential that works with the initial value and the final value here could also look like this, or it could also look like this. So you could have a faster version or a slower version of the same exponential, and all of them will start at 10 milliamp and will trend towards 0 milliamp. So it's really important to know what is the speed of the exponential in order to draw the correct one, because there's really only one exponential that is the correct one. The time constant, fortunately, is easy to find. When you look at the equation of your exponential, you will always have the independent variable at exponent. That's what defines an exponential function. But usually you will also have some other numbers in it. Now this number could be multiplied to the independent variable, so it could be multiplying the t, or it could be a denominator, it doesn't matter. You can always take the exponential function and write it in a way that looks like this, where in the exponent you have a numerator, the independent variable, which is the time, and in the numerator you have a number. In this case, I use the Greek letter tau to represent the number. For example, if you have e to the minus t, that means tau is equal to 1. If you have e to the minus 2t, that simply means that tau is equal to 0.5. So you can always transform the exponential function to look like something like this. If you do that, whatever you collect the denominator, this is called time constant, and it is usually indicated with the Greek letter tau. Time constants are so called because the unit of measurement of the time constant is the unit of time, so it's second. In the case of this circuit, the time constant is equal to R multiplied by C. So if you multiply a resistance by a capacitance, you get ohm multiplied by farad, but that is also equivalent to seconds. For RC circuits, the time constant is always given by the product of an equivalent capacitance and an equivalent resistance. In this case, we only have two components, so the time constant could have only been R multiplied by C. How do you use the time constant to draw your exact exponential? Very simple. Here's what you do. So you already individuated in the graph your starting point and your ending point, the final value. So what you do is that you draw a line parallel to the time axis that reaches your final point. Like in this case, the final point is 0, so this line is basically overlapping with the time axis, but it doesn't have to be that case, it could be somewhere else, the final value. Now, from time 0, or for whatever was the time of your initial value, in our case is 0, you move along that line by the amount equal to the time constant. So in this case, we went from 0 to 10 milliseconds because 10 milliseconds is the time constant. So all you're doing that to find this point. Now you draw a line that connects your initial value to this point, and you basically individuate a triangle here. Now that you had the initial value, the final value, and you have this triangle here, it's very easy to draw the correct exponential. Actually, let me cancel this one so I can show you exactly how to do it. You obviously start at the initial value, no surprise here. And you know that eventually you're going to trend to the final value. So now all you have to do is to determine the speed at which the exponential moves. And that's where the triangle comes into play. As you start drawing your exponential from the starting point, you have to make sure that the initial part of the exponential is tangent to the triangle. Once you do that, it will be very natural to draw the rest of the exponential in the correct way. So you start, and you make sure that the two lines are tangent at the beginning, and then at some point, you disconnect from the triangle, and you just trend towards the final value. In most cases, when you apply a step voltage, like in this case, or a step current to an RC circuit, the circuit will respond with exponential waveforms. Drawing the exponential waveform of the current of the voltage does not require you to know the actual equations, but the only thing you need to know is the starting value of the voltage or current, the final value, and the time constant. Let's now move on to the voltage waveform represented by this equation. Again, to be able to draw or to recognize that the waveform is correct, we just have to individuate the three main points of the exponential curve, which is the starting point, the ending point, and the time constant. Let's start analyzing the waveform to see if we represent correctly the behavior of the voltage of the capacitor in the circuit. The starting point for the voltage was given by the problem itself, and that is something that you always need for a capacitor. It is usually a safe bet to assume 0 volts if the circuit has been sitting there without supply for a long time, but you cannot really tell for sure. So this was V equal to 0, and this was coming from the problem. So the first point was easy to find. The final point, it's also easy to find for capacitor. And again, if you have a circuit where your supply is just a constant, like a battery, the switch is not continuously operating, open and close, but once it's closed, for example, it stays closed forever, and the components aren't changing value dynamically. So the circuit is just constant and let be, and you're just waiting for the voltages and current to settle. For a capacitor, you can always say that the current eventually, like after a very long time, got to be 0. And the voltage across the capacitor, it's also easy to find because once you know that the current is 0 in the circuit, you can easily apply the Kirchhoff law for the voltage and determine the voltage of the capacitor. For example, again, if you assume the current is 0, that also means the drop across the resistor here will be 0 because there's no current. And now, if you apply the Kirchhoff law, you will very easily determine that the voltage across the capacitor will have to be equal to 10 volts because no other drop is lost across the resistor or the switch. So that confirms that the final value here should indeed be 10 volts. And the time constant is, for this capacitor, will always be the same. Doesn't matter if it's if you're talking about the current or if you're talking about the voltage, the time constant is the same. So it will be again RC. So just as before, what you would do is that you draw a line representing the arrival point, which is 10 volts, and you extend the line back to the beginning point. And then you, from the starting point, you measure a distance, which is the tau. So this is the tau. Then you draw a line here. And then you make sure that your exponential at the beginning, when it leaves the starting point, it's tangent. And that's how you get the waveform for the voltage. As you can see, we actually determined the behavior of the voltage without looking at the equation. Now we can go back and verify that the equation is indeed presenting that curve. Let me delete a little bit of the curves here. So now, if we look at the equation, what we can see is that we have a constant term at first. So the constant term is equal to V bat. So this one is 10 volts. And then, instead of multiplied by an exponential, we have 1 minus an exponential. So that is always one of the two cases that you can encounter. So usually, when you have a behavior, which is like the one of the current, so you start from a certain value, and then you slowly trend exponentially to 0, then you're simply multiplying a constant by an exponential, a pure exponential. Whereas when you have the other possible behavior, which is you are trending up towards a certain value exponentially, similarly at the same speed at which you tend to 0, but you're just tending to 10 volts in this case. So usually the equation has that form. So you have the final value at which you tend, and then it's multiplied by 1 minus the exponential. And it's easy to verify that this works because when you substitute t equal to 0, then the exponential will be equal to 1. So 1 minus 1, 0. So the VC is equal to 0, which is exactly what we want. And then you can verify that when t is equal to infinite, the exponent of the exponential function will be minus infinite, so the value of this will become 0. So only the 1 will be left. So 1 multiplied by V bar is still V bar. So Vc is equal to 10 volt. So you see that it's correct, and infinite becomes 10 volt. The last thing that we have to verify is that the exponential is indeed using the right time constant, which is tau, which is Rc, which in this case is the only possible time constant that we have in this circuit. In the previous lesson, we have seen how to determine the main parameter of an exponential function representing the voltage and the current across a capacitor. As we've seen before, this waveform usually start at a certain point, and then they slowly tend to kind of their final destination here, which is in this case 10 volts and 0 current. Now it's worth to highlight that mathematically those destination points are never really reached unless you really wait an infinite amount of time. So if you look at the mathematics, unless t becomes infinite, the value of the voltage will never be really 10 volts. In practical terms, you don't need to wait infinite, because after a very short time, your voltage will actually be indistinguishable from 10 volts. So yes, technically it hasn't reached 10 volts yet, but there's no instruments on earth that will be able to tell you that you haven't reached 10 volts yet. To have an indication though of how fast the exponential waveform moves, that information is provided to you by the time constant. If you take two exponential waveforms and they have exactly the same starting point and ending point but different time constant, they will look very different. So this curve that we can call curve A has an equation represented by 10 milliamp multiplied by E minus t2 over 10 millisecond, right? So let's say now we represent another curve, a curve B. This curve B will also start at 10 milliamp, will end at 0, but now the time constant is 5 milliseconds, which means that either the resistor or the capacitor are smaller now. So in this case, if I go ahead and draw the waveform, I will have to do something like this. So again, I start at 0 time, and I move 0 is also the destination for the current. So I find 5 milliseconds here. I draw a kind of a straight line, and then I know that my exponential will be tangent at first, at least. So it will be something like this. So as you can see, this current will go towards 0 faster, and probably I didn't really do it really well here. It's probably more like this. Now I can remove this. And now if I wanted to draw another one that has 1 millisecond, then it will be even faster, because the line will be here. So it will be like that. So it will be much, much faster, and so on. Same concept if I pick a time constant that is long. So the time constant in effect gives you an idea of how fast the exponential function moves. Up here on the top right, I have a table that gives you a better idea of that. In this case, we are looking at the voltage than the current, but it's the same concept. So the time constant gives you an idea of how fast the exponential function moves, and you can actually calculate after each of time constant how much percentage of the final value your voltage or current has reached. So in this case, with this little table, if we look at the voltage at time 0, Vc is 0, that was a starting point. So we have a 0% of Vc over V bar, knowing that the final value for Vc will be 10 volts, which is V bar. So initially we are 0%. After one time constant, so that means at 10 milliseconds, we are at 63%. So one time constant is a very important time, because after one time constant, yes, we're still a long way to be exactly equal to the final value, but we're already 63% there. After two time constant, we are 87% there. And after three time constant, we are 95% there. So usually, like a rule of thumb for like a circuit designer, is that when you have an RC type of behavior, you know voltage and current are evolving and exponential, it will take some time. You calculate the time constant, and then it is a fair assumption usually to assume that after three time constants, your voltage and current are pretty much at their final destination, meaning they are at their final values, meaning that they are like at 10 volts or 0 amp in this case. If you want it to be more accurate, you can even go more. You can use a 4 time constant, and of course the more you add time constant, the closer and closer and closer you get to the final value. But as we've seen before, and as you can tell from the graph, the speed at which you move, the amount of percentage points that you gain for each additional time constant becomes smaller and smaller because you're approaching 100%. So you see with the 1 time constant, you get 63% already. The second time constant already doesn't give you as much, but it gives you much less. It only brings you from 63 to 87. And then the third time constant only brings you from 87 to 95, and so on. And the next time constant can only give you up to 5% because you already have 5% and 95%. So usually, a rule of thumb that I use is to assume that after 3 time constant, the voltage and the currents on the capacitor are pretty much at their final value. In this circuit, the time constant is equal to RC. So it makes sense that it depends on both resistor and capacitor. After all, this circuit is really very simple, and these two are the only 2 components we have. But I want to give you an understanding, intuitive feeling of why the product of those makes sense, rather than, let's say, the ratio or the difference or even just one of them. You can always represent RC circuit with a hydraulic example where the resistor is a constriction in the tube, and the capacitor is a tank, and the voltage in the capacitor is represented by the level of the water that you have inside. The current is the flow of the water into the capacitor, and then the voltage is also like the difference of pressure across the resistor. So this is the resistor and this is the capacitor. So now if you make the resistor twice as big, we know that for the same difference in pressure, so we have a P1 and P2, which for us will represent a voltage 1 and a voltage 2, where voltage 2 is the voltage of the capacitor. So for a certain difference of voltage, which is difference of pressure in this hydraulic example, if you make the resistor twice as big, you're going to have a flow of water, which is a current, that is twice as small. So makes sense that the tau is proportionally dependent on R, and the bigger is the R, the bigger is the tau, the slower the voltage will reach the final value. And at the same time, for the same resistance, so the same size of the tubes, of the pipes, if you have a bigger capacitor, so if the capacitor, let's say this tank, instead of being like this, is much wider, then in this case, for the same flow of water that comes into the capacitor, the level of the water will grow much slower because now we have a bigger capacitor to fill, a bigger tank. So it also makes sense that the time constant is directly proportional to the capacitance for this reason. In the previous lessons, we have seen the charge of a capacitor from 0 volt to 10 volts through a resistor. Now we're going to look at what happens when the capacitor gets discharged, and we'll find out that the equations, the behavior is very similar, just slightly different. So we look at this circuit. We have a capacitor here with a certain starting voltage that we're going to set to 10 volts. So we assume this is a capacitor that's been charged at 10 volts somehow. And then we have a switch. Again, the switch is just used to determine a starting point for the discharge. And then we have a resistor of 1 kilo. Again, the capacitor is also 10 micro, just as before. Before, of course, yeah, we already have the solution actually, but even before we can look at them, you should immediately be able to tell a few things. So first of all, you'll be able to tell that whatever the voltage in the current will do, the way, the movement, the shape of the waveform will be exponential. Then you should be able to calculate immediately the starting point for the voltage and the current. Well, the voltage has been given, it has to be given, and the current is also very easy to calculate because the moment the switch is closed, you're gonna basically apply these 10 volts across this resistor. So you have 10 milliamp, so the starting point for both current and voltage is defined. It's also easy to determine what is the final value for the voltage and the current. We know that the current has to be 0. So that's 1, that's easy. And then it's very easy to find out that if the current is indeed 0 at the end, the voltage across the resistor will be 0, and the resistor happens to be in parallel to the capacitor, so that is also the voltage of the capacitor. So both the capacitor and the resistor will be 0 volt at the end. So there we go. Finally, the only thing you really need is the time constant. This is a very, very simple circuit. You only have a capacitor and a resistor. So the time constant is again equal to R multiplied by C. And there you have it. So the two equations, the two waveform will look like this. Now here, the two starting points, I'm representing the voltage and the current on the same graph just for convenience, which means that you have to imagine that the vertical axis, it's not unique, but you have two of them, one for the voltage, one for the current. So that's why these two waveforms don't overlap in this way. That is completely arbitrary. But for both of them, as you can see, I draw the little line here connected to the time constant, and then I use that to help me draw the exponential. And up here, I also indicated the formula that gives you the behavior of the voltage and the current. This time, because in both cases we're going from a value to 0, they both look the same. So you don't have the term that is 1 minus the exponential over tau, but you only have the exponential part. Just as we did for resistors, we now want to talk about capacitor in series and in parallel, and we want to be able to calculate the equivalent series and parallel capacitance. Now let's start with capacitor in series. So we see here we have a capacitor. So I want to remind you that Q is equal to C multiplied by V, which means the capacitance is that property that defines how much charge is accumulated on the plates of the device for a given voltage. And we're going to use this relationship at our advantage to understand how we calculate the equivalent series capacitor. To make it even extra simple, as you can see here, I indicated the charge with little plus and minus sign. And usually this is just an indication of the fact that you have positive charge on the top plates and negative charge on the bottom plate. But in this case, we'll consider that as also an indication of the amount of charge. So in this case, we can say that we have 4 plus sign and 4 minus signs. And that is kind of an indication of the amount of charge on the plate of the capacitor. Let's now look at the circuit in the middle. So we have two capacitors in series. And these two capacitors in series, you can tell that it is because they will be crossed by the same current, if there was one. And you can also notice that each of these two capacitors are identical to the original capacitor on the left, meaning that they both have a capacitance value equal to C. And for this reason, when there is a voltage V across them, you have a certain amount of charge Q. One thing it's really important to remember, and the peculiar thing that happens in the middle, it's kind of the important concept here. So here, you see there are some negative charges, 4 negative charges and 4 positive charges on two different plates, but these plates now are connected electrically by a wire. So there's actually a path for these charges to see each other, to reach each other. And as we certainly know, positive and negative charges attract each other. So these charges will eventually just recombine. Also remember, when we indicate minus and plus charges, we really mean, with minus charging, we mean we have an excess of electrons, whereas with plus charges, we just mean that we have a defect of electrons, so we have less electrons. So overall, if you consider this piece of metal with this shape, so it's shaped like an eye, but eventually this is like just one piece of metal, you can consider that this piece of metal is electrically neutral because it has the same amount of positive and negative charges. So now, if you think about it in this term, that means that effectively, if we now want to jump to the right here and try to find the equivalent capacitor, effectively, we have that these two devices in series, they are equivalent to one capacitor, which has a voltage equal to 2V across it, because you see we have one V and another V, so it's equivalent to 2 times the voltage. But the effective charge that is stored is only 4 plus sign and 4 minus signs, because the one in the middle got simplified away. So at the end of the day, if you look at if you want to calculate the equivalent series capacitor, for this case, the equivalent series capacitor would be equal to C divided by 2. So actually, when you put two capacitors in series, the effective equivalent capacitor is smaller than the initial capacitance. And we understood that by doing this, by looking at this simple example where the charges in the middle plates, and the plates they get connected to each other, get simplified away. So for a higher voltage now, you actually store a smaller amount of charge. So the equivalent capacitance becomes smaller. So if we want to extend the concept, again, because the example we were seeing before just assumed two capacitors in series and they have the same value, but that obviously it's not always the case. And now in these slides, I'm showing what is the universal formula that you can use to calculate the series equivalent for a capacitor. And you will certainly remember that this formula is very similar to the one for the parallel resistor. So the equivalent series capacitor is equal to the inverse of the sum of the inverse of each individual capacitor that is in series. So in generally speaking, the series capacitor of and capacitor is always smaller than the smallest of the capacitors that you put in series. Calculating the equivalent parallel capacitance of two capacitors in parallel, it's even easier than the series one. So now we look at the left here, we have two capacitors identical in parallel. You can tell that they're in parallel because the two terminals are shorted with each other and because they will be subject by the same voltage. And these capacitors are the same as we've seen before, so they have for a voltage V across their terminal, they store a value of charge equal to Q. And we are representing this Q with 4 plus sign and 4 minus sign. If you just want to represent this with one capacitor, that is very simple and intuitive. All you have to do is that will be a device with a voltage across it equal to V because they are in parallel. But now this device, because you have the top plates and the bottom plate shorted together, you effectively can consider that as a single capacitor where the amount of charge that is stored is twice as much as before. So you have 8 plus sign and 8 minus sign. So in this case, the equivalent parallel capacitor will be equal to 2 times C. In this slide, I'm just showing the more general formula that you need to use to calculate the parallel capacitance in case you have many capacitor, potentially a number of capacitor in parallel, and with different values. So the formula is here. It's very simple. The equivalent parallel capacitance is the sum of all the capacitances of all the capacitor. If you remember, this is the same. This formula is the same. It's very similar to the one used for the series of a resistor. So the resistor and capacitor. Very useful thing to remember. The formula that you need to use to calculate the equivalent parallel in series are the opposite. So when the resistors are in series, you need to sum them, while with the capacitors, you sum them when they are in parallel. Whereas when the resistors are in parallel, you have to use that more complicated formula where you have the inverse of the resistor that are summed together, and then you do the inverse of that. And the same strange formula applies for capacitor when they are in series. In this lesson, I want to introduce different types of capacitors. We're going to discuss the main factor that needs to be considered, and we'll compare different capacitors between each other. The goal of the lesson is to allow you to recognize capacitors when you see them on a board and to understand kind of the main characteristics. There are many factors that need to be considered. We are just going to discuss the most important ones at this point. The first most important factor is the capacitance. Naturally, that's the reason why we have a capacitor in the first place. The second one is the size, geometrical dimension, and volume. This is important because you might not have a lot of space available on the board, like if you're designing a phone, for example. The third is the max voltage / the rating. So the max voltage simply indicates what is the maximum voltage at which you can use your capacitor, beyond which you will destroy it. So it's important to know. The rating is a word that is tossed around quite a bit, and what it indicates is that while the capacitor might have a nominal capacitance value, the capacitance is not a constant, but changes depending on the voltage applied or the temperature. So different type of capacitor, in particular the cheapest one, will have a capacitance that is not constant across voltage and temperature. So you have to know that when you design your circuit so that you take that into consideration. The bullet 4 is the equivalency resistance. So as you certainly imagine, every wire has a certain resistance. So you don't need to have an actual resistor to have a resistance into a circuit. So even the simple terminals of a capacitor will have a certain resistance. So when you add a component to a capacitor to a board, you're not just adding a capacitance to that point, But if you really want to draw the equivalent circuit of that capacitor, it will most likely look like something like this, a resistance in series to a capacitance. The resistance is obviously an undesired effect because it results in dissipated power, and in general it diminishes the performance of the component. The fifth bullet is the tolerance. This is a straightforward one. So the capacitance is defined as a nominal value, but it's not perfectly defined. It will have a certain uncertainty. That's usually determined as provided as a percentage. So when you buy a component, it might be, I don't know, 10 microfarad, and it's plus minus 20%. So the actual value of the component could be anywhere within plus minus 20% of the nominal value. Finally is the frequency response. We're not going to talk about that now. Frequency response simply is a manifestation of the fact that the component is not represented just by a capacitance, but is represented by a capacitance, a resistance, and also an inductance. So when you see what is the behavior for different speed of the signal applied to it, for different voltages and currents, it will behave much different whether you apply a slow moving current or voltage compared to a fast moving current and voltage. But we are not going to talk about this at this point. There are many types of capacitors available on the market. If you just Google capacitor on Wikipedia, you will find materials for hours. I just want to briefly discuss three main families and the main characteristics. The first is the multi-layer ceramic capacitor, also called MLCCs. These are very, very widely used type of capacitors, probably the most used type. So their main advantage is the small size. If you look at the smallest size of MLCC available, this could be really, really, really tiny. Only a machine can really solder them well. The smallest size could be like a 1/4 millimeter by an 1/8 millimeter. So really, really tiny. They also have low ESR, which is also a good advantage. Being the size so small, they can keep the ESR small as well. The disadvantages are obviously with the small volume of the capacitor, you have a small capacitance as well. And the other big disadvantage is that they have a high voltage and temperature dependency of the capacitance. So that means that depending on the voltage that you apply, the capacitance might decrease. So they have a certain nominal capacitance at 0 voltage, at 0 bias, but then as you apply a higher voltage, the capacitance decreases a little bit. So you have to keep that into consideration. Finally, these are also the cheapest capacitors. So it's not a surprise that the capacitance, which is sort of the main features of a capacitor, isn't very well controlled and changes with temperature and voltage and such, because at the end of the day, you have a small and cheap component, so you have to pay the price somewhere else. Second type is a film capacitor. So they also have low ESR. The main advantage compared with the MLCC is that they have instead a low voltage and temperature dependency of the capacitance. So the capacitance is pretty stable. They also give you small capacitance, but they have a larger size, and usually they're also more expensive. Electrolytic capacitor is another widely used type of capacitor. The main reason to go with electrolytic capacitor is the much larger capacitance values available. They also have low voltage and temperature variation of the capacitance, which is also good. The disadvantages are the high ESR. And given the size and given that the internal structure is pretty complicated, the ESR is quite high, and the size is large, it's pretty large. It's very likely that this will be the biggest component in your circuit. And finally, the most important thing that you have to keep in mind, I don't want to call it disadvantage, just you have to use it correctly, is the fact that these components are polarized, which means that their orientation is not arbitrary. There is a negative terminal and a positive terminal, and you have to make sure that the voltage is always oriented in that direction, otherwise you will break the component. You can see from the picture that usually the negative terminal is the one that is indicated like this. You see the negative terminal, or this little dot, or this little band. So you always have to make sure to use them with the right orientation. Besides that, is the components that gives you the highest value for capacitance. Usually, your circuit that you're going to design is going to use a mix of different type of capacitor, because each of these will have a different application where they're best compared to the others. So, and most likely your circuit will almost always contain a mix of electrolytic capacitors and multi-layer ceramic capacitors. One of the most important applications for capacitors, in particular in modern digital electronics, is to be an energy storage for integrated circuits. One capacitor used in this application for this role, they're usually referred to as decoupling capacitor. They're also sometimes referred as bypass capacitors. And what they do is pretty much to store energy, like any other capacitor, and then release it when the chip's needed. We'll see later why this is required. And pretty much the overall behavior of bypass or decoupling capacitor is that they behave like a local and faster power supply for the integrated circuits. Finally, capacitors can also be used to filter high frequency noise. On the right, I represented a simple circuit as an example to study the role of bypass capacitors. Here we have an integrated circuit, IC, usually present themselves in boards as a little black boxes with many pins. So in this case, I imagine that this IC has two pins dedicated as inputs, signal, and one pin dedicated as an output. So we don't know exactly what this IC does. It's not important for this explanation. You can imagine that maybe it takes input 1 and input 2, sum them, and provide the output at the output pin. Other two pins that you're going to find on any integrated circuits are the ground and the power supply. So these are the two pins that you have to use to connect the chip to a power supply source to a certain voltage. And these are obviously required in order for the chip to work. Without a power supply, the chip won't be able to work. Now, ground is usually indicated with G and D, so it's pretty self-explanatory. While the supply, it's usually called VDD, it could also be called VCC. Very often the case that more than one pin is dedicated for ground and for VDD. These two pins are obviously going to be connected to a battery eventually, which is always what we imagine as the power source for the circuit. So the battery is here. And with this two little symbol, I wanted to indicate that the battery is not necessarily sitting next to the chip. It might be really far, it might be quite a big board, and the battery might be located on the other side of the board. So there might be quite a distance, and the trace that connect the battery to the chip might be pretty long. Just by looking at this little circuit, I can tell you almost immediately that this circuit will never work. Even if I don't know what is the IC doing, even if I don't know what kind of IC it is, I can already tell you that this circuit has a very high chance of not working. The reason for it is that it doesn't have any bypass or decoupling capacitor. If you take any data sheet of any IC, whether the IC is analog, whether it's digital, you will almost always find a request for a bypass capacitor. So a bypass capacitor will be represented in this schematic like this. So a capacitor between the power supply and the ground. Usually, the datasheet will also tell you that this capacitor not only has to be connected like this, but it should also be located as close as possible to the pin of the integrated circuit. So sometimes these VDD and ground pins are located very close to each other in the symbol of the schematic, so that you can clearly show that the capacitor is going to be next to it. Sometimes you don't indicate the capacitor like this, connecting it between the two sides, but you might write something like this. You might just do like this. So you have a capacitor and then you indicate that it's connected to ground, but this way it's kind of obvious that this capacitor is really sort of belong to this component. It's really next to it. In order to understand how this circuit works, let's start describing the role of each of the actors. So the first is the voltage generator or the battery. As we know, this is, as the name implies, generating a certain voltage. It could be 3.3 volts, for example. And apparently, because of the way we connected the circuit, this is the voltage that is required by the chip. Different chips require different voltages. Another thing that should be intuitive is the chip. The integrated circuit contains other little circuit inside. They're fabricated in a different way than normal other components, but nonetheless, you're going to have resistors inside, capacitors, and so on. So, in order to execute this function and to do whatever it's supposed to do, it's going to require a certain current as well. So, as the chip is working, not only it will see a certain voltage at its terminal, so from here to there, you're going to have exactly the same voltage V. It's also going to require a certain current in order to operate. And the same current will come in the supply, it will come out of the ground, and then it will return to the battery. In order for you to understand why bypass capacitors are needed, I need to tell you a little bit more about the waveform of the current going in and out of an integrated circuit. Now you might be thinking that the current will probably look like something like this, a constant current over time. Why not? After all, integrated circuits do like constant voltage over time. So it seems natural that they might also like to have a constant current as well. Well, in most of the cases, 99% of the cases, the real waveform of the current in an integrated circuit looks much more like this one. In particular, when we are talking about digital chips. Why that's the case? Well, let me give you a little example that should be easy to understand, something you are certainly familiar with. Let's consider your computer. When you bought your computer, the most important chip in your computer is the CPU, the central processing unit. And nowadays, CPUs are ranked by number of cores, but one other important parameter is the speed of the clock. So the clock is a timer for the integrated circuit that is used to organize the different operation inside the CPU across time. So the CPU is really complicated. It has many circuits that has to work together. So if you don't give them a little bit of order, nothing will get done. So you need to organize them and make sure that operations are executed in a timely manner. So what happens is that the CPU usually have a pin where you have to apply a clock. A clock signal is a clock that looks like this. A series of pulses, this is voltage, a series of pulses that keeps repeating themselves forever. And they have a certain period, which is indicated with T. And the frequency, that is usually what is quoted for the CPU, is the inverse of the period. Now, these pulses are used to synchronize the operation inside the CPU. So every time there is a pulse, let's say, we could be on the rising edge of the pulse, like there, a bunch of operations are executed. And when the operations are done, no operation is executed until the next rising edge. For example, operations inside the CPU are what requires a current. So if the CPU is sitting idle and not doing anything, you can assume that the current that will require will be really low. And that is the case. Most of the current is required when operation needs to be executed, because that's when things move inside the CPU. So if you want to represent the current in this graph, I'm going to use the red now. Most likely the current will look like something like this. It will be low here, and then it will have a spike here. Then it will be low, it will have a spike. Low again, and then it will have a spike. Another reason why the required of current might not be constant is simply because the user might suddenly change what it's doing with the computer, and so all of a sudden more current might be required. For example, you might be one moment you might just be staring at your desktop, so not really much is going on, so probably a little current is needed. And the next moment you might be running a 3D video game that instead requires a lot of computing power. So that is why most likely the current for CPUs and for integrated circuit looks much more like something like this. Now, the average current that is required might very well be very similar to the example above, to the constant value of the current. But the actual waveform is completely different. It has a lot of spike and burst and up and downs. And that is why, as we'll see soon, you need to have bypass capacitor in order to guarantee a constant voltage at your device. Before I turn to the electrical circuit, I want to give you another water analogy to help you understand better the role of bypass capacitor in circuits. So I'm going to do that using this sort of hydraulic system where there is a sink and a faucet. And this faucet has a knob. And then this faucet is connected to a pump using a very long pipe. And down here we have a cistern or maybe a well where there's a lot of water and the pressure is pretty much constant. So the idea here is that you have this well where the pressure is, let's say the pressure is 0. And then you have a pump that generates a certain pressure P. And now the water is pressurized at this pressure available for you to use. So the moment you open the knob, the knob is pretty much representing a resistance in our circuit. So the resistance could be infinite if the knob is closed, which means there's no current, which means there's no water coming out. But the moment that you open the knob, you're going to set a certain value of the resistance. Here you have 0 pressure. So the difference in pressure is delta P divided by the resistance. It will give you a certain flow of water. So you get a certain current, which is your water stream. To understand the effect that all of these operation on the knob have on the pressure, we have to look at these more closely in the time domain. So let's have a little graph here with the time in the time domain. And let's assume that the knob is operated in this way. So the knob is kind of closed at the beginning, then at some point it is open, and then eventually it's closed again. Now let's look at what happened at the pressure. So this hydraulic system has been designed to have a constant pressure of P before the knob. That was the design of it. So we know that we start with a pressure equal to P here. Pressure is equal to P all the way till the moment in which the faucet is open. Now we know that because the pump will do anything in its power to get the pressure equal to P, we know that eventually the pressure will return to P after we open the knob. And we also know that the pressure will return again to P after we close the knob. What we really want to know now is what happens a short amount of time after the knob has been opened and after the knob has been closed. So you might be tempted to think that the pressure will still be equal to P, because after all we have a pump and the sole goal of the pump is to keep the pressure constant. However, think about it in physical terms. So if this is really an hydraulic system with a very long plumbing, the moment you open the knob, a large amount of water will be allowed to exit the faucet. Remember that the pressure is a representation of the presence of a large amount of water into a tight space. The moment you allow the water to exit your faucet, all of a sudden your pressure has to decrease because there's just less water available to generate that pressure. So, as a consequence, the moment which you open your knob, the pressure will suddenly drop, and later it will recover thanks to the action of the pump. At the same time, the moment which you suddenly close the knob, the pressure will suddenly increase, and then will decrease, returning to the value established by the pump. What we're saying here is that the pump, it takes some time to realize that the pressure has decreased, and it will try to increase the pressure at the faucet by injecting a higher amount of water into the system. But in order to do so, and it's because we assume the tubes are really long, it just takes some time. So the very moment you open the knob, you open the faucet to get more water, the pressure will suddenly decrease to then recover to the original value. So what can you do to improve this system? What if you don't like that the pressure has a sudden drop or a sudden overshoot? You want to keep the pressure as constant as possible. Well, what you can do is that you can add a pressure tank to the system. So this that I'm representing here is a pressure tank. So it's a device that is filled with water at a constant pressure and it's connected very close to your sink, to the faucet of your sink. So now, when you are applying a certain pressure P, here you have pressure equal to P everywhere. This pressure tank is obviously representing a capacitor. So as you can see, because we have a pressure P here and pressure 0 here, we have the elastic membrane that is being bent, as we've seen in the past, and some energy is being stored into the capacitor as elastic energy. If you think about the situation as a steady state, everything works just as before. You have a certain amount of water coming down. Now let's go again and see what happens when we suddenly open or close the faucet. In time domain, that's what we do again to the faucet. We just open and close it really fast. Well, just as before, the pressure was P before the knob, and all the way through it will be P again eventually, and it will also be P here. The moment in which we open the faucet really fast, we see that the amount of water available before the knob will just decrease. That will generate a sudden decrease of pressure. However, in this case, if the pressure P decreases, so if you have now something that is smaller than P, that means that the capacitor, the membrane of the capacitor will suddenly be able to push a certain amount of water up in the stream. So a certain amount of water would be provided by the capacitor because now the steady state equilibrium of the membrane is not respected anymore. The membrane is actually able to go up a little bit because the pressure has decreased. Hence, some water will be injected in the system. The net effect of this is that you will still have a drop in the pressure at the faucet, that is inevitable, but the amount of drop at the faucet will be much smaller than before. And the same can be said as far as when you close the faucet, the amount of overshoot of the pressure will be much smaller now. The simple reason for that is that you have a storage of energy, in this case pressurized water, sitting very close now to your sink, And the moment the pressure decreases at your sink, at your faucet for any reason, this device will automatically inject or take in an additional amount of water, trying to compensate and to keep the pressure as constant as possible. Naturally, unless you have an incredibly fast device, incredibly fast pressure tank, you're always going to have a certain delay in which this additional water is provided. But at least if you have a lot of this pressure tank next to your faucet, the amount of pressure drop that you will feel will be much smaller, and probably you wouldn't even be able to feel it at all. If that wasn't obvious enough, let me now state or reveal that the sink and the faucet in this hydraulic circuit represent the integrated circuit. So this is the user, this is the device that is responsible for requesting this kind of currents that go up and down. The pressure tank is the bypass capacitor, and a pump is representing the voltage generator or the battery. Now it should be much easier to understand why bypass capacitors are fundamental components in electronic and fundamental companion of any integrated IC. Integrated circuits, they require a constant voltage in order to work. The voltage doesn't need to be perfectly constant, but it needs to be within a certain tolerance band. So for example, if your nominal voltage is 3.3, you can allow the voltage to go as high as 3.5 or as low as 3.1, but you don't want to go beyond this range. If the voltage is too high, you risk to break the chip. If it's too low, you risk to turn it off. Unfortunately, integrated circuit likes to require currents that behave like this, that jumps up and down really fast. And that makes it very difficult, if not impossible, for the battery to provide the current and to guarantee that the voltage always stays within the tolerance band. In the context of the hydraulic circuit, we said that that's the case because the water needs some time to replenish the water that was consumed at the faucet. In this case, the real explanation involves also the concept of inductance, but you can still think it in the same term. The charge needs some time to go from the battery to the device, and if the device, the integrated circuit, changes the request of current immediately, it will take some time for the power supply to provide the additional current required. So the presence of a capacitor as an energy storage, as a charge storage, if you will, next to the integrated circuit can be very important because it can supply the additional charge that is required in moments of needs. So if we look at this current and we assume that is the current that is requested by an integrated circuit, if you didn't have a capacitor, so you will start from the nominal, let's say this 3.3 volts. So you start until the point, and then when you get here, you will get a drop, a quite significant drop. Then the voltage will slowly try to recover thanks to the voltage generated to the battery. But then again, it will be hit one more time by a very strong current. Then it will try to recover again, and then it will be hit again. Then it will recover here and hit once more. And then finally, maybe he will allow to actually return to the final value because there's no more current anymore. And so the voltage supply can provide the charge required to bring the voltage at the integrated circuit back to the nominal value. With a bypass capacitor, the impact on the voltage, it's much smaller. It's probably gonna look like something like this. So when there is an extra current that is required, you are gonna be hit, but the amount of drop of the voltage is gonna be much smaller, and then the system will recover, and so on. So here it will be hit again, and here the release will look like that. So here will be hit like this, and like that. And here it will do something like this. So you can see here, the voltage is still changing due to the erratic, if you want, behavior of the integrated circuit. But thanks to the presence of the bypass capacitor, the change in voltage is much smaller, much more contained. Another very useful application of capacitor is filtering. Filtering is an operation where you have an input signal, a certain voltage waveform. You pass it through a filter, and as a result, you have another version of the same signal out, which supposedly remove part of the signal that is not desired. The part of the signal that you might want to eliminate could be straight up noise. That's definitely something you always want to remove. But it could also be part of the actual signal that you just don't need. or that just will make things more complicated down the line. Now, it's kind of hard to understand, but to give you sort of an idea of this, think about MP3 files. So when you take a song and you convert it to MP3, you are losing something, and you're losing useful information because it's removing some of the frequency that are part of the audible range for humans. But what you get out of it at the end is something that it sounds very, very similar to the original song, but it occupies much less space on your drive. So it's a trade-off that is worth making in that case. And with filtering on circuits, is the same story. Most of the time, the filtering is done to remove noise, but sometimes you just have to kind of reduce the spectrum of your signal to make it easier to be digested for other blocks down the line. Now here I have a little example of a circuit made with RC components, so a resistor and a capacitor. So this filter is usually called, it's a low pass filter, and we'll see what that means. And let's just look at what happens at the output if we apply the input waveform that I indicated in red. So the input waveform is a voltage. I use this kind of strange symbol to indicate that it's not a battery, but it's a generator that can make any waveform you want. And then we have a resistor, capacitor, and the voltage across the capacitor is the output of this filter. So if you want the block that I indicated below, the filter that I indicated below will be this guy here. So we just want to see how the V out in blue looks like given the input signal V in. In order to be able to solve the circuit, I need to give you some information related to the components. I need to give you the values of the components, but the only thing I need to give you is really the time constant, the product of them, as you should remember from the charge and discharge lesson. So the time constant is RC and has a unit measurement of time. So we can compare the time constant dimension relative to the graph here. And depending on that, you're going to get very, very different results. For example, let's say one time constant, 1 tau, is this size here compared to the time scale. Now this is a very short time constant. So the output of the circuit will look like something like this. 3 time constant, 3 taus, will make the capacitor basically reach the final value of the input voltage. So we'll start from 0, let's say. And now in about 3 time constant, this will reach up here, then we'll do down here, almost all the way up, down, the final version of the voltage, the output voltage, resembles the input voltage, so you can tell that this is sort of a filtered version of the input, but all the hard edges have been removed. And that is why this filter is called low pass filter, because it only allows the low frequency components, so the components that move very slowly, to pass through, whereas the fast components are attenuated. If you recall, a capacitor doesn't like to change its voltage, so in order to change its voltage you need to apply a lot of current. So as a result, if you apply voltage to a resistor on a capacitor in this configuration, what you're going to get is that the low speed moving components will pass through in the output signal, whereas anything that moves really fast will be attenuated. The first step here was being smoothed out, but rounded a little bit, but you have the whole intensity is there, so the voltage actually reaches the peak, while this little pulse that is really, really fast, up and down just really fast, you still get something out, but it's attenuated. The peak is much lower now. So the output signal now, the components that want to move really fast have been removed. In this section, we're going to talk about diodes, a very important electronic component. We'll discuss how diodes work, the simplified IV curve for a diode. We will talk about the different types of diodes, and finally, we'll discuss the applications of diodes. Diodes are another type of component that is incredibly important in electronics. It is fundamentally a component with 2 terminals. As we can see in the picture here, there are 2 terminals for the diode. Another characteristic of the diode is that the diode is a non-linear component, and this is the first non-linear component that we encounter. and we're going to talk about this a little bit more later. Applications of the diode are countless. Diodes are used for rectification, for clamping, reverse polarity protections, and many other applications, and we will see some of them in this section. And finally, it's important to know that there are different types of diodes, each of them tailored for slightly different applications. For example, we start from classic diodes, like the one on the top in this picture, and then we can have Zener diode, which is another type of diode. Then we have LEDs, which are diodes that are able to emit light, as shown in this picture here. The two at the bottom, we have two LEDs, one orange and one red. In addition to be able to emit light, there are also type of diodes that can be used to detect the presence of light, and those are called photodiodes. The drawing in the slide represents the schematic symbol of the diode. This is the symbol. As you can see, it's composed by a triangle that connects to a line here. The symbol is obviously not symmetric, differently from the resistor symbol, for example. Here we have two distinct terminals. One terminal, the one directly connected to the triangle, is called anode, and it's usually indicated with A. The other terminal instead is called cathode, and is usually indicated with K. Given that diodes are not symmetric components, it's important for the designer to be able to distinguish between the cathode and the anode. Diodes come in different packages and different sizes, so depending on the package, the manufacturer will find a different way to help the designer distinguish between the two terminals. In the case represented in this slide, this is a pretty big through-hole diode, and the way the cathode is indicated is by the means of this gray band. On the image, I also indicated a current with ID and the voltage with VT. Now, looking at the symbol of the diode, you can very easily notice that the symbol looks very similar to an arrow. It looks very similar to something like this. That is intentional, and it's meant to tell you, to remind you how the components work. We haven't seen that yet exactly, but I can give you a preview. What the symbol is trying to tell you is that the diode is a component that allows the current to flow only in one direction. So the direction of the current is obviously the one indicated by the arrow of the symbol, and it's also the one indicated here. So the diode is a component that in the vast majority of cases, in particular for standard diodes, allow the flow of the current only in one direction. And the direction of the current is from anode to cathode. In order to understand how diodes work, we need to look at their IV curve. The IV curve for a component represents the relationship between the voltage applied to the component and the current that flows through it. Before we continue the study of the diode's IV curve, let's look at the IV curve of a resistor. The IV curve of a resistor is a straight line passing from the origin of the graph, here, where both the voltage and the current are equal to 0. The slope of the curve, which you can indicate this way, indicating the angle between the horizontal axis and the curve, represents the resistance of the component. A resistor with a lower resistance will be represented by a straight line passing from the origin that has a higher slope, like this, for example. So this is for smaller resistance. This is intuitive, as smaller resistors require larger currents for the same applied voltage. The IV curve for a resistor is simply a representation of the Ohm's law for the component. The Ohm's law for a resistor is I is equal to V divided by R, and this curve is simply representing this equation. The IV curve is a tool that allows you to find the value of the current for a given voltage. Here's how. Say you have applied a certain voltage Vx to this resistance R. So Vx is here on the horizontal axis. And wonder what is the current that flows through the component? Well, you can solve the problem in two ways. The first way is to use Ohm's law. This is probably the easiest way in this case, because Ohm's law is such a simple equation. So Ix, which is the current going through this resistor, will be simply equal to Vx divided by R. And this is probably what 99% of the people will do. Another way is to use the IV curve. From the value of Vx on the horizontal axis, you draw a vertical line till you meet the IV curve. For example, we can represent it with a dashed line. Then you find what is called the operating point on the curve. And then you draw an horizontal line till you meet the axis of the current. This is the value of the current Ix that you're looking for. Note that the IV curve for a resistor is said to be linear, because if you, for example, now decide to take a value of a voltage that is equal to half Vx, your current will also become half. Before moving on to the study of the diode's IV curve, it's important to highlight how every IV curve chart should always indicate how the voltage and the current were measured on a component. In this slide, I indicate that by adding a little sketch on the top left corner of the IV chart. Note that this is really important because if I decided, for example, to measure the currents in a different way and to consider as positive the currents going in this direction, the IV curve would have changed. And instead of looking the way it is now on the slide, it would have flipped around the horizontal axis. So it would have gone from this way to this way. Let's now look at the IV curve for a diode. First of all, let's look how the voltage and the current are measured for this component. You can see from this little graph that V will have a positive value when the anode has a higher potential than the cathode, like this. Furthermore, you can see that the current is considered positive when it flows from the anode to the cathode. So this is really important to be able to understand what's going on in the IV curve. By looking at the curve, first off, we can immediately say that this is not a linear curve. Linear relationships and curves are always represented by straight lines, and this is everything but a straight line. So this component is not a linear component. Secondly, in order to study the curve better, we can split the graph in three different sections. The first and probably most important region, it's called forward region, and it's characterized by a voltage V that is equal to 0 or larger than 0. So all this region is the forward region. And the diode, when it's operating in this region, is said to have a forward bias. The second region is called reverse, and the diode is said to have a reverse bias. In this region, the voltage is negative from 0 volt up to, in this case, for this specific model of diode that I picked, that is the 1N4148, just an example, all the voltages from 0 to minus 75 volts. Minus 75 volt is called reverse voltage of the component. And finally, the last region is the breakdown region. Breakdown. In the breakdown region, the voltages are negative and higher than 75 volts. So for all voltages negative and higher than 75 volt, we are in the breakdown region. Let's look at the three regions of operation more closely. Let's start with the forward region. So in the forward region, as you can see here, the current is quite low for voltages lower than 0.7 in this case. But then it grows really fast, exponentially, for voltages higher than 0.7 volt. This 0.7 volt is called forward voltage, but is also referred as V diode or threshold voltage. You can see how this voltage behaves like a threshold for the diode. Any voltage lower than the threshold will keep the diode off, while as soon as the current becomes even slightly higher, a large amount of current is allowed to pass. You can think as the diode in this region as a voltage control switch. If the voltage applied to the diode is lower than the threshold, the diode is like an open switch. But as soon as the voltage reaches the threshold and goes beyond the threshold, the diode becomes similar to a closed switch. In the reverse region, voltages are pretty high. They go from 0 to minus 75, much higher than 0.7, 1 volt, 2 volts that we have in the forward region. However, even if we have such a high negative voltage, the diode does not allow the passage of the current, and only a very tiny negative current is allowed to pass. Note that this current is really low. This graph is not to scale, but you can see that the negative part of the vertical axis says that the current at this point is 0.1 microamp. That means that the negative current that is flowing in the reverse region is in the order of less than 1 microamp, which is practically zero for most applications. If the negative voltage keeps increasing beyond the reverse voltage of the diode, which is minus 75 in this case, so if we enter in this region, the diode will enter into the breakdown region. Now in the breakdown region, a large negative current is allowed to flow. Normal diodes are not designed to work in the breakdown region, hence they will break. The reason for the failure is thermal. At this point in the curve, for example, you have at the same time a very high current and a very high voltage. The product of voltage and current is the power dissipated by the device, and with a high dissipated power, the temperature of the device will increase really fast and eventually will fail. Thankfully, for most applications, the value of the reverse voltage is so high that you really don't need to worry about it. If you have a device that is operated by a battery, you have a much lower voltage. So in order to get to minus 75, you really have to do something special. There are some circuits that can bring the voltage to negative values that are pretty high, but in most of the cases, you will not have to worry about it. It's important to note that while normal diodes will break in the breakdown region, there are some type of diodes, like the Zener diode, that are designed to operate in this region, and we'll talk about them later. In the previous lesson, we analyzed the IV curve for a diode. We have seen that the curve is not as simple as the one of a resistor, and it is convenient to study it by separating it in three different regions of operation: the forward region, the reverse region, and finally the breakdown region. While simulation softwares can easily solve circuits with diodes using real IV curve, the relationship between voltage and current is still too complicated to be handled by hand. Furthermore, it's not necessary for the vast majority of the circuits. In this lesson, we will see how the diode IV curve can be simplified to make possible to solve circuits with diode by hand. In this chart, we represent in blue the original real IV curve for the diode, and in red the equivalent simplified curve. As you can see, we've gone from the real curve to the simplified one by doing two things. Number one, all the parts of the curve where the current was either rising or falling fast with the voltage have been replaced with a vertical line. For example, here and here, you can see that the simplified model uses a vertical line. And number two, all the parts where the current was really low have been replaced with a current equal to zero. As you can see here in this region, in the reverse region of operation, and here in the forward region of operation. Just like we did before, we can split the simplified diode IV curve in three different regions. Because the IV curve has changed, we can now define three new, slightly different and more convenient regions of operation. The first is the on region, which is defined for all voltages equal or higher than the threshold voltage of the diode. So for V equal or higher than V threshold. The off region is the region in which the current is equal to zero, which goes from the reverse voltage, which is minus 75 in this case, up to the threshold voltage, 0.7 volt. So the off region is this one. And finally, we have the breakdown region, for negative voltages higher than VR, so this direction here, which is the only region where the current becomes negative. This is a much easier curve to study because, as we will see next, we can substitute the diode in each of its region of operation with a much easier equivalent circuit. Finding an equivalent circuit for a diode in the off region is very simple. The off region is this region where the current is always equal to 0. We can see that here in this region, no matter what is the voltage across the device, we always have 0 current. So the best way to represent this region with an equivalent circuit is to use an open switch. In an open switch, there is no path for electrons to flow, so the current has to be 0 no matter what is the value of the voltage across the switch. In fact, the IV curve for a switch will be something like this. Current and voltage here. This will be the IV curve for an open switch, where no matter what is the voltage across it, the current always has to be 0. Naturally, in this case, this approximation is only valid when the diode is off. It's not valid in the other two regions of operation. Let's now look at what happens when the diode is in the on region of operation. This is the on region of operation. We can see that the voltage is always equal to 0.7 volt and the current is positive. The best approximation of a diode is in the on region is a closed switch in series to a voltage source. So here we have a voltage source, and here we have a closed switch. Now, because an ideal closed switch is indistinguishable from just a wire, we can further simplify this model and remove the switch and just leave only the voltage source. The value of the voltage source is equivalent to the threshold of the diode, which in this case is 0.7 volt. Let's try to understand why this model is correct. An ideal voltage source, like an ideal battery, is a device that, no matter what is the current flowing through it, is characterized by a constant voltage. So if we represent the IV curve for an ideal voltage source equal to 0.7 volt, that's what it will look like. Just a straight vertical line crossing the horizontal axis at 0.7 volt. This is very similar to how the IV curve for the diode looks in the on region. The only difference that one has to keep in mind is that while the voltage source allows for both positive and also negative currents, in the diode we don't have negative currents when the diode is on, but only positive currents. So only currents flowing from the anode to the cathode is allowed. Another interesting thing that is worth highlighting is that the simplified model of the IV curve does not allow for any voltage across the diode that is either higher than 0.7 or lower than minus 75 volt. As you can see, there is no corresponding point in the curve for any voltage higher than 0.7 or lower than minus 75. This is an oversimplification because, as you can see, the real IV curve keeps going for higher voltages and for lower voltages, but this simplified model is good for most applications. The circuit used to approximate the diode when it's in the breakdown region is very similar to the one used for the on region. The breakdown region is this one. The voltage is always equal to minus 75 volt and the current is negative. So the equivalent circuit is the following. Again, we have a closed switch in series to a voltage source. If we neglect the presence of the closed switch, we can just replace the diode with a voltage source equal to minus 75 volts. Just as in the case of the diode in the on region, this model is only valid for negative currents, which is currents going from the cathode to the anode. This model is not comparable with the positive current, as one can easily see from the simplified IV curve, there is no positive current in the breakdown region, but only negative values of the current. In this lesson, we're going to talk about an hydraulic equivalent for the diode. Just as in the case of the resistor and the capacitor, for example, the equivalent model is meant to help providing an intuitive understanding of how the component work, but it's not an accurate representation of its operation from any point of view. The behavior of a standard diode can be represented by a one-way gate. As you can see in this sketch, the one-way gate is composed by a gate flap, a hinge, and a flap stopper. The flap stopper prevents the flap from swinging open towards the left, but it can only open towards the right. Down here I indicated the symbol of the diode, and you can see how it maps with its hydraulic equivalent, and you can see that the anode is on the left and the cathode on the right. Let's see how the hydraulic model of the diode can be used to represent the component. Let's start with the example on the left side of the slide. If a voltage is applied to the diode in this way, which is with a higher potential at the cathode compared with the anode, we know that the current will be about zero. We can call it zero. We know the diode is in the off region of operation. Let's see what happens with the hydraulic equivalent. Well, we know that higher voltage is represented in the hydraulic world with a higher pressure of the water. So if you are having higher pressure on the right side of this gate, the gate will be shut closed and no water flow will be allowed. This example represents the simplified IV curve of the diode in this region. So it represented for all the points where the voltage is negative up to the breakdown region. How can we explain the behavior of the component in the breakdown region? Well, you can imagine that if the pressure on the right of the gate is high enough, eventually the gate will be broken open and water will be allowed to pass, but the component would have been damaged. On the other hand, we know that if we apply a potential that is higher at the anode compared to the cathode, it is possible to have a current higher than zero through the diode if the voltage difference between anode and cathode is large enough and higher than the threshold. It is easy to explain the behavior of the diode using the hydraulic example. If the pressure of the water is higher on the left compared to the right, we will have a positive net force pushing the gate flap from the left to the right. Hence the gate will open and the current will be allowed to flow. This example represents the simplified IV curve of the diode in the on region. Here. If you imagine that the gate flap takes a certain amount of force to open, you can see how the model can be used to represent this region as well, where the pressure is higher on the left compared to the right, but it's still not quite high enough to open the gate. In this lesson, we will study a few circuits with diode to understand how to use the IV curve we've just learned in practice. The challenge with studying circuits with diode is that, differently than with resistors, capacitor, and other components, diodes are nonlinear components and they behave in a different way depending on the region of operation they are in. Let's look at one example. On the left, you can see what looks like the simple possible circuit with diodes. A voltage source, like a battery for example, connected to a diode. I indicated the voltage of the voltage source as VCC. This is quite common. And then I indicated the voltage on the diode as VD, and then we have of course the current through the diode that I call ID. We will see how this circuit is really not that trivial at all. In the center of the screen, I represented the IV curve for this diode, and I indicated its threshold and reverse voltage. I assume that these voltages are 1 volt and 100 volts respectively, and they're indicated here. On the right, there is a table that we're going to fill for different values of the supply voltage VCC. Solving this circuit, which is finding V diode and I diode for each VCC, seems simple. The only thing one has to do is to use the IV curve for the diode. The first step is easy. If we look at the circuit, we recognize that because the voltage source and the diode are in parallel, the voltage on the diode will have to be the same as the voltage on the voltage source. So filling up the first column here is rather simple. I'm just going ahead, minus 10, 0, 0.5, 1, 10, minus 150. And of course here I indicate the unit of measurement, so we're talking about volts for VCC, volts for VD, and amps for ID. Now let's go ahead and solve the circuit for the current in the diode. The first points are simple. For voltage equal to minus 10 volts on the diode, that means that on the IV curve will be somewhere here, and we can immediately see that the current is equal to 0. For a voltage equal to 0, we are here, the current is also 0. For voltage equal to 0.5, we are here because the threshold is 1, so we are halfway between the 0 and the threshold, so we have a 0 current. The last 3 points of the table are the most difficult to calculate. Let's start with the first. For VCC equal to 1, V diode is also equal to 1. 1 volt is the threshold of the diode, so we know that the diode will be on and conducting some current. Unfortunately, the simplified IV curve does not help with finding the value of the current, because there is more than one point corresponding to V diode equal to 1. As you can see here, we could pick this point, this point, this point, this point, or this point. There is an infinite amount of points that we could pick. This is one rare example where the simplified IV curve for the diodes fails to provide an adequate answer. The only way to solve this circuit is to either use the real IV curve, which could look like something like this, where only one point corresponds to voltage equal to V threshold equal to 1 volt, or at least, if not a real IV curve, a more sophisticated simplified model. For example, a model that instead of using a vertical line for the on and the breakdown, uses a line with a certain slope that tries to fit better the real curve of the diode. We don't want to do that, so for now we don't get an answer for the current of the diode, and we're just going to indicate that the current is going to be larger than 0. The simplified IV curve falls short in the last 2 cases as well, but for a different reason. As you can see from the graph, there is no point corresponding to voltages higher than 1 volt or smaller than minus 100 volts, so there's no solution to our problem. Once again, this point can only be solved by using the real IV curve for the diode, which instead will have points for voltages higher than 1 and points for voltages lower than minus 100 volts. However, that's not what we have available. We do know what is the shape of the real IV curve, so we can just say that the current will be much higher than 0 at 10 volts and much smaller than 0 at minus 150 volts. The circuit presented in this lesson seems very simple, and the fact that simplified IV curve cannot be used to solve the last 3 points of the table is puzzling. What's the use of a simplified chart if it cannot be used in some conditions? First of all, it's important to highlight that all simplified models are only valid in a limited region of operation. This is the compromise you have to make for having reduced complexity. It's the engineer's role to make sure that all the models that he or she is using are valid. As far as the diode is concerned, this example, while seemingly simple, is actually extremely rare. Diodes are almost never connected in parallel to a voltage source. The reason for that is simple. If you take 2 diodes of the same model, same part number, same vendor, and even if you buy them in the same shop, their IV curve will be different. There is no way it could be exactly the same. This is true for any component. However, in the case of the diode, the IV curve is so steep that if you try to get to a precise current by setting the diode voltage, you will have a very large error between different devices. Let me give you an example. Let's say you have a diode and the real IV curve looks like this. Now you have a second diode, you build a second circuit with another diode, same part number, same model, but these other diodes have an IV curve that looks like this. They are very similar to each other, they just have a slightly different threshold voltage. They could also have a different slope, they could have quite a few differences. However, let's just assume that they only have a difference in threshold voltage. Now, if you try to set a precise current through the diode, by setting the voltage here, for example, it's easy to see how you will have big difference in current between the two diodes. The first diode will have this value of the current. The second diode will have this value of the current. So you can see how the second diode will have more than twice as much the current of the first diode, while in theory you expect them to have exactly the same current. It's common to say that diodes are not controlled with voltage, but they are controlled with current, and we will see an example of that in the next lesson. In this lesson, we will see what is the behavior of the diode when its current is controlled externally. In the circuit on the left, I've replaced the voltage source with a current source. An ideal current source is a device that, no matter what is the voltage at its extremity, it always provides the same current. So if you want to represent the IV curve for a current source that generates, say, 1 amp, that's how it will look like. Current, voltage, just an horizontal line crossing the vertical axis at 1 amp. Meaning that no matter what is the voltage, the current will be always the same. Just like with the voltage source, different symbols can be used to represent the current source. In this symbol here, we have two circles, and then we have an arrow to indicate the direction of a positive current. Another way to represent the current source is the following, like this. I tend to like the first better. The current source is an idealized device. There is no simple equivalent component like the battery is for an ideal voltage source. But you can generate an equivalent current source by using a professional voltage supply. This scenario is simply meant to represent what happens when your external circuit forces a certain current into the diode rather than a voltage. We will see a more realistic example of this in the next lesson, but this is a good place to start. This time, the current is the input of the exercise, so I indicated here different value of the ID current, the current in the diode. I changed the unit of measurement to milliamp, which is more realistic. The other thing that we don't have to worry about is VCC, which is how I call the voltage across the current source, because as we already seen in the previous lesson, it's the same as VD, so we don't need to calculate, so we can probably just write equal to VD. That's it. One thing that we can note immediately is that, differently than with the voltage, the IV curve has point for any value of the current that we want, because here the graph will continue and also in this direction. Let's start the analysis. Let's start with the first point here, minus 10 milliamp. Because the current is negative, that means that we have a 10 milliamp current going in the opposite direction of the arrow of the current source, which means that the current is going in this direction from the cathode to the anode of the diode. That means that the diode has to be in the breakdown region. Now we don't know where 10 milliamp is in this scale, minus 10 milliamp. We can say that it's probably here, which will mean that the voltage across the diode is minus 100 volts. which is the reverse voltage of the diode. Same results for minus 5 milliamp, which would be somewhere here. We get the same voltage, minus 100. Note that in reality, the voltage will be different between these 2 points. For example, if we represent the IV curve, the real one, it could be something like this. So one point will be here and the other will be here. So as you can see, there is a little difference between them, but this difference can be neglected in most applications. In particular, if you consider that we are working around 100 volts here. So even if this difference ends up being a volt, it's still neglectable in most cases. Let's keep the case with the 0 milliamp and let's go to the positive currents. Now, because the current is positive, that means that it's going in the same direction as indicated by the current source. So it's a current going from anode to cathode, which means that the diode is on. If the diode is on, as we can see here, any positive current will always have the same voltage in the simplified IV curve, which is the threshold voltage, which is 1 volt. So we have 1, 1, and 1. No matter what is the value of the current. We can make the same argument here that we did for the breakdown region, the fact that in reality the voltage is slowly increasing with the current. But again, unless you're designing a precise analog circuits where the precise voltage across the diode matters, you can neglect this difference. Finally, let's look at the current equal to 0. What happens in this point? In this case, the diode is off because the current is 0, and the voltage is undetermined, as it could be anywhere between minus 100 and 1 volt, accordingly to this IV curve. Let me cancel here. If you look at this IV curve, we have 0 current in this whole region. So that means that the voltage could be anywhere between minus VR and the threshold. While this limitation might seem as big as the one we encountered in the previous lesson, there are 2 important differences. The first is that the diode is off. Hence, it behaves like an open switch. Every time you have an open switch, you cannot tell what is the voltage just by looking at the switch. The voltage will be determined by the external circuit. In this case, the external circuit is an ideal current source, which is a component that doesn't exist, and probably the only component that is not able to determine its own voltage. In reality, there will always be some other component that sets the voltage. Most likely, the voltage will be 0 volts. Second point, we might not have an exact voltage value if we use the simplified IV curve, but compared with the previous lesson, at least this is not a dangerous operating point. The diode is off, the current and the power are 0, so nothing is going to break. On the contrary, when you play with the voltage, when you force the voltage on the diode, if you make a mistake and the voltage happens to be a little bit too much beyond the threshold, you could have quite high currents because the curve is very steep and you might suddenly break the device. In this lesson, we will look at a much more realistic circuit. As you can see, in this circuit we have the series of a resistor and a diode, all in parallel to a voltage source. This is one of the most common ways that diodes are used in real life. We know that VCC is 3 volts, we know that the resistance is 200 ohm, and we also know that the threshold of the diode is 1 volt. And we want to find the voltage on the resistor, the voltage on the diode, and the current in the diode and the resistor. This time, we will solve the circuit by using the equivalent circuits of the diode in the different region of operation instead of looking at its IV curve. In the previous examples, either the voltage or the current of the diode was known. Hence, one only has to use the IV curve to solve the circuit. Because if you have one of them, and this is your IV curve, now representing the real one, once you have either the voltage or the current, you can always find the other one using the IV curve. In this case though, due to the presence of the series resistor, neither the voltage nor the current are known, but they need to be derived somehow. As you can see here, we know that we have 3 volts on the series of the resistor and the diode, but we don't know how much of these 3 volts will go on the diode and how much will go on the resistor. Here is where using the simplified IV curve, or even better, equivalent circuits, helps speed up the study of the circuit. If you had to use the real IV curve or the real equation to solve this circuit, you would have to solve much more complex equation to get your result. Solving circuits with diodes require following a 4-step procedure. Point number 1. Make an hypothesis on the operating region of the diode. Just by looking at the circuit, you can have a rough idea and try to guess whether the diode will be on, off, or in the breakdown region. It doesn't matter which one you pick. It's an arbitrary choice. In point number 2, you replace the diode with the corresponding equivalent circuit of the region of operation that you chose. In point number 3, you now have a circuit without any diode, because all the diodes have been replaced with their equivalent circuit. So you can go ahead, solve the circuit, and verify that the voltage and the current on the diode are compatible with the chosen operating region. Finally, point number 4, if the voltage and the current at the diode are compatible with the region of operation that you guessed in point number 1, you're done. If not, change the hypothesis and restart from point number 1. Okay, let's try to solve this circuit. Let's start with the assumption that the diode is off. So this is point number 1. Point number 2. If the diode were off, the equivalent circuit will be an open switch. So we delete the diode and, okay, we can leave it like that. The circuit is open, so it's equivalent to an open circuit, or if you want to make it better, we can actually draw the switch. Now, at this point, there's no more diode in the circuit, so we can easily solve the circuit using Ohm's law and the Kirchhoff laws. Because the diode was replaced by open switch, the current will have to be 0. So ID, in this case, will be equal to 0. But if ID is equal to 0, VR will also be equal to 0. Now, if you apply the Kirchhoff voltage law, it will be very easy to determine that if VR is equal to 0, VD has to be equal to 3 volts. Now, point number 4, let's verify our hypothesis. Is the diode off if the voltage is equal to 3 volts in that direction and the current is equal to 0? The answer is no. The threshold of the diode was 1 volt. So with 3 volt in that direction, which is the right direction to turn the diode on, the diode will definitely be on. In conclusion, we started assuming that the diode was off, but after we had gone through all the steps of the process, and we have calculated what would be the voltage and the current through the diode if the diode were to be off in the circuit, we found out that those values of current and voltage were not compatible with the diode in the off region of operation. So that assumption was wrong, and we have to start from scratch. Let's restart from point number 1, and this time we assume that the diode is on. If the diode is on, the equivalent circuit of the diode will be a voltage source equal to 1 volt, where the potential is higher at the anode. So let me delete the open switch, and we replace with a voltage source equal to 1 volt. It's easy to see, using the Kirchhoff voltage law, that the voltage on the resistor has to be 2 volts now. You can see that the diode and the resistor are in series, so 2 plus 1 is equal to 3, which matches with the voltage source that is in parallel. Now, if the voltage on the resistor is equal to 2 volts, and the resistor is equal to 200 ohm, that means that ID will be equal to 10 milliamp. Is this condition compatible with the diode in the on region of operation? Yes. When the diode is on, the voltage at its terminal is equal to 1 volt, which is the threshold of the diode, and the current has to be positive going from the anode to the cathode. Just like in this case, we have 10 milliamp going down and crossing the diode from the anode to the cathode. We have completed the study of the circuit. Notice how it is the combination of the voltage source and the resistor that determines the value of the current in the diode. The diode is simply either off, enforcing a 0 current, or on, enforcing 1 volt. The current is determined by the external circuit. This is how the current was calculated, in fact. VCC minus V diode divided by R is equal to the current in the diode. You take VCC, which is the overall voltage, you remove the drop on the diode, so then you're left with the voltage on the resistor. You divide by the resistor and you find the current in the resistor, which is also the current in the diode. This is the way the diodes are used most of the time. You turn on the diode by providing a voltage that is higher than this threshold. In this case, the circuit is able to provide a 3 volts, which is higher than 1, so most likely it's going to be able to turn on the diode. And then you place a resistor in series to the diode to fix the current to a desired level. In this lesson, we will study a particular type of diode called light-emitting diode, or LED for short. LEDs are a type of diode that emits light when a current flows through them. LEDs are operated in a very similar way to standard diodes. The only difference is that when they are in the on region of operation and there is a positive current going from the anode to the cathode, LED will emit some visible light with a different color depending on the type of LED. LEDs are widely used for traffic signals, automotive, indications in electronic devices, and in recent years they have also become more and more popular as outdoor and indoor illumination sources thanks to their higher efficiency and longer lifetime. LEDs come in different packages and form. A few examples are shown in this slide. Here you can see surface-mounted LEDs used in LED strips for illuminations. This is another example of surface-mounted LED used to signal the presence of power on a circuit. These are classic through-all red LEDs. Finally, on the right, I show the internal design of a through-all LED, like the red ones that I've just shown. Differently than with regular diodes, the way the cathode is distinguished from the anode is via the flat spot on the component package. This region here. Additionally, when the LED is new and its lead have not been cut yet, the cathode can be distinguished by its shorter lead. As you can see here you have one component. If you look at this one, you will notice that one of the lead is shorter. This will be the cathode. Let's try to understand how light can be created in LEDs. On the left, we have a circuit composed by a voltage source in parallel with the series of a resistor and an LED. Note that the symbol of the LED is the same as the symbol of a diode, just with 2 extra arrows to indicate that it's a component that emits light. The voltage source generates 5 volts. The LED requires 2 volts in order to operate, so the remaining 3 volts is falling across the resistor. The current is equal to 20 mA. At the beginning of the course, we learned that voltage is a representation of the electrical potential energy of the charges per unit of charge. Let's think of what an imaginary positive charge will do in this circuit. The positive charge will start the journey here with a very high energy, indicated by the 5 volt. Then, as the charge proceeds towards the opposite side of the voltage source, it will lose 3 volts worth of energy crossing the resistor. And finally, it will lose the last 2 volts worth of energy crossing the LED. You might have heard that there is a thing called the principle of conservation of energy, which is a very important principle, which states that energy can neither be created nor destroyed, but it can only transform from one form to another. And we've just seen that the positive charge started with a very high energy out of the voltage source, but then it lost all the energy crossing the circuit. So the question is, where does the energy go? The energy lost on the resistor converts into thermal energy, which means that the resistor's temperature will increase. The energy lost on the LED converts into 2 forms of energy. A small part of the energy is converted into thermal energy, which will also cause the diode temperature to rise. The designer of the component will try to minimize this contribute as much as possible. The remaining part of the energy is converted into light emitted from the diode. The higher is the portion of the energy that is converted into light, the higher is the efficiency of the LED. As we've seen in the previous lesson, when a charge crosses the LED diode, a certain amount of its energy is converted into a different form. Let's consider an electron. Electrons will move in the opposite direction of the imaginary positive charges that we considered before, so it will move from the cathode to the anode, like this. The total energy that the electron loses by crossing the LED will be equal to U equal to E multiplied by VLED, where E is the charge of the electron and VLED is the voltage across the diode when it's in the on region of operation. Part of this energy, that we can call UT, will be lost as heat, which means that the diode will become hotter. Another portion of this energy, that we can call UEM, will be converted into electromagnetic energy. Just as electrons are the fundamental unit of the electric current, electromagnetic radiation can be thought as composed by a stream of particles called photon. So in the end, one electron with energy U that is passing through the diode will convert a fraction of this energy, called UT, into heat, this one, and the remaining energy will generate a photon with energy exactly equal to UEM. So the remaining energy will be given to a photon that is emitted outside of the component. Now the question is, how much energy one needs to make a photon? Well, it depends on its color. Visible light is part of the electromagnetic spectrum, which ranges from radio waves to X-rays and beyond. Only a small portion of the spectrum is visible, and it's the one that I represented here with this colored chart. Within the visible electromagnetic spectrum, photons with different energy will be perceived as having different color by the human eye. Different LEDs are designed such as when electrons convert their energy into photons, they will do so at a specific energy or color. The chart in the slide shows the energy of photons for different colors. The energy here, these numbers, are indicated in electron volt. Which is indicated with EV. 1 electron volt is exactly the energy that one electron loses or gains when its potential changes by 1 volt. So at the end of the day, the numbers on the chart tell us how much energy expressed in volt we need to consume at a minimum on the LED to produce a certain color. As you can see, red is the color that requires the least amount of energy, while blue is the one that needs the most. That explains why the threshold or forward voltage of the LEDs is different depending on the color. Note that because some energy is always lost as thermal energy, the number in the chart is only the minimum voltage required for each of the colors. In this lesson, we will talk about another type of diode, the Zener diode. Zener diodes are diodes designed to work in the breakdown region. On the left, I show a typical IV curve for a Zener diode. And I also show here the new schematic symbol for this component. It's very similar to the one of the standard diode. It just had 2 little legs at the cathode, like this. Looking at the IV curve, we can see that the on and the off region are very similar with the standard diode, with a forward or threshold voltage between 0.3 and 0.7 volts. The big difference is in the breakdown region. With a standard diode, the breakdown region starts for very high negative voltage, whereas with a Zener diode, we have much lower voltages. For example, minus 4.3 volts in this case. Because of the low breakdown voltage and because of the way they're designed, Zener diodes can be operated continuously in the Zener region without suffering any damage. So you can bias the device to have a negative current here, for example, corresponding to a certain voltage, and you can keep the device in that point of work indefinitely. In this slide, we see a typical application of a Zener diode. Very often, Zener diodes are used to generate relatively constant voltage from a variable source and for a variable load. Let's see how it works. Let's look at the circuit on the right. It's easy to see that if the voltage of the battery is high enough, that is, higher than the Zener voltage of the Zener diode, the diode will be in the Zener region of operation, because a current with this direction will be forced through the device. The key of the circuit is to dimension the resistor so that the diode is properly biased in its Zener region of operation. You don't want to bias the device rather than somewhere here, because you're not really in the Zener region of operation, but you want to bias it deep into the breakdown region, where the curve is so steep that the device is actually behaving like a voltage source. At the same time, you don't want to use a current that is too high, because that will just drain the battery faster and heat up your components. Let's say that after consulting the datasheet, we figure out that the right amount of the current that we want is 50 milliamp. So we want to find where 50 milliamp is here. This is minus 50 milliamp. So that we want to bias our Zener diode in this point of operation. In order to do so, we have to design R to have a certain value. The voltage of the battery is 9 volts. And we'll try to get the Zener diode into the Zener mode. So when it will be in Zener region of operation, the voltage here will be 4.3 volts. So that tells me that the remaining voltage across the resistor will be 4.7 volts. And we said that we wanted to have a current that is 50 milliamp. So to get a current equal to 50 milliamp with 4.7 volts of drop, we need R equal to 4.7 volt divided 50 milliamp, which is about 94 ohm. So now that we know the value, we can cancel this, and we just say that R is equal to 94 ohm, and the current will be 50 milliamp. Let's indicate the current here, because that will be the current in the resistor. And the voltage across the diode will be 4.3 volts. And we succeeded in biasing the device in this point of operation. Now you can see how this application is quite good at generating a constant voltage equal to 4.3 volts, because now even if you connect a certain circuit afterwards, like here, this circuit, in order to work, is going to require some current. But as long as the current that is required by this device is not too high, let's say up to, we can call it maybe 30 milliamps, then we will still have a remaining 20 milliamp going to the diode, and we will still guarantee that the diode is crossed by a negative current in that direction, so the diode is in a Zener mode of operation with a voltage approximately equal to 4.3 volts. At the same time, you can notice this other thing, that even if the battery voltage drops as the battery discharge, the output voltage will remain constant, equal to 4.3 volts, as long as the drop across the resistor, which is V bat minus 4.3 volts, is high enough such as the current going through the device, it keeps the device in the Zener region of operation. The trick to use a Zener diode to generate a constant voltage is to design a circuit around it that guarantees that for all application conditions that you want to consider, there is always a minimum amount of current going through the diode to keep it in the Zener mode. For instance, in this example, the circuit forces a 50 milliamp current through the diode when the battery is full at 9 volts and there is no load. However, we've seen that as the battery discharges, or if you connect something in parallel to the Zener, the amount of current to the component will decrease. So the point of work will move from here, it will go up, getting closer and closer to the end of the Zener region, where the curve is not as steep anymore. It is up to the designer to make sure that in all conditions the current never gets below a certain value, a certain limit, such as the operating point will stay in the steep part of the curve and the diode will keep a relatively constant voltage. In this lesson, we will discuss one of the typical applications of diodes, rectification. On the left, we have a circuit that is composed of an AC voltage source, a diode, and a resistor. We decided to call Vin the voltage generated by the voltage source, and we have represented it in a graph on the right. As you can see, the voltage Vin is sinusoidal, so it periodically switches between positive and negative. We also indicated that the max and the minimum value of the AC voltage is V peak and minus V peak. We will need this later to calculate the value of the current. We call V out the voltage on the resistor, and we call ID the current in the diode. We also assume that the diode is ideal, meaning that its forward voltage when it's on is equal to 0 volt. This helps simplify the study. This circuit is called half-wave rectifier. And it will be easy to understand the reason of the name after we have solved the circuit. The goal of this circuit is to take an alternating current and convert it into a direct current. An alternating current is a current whose direction of flow changes with the time from positive and negative. If you imagine that we replace the diode with a short, like this, the resistor will be in parallel to the AC voltage generator, hence the current will continuously change between positive and negative. So the current will be something like this, where the peak here will be equal to V peak divided by R, and this peak here will be equal to minus V peak divided by R, as per Ohm's law. When the diode is added to the circuit, things change. So let's delete these markings. Let's delete the short, another wire. And let's see what happens when we add the diode. In order to solve this circuit, we have to remember how the simplified model of the diode works. When the diode is off, it behaves like an open circuit, so the voltage on the resistor will be 0 volt, because no current can flow. When the diode is on, V out will be equal to V in, because the ideal diode becomes effectively a short circuit, given that the threshold voltage is assumed to be 0 volt. Solving the circuit is a matter of understanding when the diode is off and when it's on. To solve the circuit, let's assume the diode is off all the time. Let's draw the corresponding V out and ID, and let's see if they are compatible with the diode IV curve at all times. So if the diode is off at all time, the circuit is open, the current has to be 0, and therefore the voltage V out will also be 0 at all time. So it will just be a line like this. If V out is 0, that means that the voltage V in is also representing the voltage across the diode, because the voltage across the diode will be represented like this, Vd. Now if this side is always equal to 0, and this side has a value different than 0, then the voltage Vd across the diode will be exactly equal to V in. If that is true, it's easy to see how the diode will be indeed off when the voltage is negative, but it has to be on when the voltage is positive. So in this region, from here to here, the voltage across the diode is negative, and if we remember the IV curve of the diode, we know that the diode has to be off. Obviously, we are assuming that the V peak is much smaller than the breakdown voltage of the device. Conversely, if we look at the other two regions, region A and region C, we can see that in region A and region C, the voltage is positive, and that means that the diode has to be on, because a voltage larger than the forward voltage of the diode, which in this case is 0 volt, is applied in the right direction, between anode and cathode. So the diode has to be on. Now that we understand when the diode is on and when the diode is off, we can redraw the curves of VR and ID. So just to make it a little bit more clear, let's cancel ABC and let's just say on, off, and on. I delete the previous Vout and let's update the graph. Okay, when the diode is off, Vout will be equal to 0. So this is how it will look like. When the diode is on, Vin will be equal to Vout. So the output voltage will be exactly the same as the input voltage. Like this. As far as the current is concerned, when the diode is off, the current will be equal to 0 as well. But when the diode is on, then you just have to solve the Ohm's law. The drop across the diode is 0 volt, so the whole Vin is going across the resistor. So just as before, we're gonna have that the current will look like this, and where these points will be equal to V peak divided by R. As you can see, the circuit took an alternating voltage as an input and returned an output voltage and current that are only positive. Circuits similar to these are employed in many products to convert AC voltages, like the voltage in your home power network, to direct voltage that is required to run electronic product. It's also easy to understand why the circuit is called half-wave rectifier. If we compare the input and the output of the circuit, you can see that in a way the circuit got rid of half of the wave. The negative part of the curve of the input voltage has been eliminated, and only the positive part was able to pass through the circuit. So the circuit is called half-wave rectifier. In this lesson, we will look at another important application of diodes. The schematic on the right is just a fraction of the overall schematic of the Arduino board, a famous open source electronic platform. Let's find each of the components on the board. First we see a big component called X1. This is a connector that you can see here on the board. Here is where you connect your jack to provide a 12-volt supply to the board. Then we have a diode, D1, which is obviously here. Then we have two electrolytic capacitors, PC1 and PC2, and they're obviously here. This is PC1 and this is PC2. Then we have a small capacitor called C2, which is here. And finally we have a chip that is used to convert 12 volts into 5 volts. As you can see, after this chip the voltage has become 5 volt, which is called U1, and it is this component here. For the purpose of this lesson, we can forget about most of these components and we can focus just on D1 and X1. So let me delete all these markings. So this one is X1 and this is D1. So what is the function of D1? Very simple. D1 is used to protect the circuit against connecting the power supply upside down. Note that doing this is really hard, because the 12-volt receptacle and the corresponding jack are standard components and are keyed, meaning that you can only connect them in one way, the correct way. But let's say that the power supply that is connected to the jack is compromised, and somehow the positive and the negative terminal got swapped. Now if you connect the power, you will be providing minus 12 volt instead of plus 12 volt. This can break all the components on the circuit, and you would find yourself with a bricked board. To protect against that, the designer put a simple diode in series with a 12-volt power supply. Now, if the voltage that is applied is negative, the diode will turn off and act as an open circuit, protecting the components downstream. So it will be like this, just like an open circuit or an open switch. No voltage is applied to the components that follow, and no current can flow. So the board is protected. Conversely, when the voltage is positive, the diode turns on, behaves sort of like a short circuit or a closed switch, and the circuit is allowed to function. This application is called reverse polarity protection.